So this is the entire syllabus. So the subtopics in each and every bigger topic. Convection में forced and free convection we will complete, heat exchanger, LMTD effectiveness, radiation definition, laws, analysis, everything will be covered. So this is the GATE entire syllabus for heat transfer. All right. So before I start, let me quickly give you the idea of the reference book you can follow for the heat transfer. One is Yunus A. Sengel, very important and beautifully written book for heat transfer. Conceptual clarity, you can follow Sengel, and you can go with the Holman also. But if you are seriously attending all our lectures, if you are sincerely giving your full attention to our courses, these sessions, then it is not required to refer any book, because there is no time. The gate is around the corner. So the more you practice, the more comfortable you become. So practice is very important rather than studying the theory from these books. So the notes are already there. If anybody is not having the notes with them, you can always ask us to share the notes through the Telegram group. All right. Yes, so let us begin the subject. Please do let me know, what do you understand by the term heat transfer? We are going to discuss the mechanism of the heat transfer. Mechanism or principle of the heat transfer. What are the various modes of heat transfer? What are the various modes of heat transfer? What is the prerequisite? What is the condition? Convection, Bhaumik, be with us. We will discuss all your doubts. We will clear all your doubts, provided you should have full energy, full power, full motivation to the session. So for heat transfer to take place, the most important thing is the temperature difference. The temperature difference, whenever there is a temperature difference, the energy will transfer in the form of heat, or we can call it as thermal energy. The flow of energy will take place due to temperature difference, and that always takes place from high temperature to low temperature region. These are the two things which are important for this. One is there has to be a temperature difference. The another thing is the direction of heat transfer will always be from high temperature to low temperature. That was given by Clausius' statement of second law. That is the Clausius' statement of second law of thermodynamics, which says heat always flow from high temperature to low temperature. But in thermodynamics also we study the about the heat transfer, heat and work transfer, the energy interaction with system and surrounding. But what makes the heat transfer different from thermodynamics? These are the points which differentiate these two subjects. So there is a possibility that the question might come combining both the subject together, because there is a close connection between heat transfer and the thermodynamics. The one major difference between the thermodynamics and heat transfer is thermodynamics takes place when the systems are in thermodynamic equilibrium. When the system is in thermodynamic equilibrium, right? But the heat transfer takes place due to non-equilibrium, when there is a temperature difference, if T1 is not equal to T2. And that is the reason heat transfer is called as transient phenomena. That is the reason we call the heat transfer to be a transient or the temporary phenomena, because the heat will flow until the temperature of both the bodies become same. As long as there is a temperature difference, the heat will flow. The next major difference between heat transfer and thermodynamics is time is not a variable. I will use tau for time. Time is not a variable. Time will be constant. Time will be constant. But heat transfer talks about the time. Time is the variable parameter. We will talk about the variation of heat transfer with time, variation of temperature with time. And then the last difference is the thermodynamics talks about the total heat transfer in joule or kilojoule. that is a scalar quantity, whereas in heat transfer we will talk about the rate of heat transfer, that is joule per second or watt. Q, I will use the notation Q, that is a vector quantity, rate of heat transfer in a particular direction. All right, yes. Yes, what are the various modes of heat transfer? There are 3 modes of heat transfer. It can be, the heat transfer can be due to conduction, the flow of heat energy can be due to conduction, and it can be through radiation, or it can be mix of 2 or more modes of heat transfer. These are the various modes of heat transfer. We will be discussing one by one in the entire subject. Bataiye, what makes the difference? How we come to know whether the heat transfer is due to conduction, convection or radiation? The major difference between these 3 modes of heat transfer is the medium. It is the medium which differentiates the mode of heat transfer. What is the medium? The region between the one surface and the other surface, which are having the temperature difference. The points which are having the difference in the temperature are separated by some medium. So medium will be going to decide whether the mode of heat transfer will be conduction, convection or radiation, or 2 or more of them. So first of all, before proceeding further, let us discuss about the difference between these modes of heat transfer, because first of all you should understand what will be the mode of heat transfer which will be applied, and accordingly the analysis will be based on that particular mode only. All right, yes Naveen, through medium. When the medium is stationary, when the medium is stationary, like solids are an example of a stationary medium. It means there is no relative motion. When there is no relative motion in the medium or in the particles of the medium, then the medium is said to be stationary. The mode of heat transfer will be conduction. And in case of dynamic medium, what does that mean? Liquid and gas are example of dynamic medium when there is a relative motion between the particles of the medium. When there is a relative motion, then the mode of heat transfer will be convection. And for radiation to occur, there is no requirement of the medium. Radiation can occur in vacuum also. So what we can say about radiation is everywhere. Radiation will be everywhere. Along with convection, there will be radiation. Along with conduction also, there will be radiation. In stationary medium also, there will be radiation. In dynamic medium also, there will be radiation. So radiation will be everywhere, but radiation becomes important when there is no medium. Because when there is no medium, in case of vacuum, the only possible mode of heat transfer is, in case of vacuum, the only mode of heat transfer is radiation. So when conduction and convection occurs, we generally ignore the effect of radiation. Conduction is internal phenomena, or we can call it as microscopic phenomena, because the molecules or atoms or electrons are taking part in the transfer of heat through conduction. So that is why it is called as internal phenomena. It takes place inside the solid or 2 solids in physical contact. Similarly, convection is a surface phenomena. When a surface is in contact with the fluid at a different temperature, the mode of heat transfer will be convection, because in fluids, the medium is dynamic. When it is a fluid, the medium is a fluid, then it is a dynamic medium, and the surface will exchange the heat with the fluid. That is why it is called as surface phenomena, and radiation is known as the wave phenomena. All right. So I am talking about the basic introduction first, and then we will proceed to the steady state conduction. Convection is also called as macroscopic phenomena. Why it is called as bulk phenomena? Because the particles are involved. The fluid particles are involved in transferring heat due to convection. That is why it is called as macroscopic phenomena, and the radiation takes place in the form of electromagnetic waves which travel in the straight line motion due to change in electronic configuration of atoms, molecules or subatomic particles. The most important thing about conduction is the conduction takes place due to diffusion of energy. What is the meaning of energy diffusion? Anybody can tell me what is the meaning of diffusion of energy? Diffusion of energy means the molecules which are at higher temperature have more vibration, they collide with the adjacent molecules and they transfer the heat to the adjacent molecules. Getting the heat, the adjacent molecules will also start vibrating and they will transfer the heat to their adjacent molecules. So the heat is getting conducted layer by layer through the molecules or through the electrons or through the atoms. So that is why it is known as diffusion of energy. And for diffusion of energy, the temperature gradient will be required. For conduction to take place, there has to be a temperature gradient along with the temperature difference. That is important. All right. And convection can be called as mixing or circulation of the fluid particles. The particles which are at higher temperature, they mix with the particles with the lower temperature and there is a continuous circulation of the fluid particles, and that is how the fluid gets heated or the fluid gets cooled. All right. Yes. So let us start with the just a second. Yes. So conduction. Let us start with the conduction, which occurs due to diffusion of energy. Conduction is given by Fourier law. The law governing conduction is Fourier law. What is Fourier law? According to Fourier law of heat conduction, the conduction heat transfer rate in a particular direction x is given by minus k into a into dt by dx. There has to be a temperature gradient for conduction to take place. Minus k into a into dt by dx. dt by dx is the temperature gradient. What is a? A is the area perpendicular to the direction of heat flow, perpendicular to x direction. If the heat transfer is taking place in x direction, area will be, A will be the area which is normal to the direction of conduction, and K is known as thermal conductivity of the fluid. K will be called as the thermal conductivity of the fluid, and that is why the Fourier law of conduction is called as the defining expression for thermal conductivity. You should understand the significance of each and every term. Why there is a negative sign here? Can you just let me know why there is a negative sign? What is the significance of this negative sign in case of Fourier law? Because dt by dx is always negative. In the direction of heat flow, there has to be a decrease, negative temperature gradient, or the temperature must decrease in the direction of heat flow. Then that is why, because it is negative, to make the conduction heat transfer rate positive, this negative sign is inserted. Or we can say, to satisfy the Clausius statement of second law of thermodynamics. I hope this is clear to everyone. If anybody is having any doubt in any of the expression or any of the parameter which is used in the expression, you can just let me know. Similarly, we can write Qy is equal to minus thermal conductivity, area perpendicular to y direction, into the temperature gradient along y direction. All right, the temperature gradient along y direction. This is how we can write the Fourier law for conduction. So it is the defining equation for thermal conductivity. What is the unit of thermal conductivity? What is the unit of thermal conductivity? Quickly, do let me know. How to define K? That is equal to minus Q upon A into dt by dx, isn't it? Minus Q upon A into dt by dx. So what is the unit of thermal conductivity? It will be watt per meter square, or watt per meter Kelvin, or we can write it as watt per meter degree Celsius. That is the unit of thermal conductivity. Thermal conductivity is the property of the material. It is decided by a particular material. Yes, Ashank. Yes, Negiji, Rishikesh. Well done, Aditya. Thermal conductivity is the property of the material. What its significance is, it gives us the information about the ability of a conduction in a particular material. What does that mean? More is the thermal conductivity of a particular material, more will be the ability of conduction in that particular material. All right. So it gives the ability of conduction in a particular material, and thermal conductivity is a function of temperature. It is a temperature dependent property like any other property. All right. So please guys, do share the link of this session to all your friends so that more and more people join and get benefited. We also get the motivation from the students. When more and more students join, we also feel positive, we also feel energetic. So it definitely improves our performance also. This is the general behavior of the thermal conductivity of the material. The maximum thermal conductivity is among the pure metals. The pure metals are having maximum thermal conductivity, and then comes metallic alloys. If they are alloys, they are having relatively lesser thermal conductivity. Non-metals are having lesser thermal conductivity than metals, like construction materials. Then comes the liquid, then insulator like cork, wood, etc. And finally, the least thermal conductivity is among the gases. Yes, Aditya, I will talk about the mechanism of conduction. First of all, you need to understand, in conduction, not only the molecular vibration, it is sometimes the molecular vibration, it's sometimes the electron flow, it is sometimes the atomic vibration. So atoms, molecules, electrons, they are all involved in transferring the heat through conduction. I will talk about this. So in liquid, how the mechanism of conduction takes place. In gases, how the mechanism of conduction takes place. In insulator, metals, how the conduction takes place. I will be discussing that. Let us start with the gas. So many students have a confusion because in gas, the medium is dynamic. I have already told you, when it is a gas, it is a dynamic medium. But when it is a dynamic medium, how the conduction can take place in the medium, in the gas. So in gas, the parameters which are involved in transferring heat energy through conduction is molecular collision and molecular diffusion. It is the molecular collision and molecular diffusion which governs the conduction in case of a gas. So in gas, this dominates. This is the dominating parameter. Try to understand this. Mechanism of conduction in gases, the collision of the molecules, because the molecules are widely spaced. The molecules are widely spaced. More is the molecular collision, more will be the thermal conductivity of the gas. The molecular collision decides the, so we can say, as the molecular collision increases, thermal conductivity of the gas also increases, right? So the faster the molecules move, faster they will transport thermal energy by conduction. That is the mechanism of conduction in case of a gas. And the molecular collision is decided by molecular velocity. So we can say molecular velocity is directly proportional to thermal conductivity of a gas. In case of a gas, molecular velocity will decide the conduction ability or the thermal conductivity. Is this clear? And according to kinetic theory of a gas, what we can say, half mv square is equal to 3/2 k into T. K is the Boltzmann constant. So half mv square is 3/2 kT. So from here we can say the molecular velocity is directly proportional to under root T for a gas. If we combine these together, then we can get the mathematical expression relating the thermal conductivity of a gas and the temperature. thermal conductivity of a gas is directly proportional to under root T, but T is the absolute temperature. What is T here? T will be the absolute temperature. Yes, what is the absolute temperature? Absolute temperature means in Kelvin only. The temperature must be in Kelvin. If the temperature is given in degrees Celsius, we can add 273 to make it temperature in Kelvin. So as the temperature of the gas increases, the thermal conductivity of the gas will also increase. As the temperature of the gas decreases, the thermal conductivity will also decrease. That is how the conduction takes place in case of gas. Again, in liquid also, these are the two parameters governing the conduction. Again, the same parameters, the molecular collision and molecular diffusion. What is the difference between the conduction in gas and conduction in liquid? The major difference is in liquid, the molecular diffusion dominates. In case of liquid, it is not the molecular collision which dominates, which governs conduction. It is the molecular diffusion which governs conduction in case of a liquid. But in case of a gas, it is the molecular collision. Why the molecular diffusion governs the conduction in case of liquid? Because the molecules are closely spaced. The molecules are closely spaced. So physical mechanism of thermal energy conduction is same as gas, but more complex because molecules are closely spaced in case of a gas. Because the molecules are closely spaced, that is why the collision will not govern the conduction. It is the diffusion of energy that governs the conduction in case of liquid. And as the temperature of the liquid increases, molecules move away from each other. You all know, when we increase the temperature, there is more space between the molecules, and if the molecules move away, then we can say the molecular diffusion decreases. Diffusion of energy. Diffusion of energy is transferring of energy from one molecule to another adjacent molecule. That is called as energy diffusion. So molecular diffusion decreases, and that is why thermal conductivity of the liquid will decrease. So diffusion is the dominating parameter in case of liquid, whereas molecular collision is the dominating parameter in case of gas. Now let us talk about the solid. What are the factors governing conduction in solid? In solid, lattice vibration and flow of free electrons. These are the two factors which governs conduction in case of gas. Drift of free electrons and the lattice vibration are the governing factor in case of solid. Governing factor for conduction in case of solid. Now what we can say from here is, as the temperature of the solid, or if electron flow or lattice vibration. What is lattice vibration? Lattice vibration is the vibration of molecules at about their mean position. As the electron flow or lattice vibration increases, then the thermal conductivity of solid also increases. As the lattice vibration or electron flow, if any of them increases, then that will increase the thermal conductivity of the solid. But the problem here is in case of solid, if the temperature of the solid increases, if we increase the temperature of the solid, then what happens? The lattice vibration increases. The lattice vibration increases, but the flow of free electrons decreases. So we cannot, by checking the temperature, we cannot say whether there will be increase in thermal conductivity or will there be decrease in thermal conductivity, isn't it? Whenever we increase the temperature of the solid, the molecules have more vibration about their mean position. So lattice vibration increases, and due to more lattice vibration, the flow of free electrons is disturbed. So the flow of free electrons decreases. So we need to check out of these two factors which is actually governing conduction in solid. Can you just let me know which will decide? Will it be lattice vibration or electron flow? Which is going to decide the conduction in case of solid, which is the dominating factor in case of solid. Now, your turn. Can you just let me know? Everyone, do let me know. There are two factors governing conduction in case of solid: free electron flow and lattice vibration. My question to everyone is, when we increase the temperature, lattice vibration increases, but the flow of free electrons decreases. So what happens to the thermal conductivity of the solid? What is going to govern the thermal conductivity, whether it will be lattice vibration or flow of free electrons in case of solid? Everyone, please do respond. बताइए quickly. Now here, the solid can be divided into two parts. Here we can divide the solid into two parts based on their molecular structure. Now Bhaumik, Naveen, Aditya, sabka galat hai. When I talk about solid, we cannot judge, we cannot decide whether it is lattice vibration or free electron flow. So it is actually decided by the type of solid. If it is a conductor, or metal, if the solid is a conductor or a metal, then the contribution of free electron flow will be more compared to the contribution of lattice vibration. In conduction, in case of metals or conductor, because of the crystalline nature of the structure, it is well organized molecular structure, and because of which the dominating factor is free electron flow. So whenever we are going to talk about the conductor or metal, we will focus on this parameter. This will be the dominating parameter. This dominates. Free electron flow dominates, and lattice vibration is less dominating. So as the temperature of the conductor increases, or temperature of the metals increases. If we increase the temperature of the metal, I have already told you, when we increase the temperature of the solid, what happens to electron flow? We will focus on the electron flow. Focus on the electron flow. So what happens to the electron flow? Flow decreases, and that will decrease the thermal conductivity of metal or conductor. That will decrease the thermal conductivity of the metal or conductor. Is this clear? But when the solid is an insulator or non-metal, when the solid is not a metal, if it is a non-metal or insulator, then the contribution of free electrons is very less. The dominating parameter is lattice vibration, which governs 90% of the conduction in case of non-metal. So in case of non-metal or insulator, the lattice vibration governs the conduction. So if the temperature of non-metal increases, then we will not focus on this parameter. We will see what happens to lattice vibration, and because of the increase in the lattice vibration, the thermal conductivity of the non-metal or insulator, because of amorphous molecular structure, disorganized molecular structure, the non-metals will have an increase in thermal conductivity as the temperature increases. So I have talked about 4 types of materials. I have talked about the gas, I have talked about the liquid, the dominating factor. I have talked about, in case of liquid and gas, molecular diffusion and molecular collision governs the conduction. But in case of gas, the molecular collision is the dominating factor. In case of liquid, molecular diffusion is the dominating factor. Similarly, in case of solid, we can classify the solid into 2 types based on the molecular arrangement, molecular structure. If the solid is a metal or a conductor, then the free electron flow governs the conduction. But whenever it is non-metal or insulator, the lattice vibration start governing the conduction. So accordingly, we can decide the variation of thermal conductivity with the temperature. So what we can say from here is, conductors are having more thermal conductivity at lower temperatures and insulators are having more thermal conductivity at higher temperatures. Is this clear? Do you agree with this point? For better conduction of ability, for better thermal conductivity of the material, if we are using a conductor, then the conductors must be used at a lower temperature because they have better thermal conductivity at lower temperature, whereas the insulators are kept at higher temperatures. Is it all fine with everyone? Please give me thumbs up, everyone. If anybody is having any doubt, you can just let me know. Otherwise, can I expect a thumbs up from each one of you? So if I summarize everything, temperature versus thermal conductivity, temperature on x-axis and the thermal conductivity on y-axis, then that by increasing the temperature, thermal conductivity decreases. In what? In case of liquid, in case of conductor, in case of metal. Whereas when we talk about the variation of thermal conductivity in case of a gas, it increases with the rise in temperature. For a gas, insulator or non-metal. This is the summary of the mechanism of conduction in different materials. All right. There is a question on the screen. Now let me know the answer to this question, everyone. Those who are here, keep on responding, keep on asking your doubts. We will be more than happy to assist you with your doubts. Do let me know. What is the answer to this one? Can you see the question? As the temperature increases, what happens to the thermal conductivity of the gas? As the temperature increases, thermal conductivity of the gas. So for a gas, thermal conductivity of a gas is directly proportional to under root T. That is the mathematical expression according to kinetic theory. So it increases in case of a gas also, in case of insulator also, in case of non-metal also. It decreases in case of a liquid, in case of conductor, in case of metal. All right. Option A is the correct answer. Very good. Good. Raju Naik, Sujesh, Naveen, Rishikesh, well done guys, Sandeep, everybody had given the right answer. Now, the next mode of heat transfer is convection. What is the governing law for convection? Can you let me know what is the governing law for convection? Which law governs convection? Everyone. Convection is a bulk phenomena. Bulk or macroscopic phenomena. Convection is a bulk or macroscopic phenomena. Which law governs convection? It is the Newton's law of cooling governing the convection, which gives the defining equation for convective heat transfer coefficient. According to Newton's law of cooling, Q convection is given by H into a surface area. It is a surface phenomena into delta T. That is the mathematical expression for convection heat transfer rate. That is joule per second or watt. You should know the significance of this AS. AS is the surface area here. In case of conduction, it is the area which is perpendicular to direction of conduction. But in case of convection, it is the surface area which is available for convection. And how do we find out what is the surface area which is available for convection? The surface area which is in contact with the fluid. The surface area of the body which is in contact with the fluid, the mode of heat transfer between the surface and the fluid will be convection. So it will be the surface area, and delta T is bulk temperature difference. What is delta T? Is it surface temperature minus fluid temperature or fluid temperature minus surface temperature? If surface temperature is greater than the fluid temperature, the heat will flow from the surface to the fluid by convection. Then it will be Ts minus Tf, and it will be Tf minus Ts when Tf is greater than Ts. If the fluid temperature is more than the surface temperature, then the heat will flow from the fluid to the surface. It is always flow from high temperature to low temperature. And if the surface temperature is greater than the fluid temperature, then the heat will flow from the surface to the fluid. That is known as bulk temperature difference. We call it as bulk temperature difference. All right. And what is H here? H is known as convective heat transfer coefficient. Is it a property? Yes or no? Please write Y in the comment section for yes, and please write N in the comment section for no. Y for yes, N for no. Quickly. Is the convective heat transfer coefficient is a material property or a fluid property? Is it a fluid property? Is it a property of a fluid? Yes or no? Now, because in the fluid, the convection is taking place. The mode of heat transfer in the fluid is convection. Why? Because of bulk motion of the fluid, because of the relative motion in the medium, the mode of heat transfer will be convection. And based on the fluid motion, because it is the fluid motion, so convection can be classified in two types based on fluid motion. So that is why convection is all about fluid mechanics. Based on the fluid motion, the convection can further be classified as forced or artificial convection. When do we call it as forced convection? When the fluid is forced to flow by using some external means. When the fluid is forced to flow by using some external means, then it is called as forced or artificial convection. The two factors governing the forced convection or the fluid motion in case of forced convection, one is the pressure gradient. There is the negative pressure gradient developed. Pressure gradient. And due to the pressure gradient, there is an inertia force acting on the fluid particles to make them move from high pressure to low pressure region. So pressure gradient and the inertia force are the two factors which governs the flow of fluid by external means, like a pump. So the convection will be called as forced convection when the fluid is forced to flow by using some external means, and the another will be natural convection or free convection. The next one is natural convection when the fluid flows naturally without any external means. When the fluid is flowing without any external means, then it is called as natural convection. And for the fluid motion, we should call it as fluid motion. For the fluid to have a motion, the density gradient plays an important role. The density gradient d rho by dy, positive density gradient. How the density gradient develops? The molecules which are at higher temperature, expands, and because of expansion they become light and they move in upward direction. The heavier molecules which are away will come back. So that is called as mixing of the fluid particles. That is why it is called as mixing. The fluid particles which are at higher temperature, they expand due to heating, and due to expansion their density decreases, and due to decrease in the density, so rho1 is less than rho2. Due to density difference, the buoyant force acts on the fluid particles, and due to buoyancy, there is a mixing of the fluid particles. The particles will start moving in upward direction due to buoyant force, and the heavier particles will come down. That is how the free or the natural convection. In both type of convection, there is a motion in the fluid. When the motion in the fluid is done by using some external source, then it is a forced convection. And when the motion of the fluid takes place on its own without any external source, natural way, then it is the free convection. Can anybody give me an example of natural convection? Can anyone give me an example for natural convection? Example for forced convection, I can write automobile radiator. Anybody can give me an example for natural or free convection? Yes, when you heat water in a container, that is a natural convection. We are not forcing the fluid to move, but yes, you can see the circulation, mixing you can see. When you observe the boiling water in a container, yes, T is a natural convection. T की याद दिला दी आपने. It is the time for having a tea. So T is an example. The tea gets cold when it is kept on a surface or when it is kept on a table, is an example of natural or free convection. I was asking about the convective heat transfer coefficient. I asked you, will it be a material property? The convective heat transfer coefficient is not a property of a material, but an experimentally determined very complicated parameter. Convective heat transfer coefficient is not a property of a material. It is not a property of the material, but it is an experimentally determined very complicated parameter. Why do we call it as complicated parameter? Because convective heat transfer coefficient depends on so many factors, like the type of the fluid, whether it is a liquid, H will be different, gas, two-phase fluid, or it depends on the properties of the fluid, density, viscosity, thermal conductivity, specific heat, etc. It depends on the type of the fluid motion. I hope you are comfortable, you are clear with the type of fluid motion, laminar and turbulent. Laminar means organized flow, turbulent means disorganized flow. So it depends on the nature of the fluid motion, whether it will be laminar or turbulent. How do we identify whether the motion of the fluid is laminar or turbulent? How do we identify, how do we find it out whether the motion of the fluid is laminar or turbulent? बता सकते हैं? बताइए. And it also depends on the surface geometry. When the fluid is kept on a plate, fluid is flowing in a pipe, or fluid is flowing over a sphere, yes, it is always the Reynolds number. So here we will be talking about fluid mechanics. And the last point is very, very important. The convection is actually, the last point is very, very important. Let me know if you know about this last point or not. The film conductance. Somebody has written. किसने लिखा था in the comment section? Film conductance. This H is known as film conductance. Why we call it as film conductance? Because of its combination with the conduction. Convection is the combined effect of conduction, that is the diffusion of energy, and the fluid motion, that is the mixing of the fluid particles. So what happens is, try to understand this last point. What happens is, when a fluid is kept on a surface, the fluid particles in direct contact with the surface will stick to the surface. The fluid particles in direct contact with the solid surface will stick to the surface, or they will have no slip over the surface. That condition is called as no slip condition, and in no slip condition of the fluid, the mode of heat transfer is definitely conduction. And outside the no slip region, the mode of heat transfer is convection. So that is why, that is the reason H is also known as film conductance. What is the unit of H? What is the unit of H? H can be written as Q convection upon surface area into delta T. That is the mathematical expression for H. Q upon AS into delta T. What is the unit of H? Either we call it as Kelvin or degree Celsius, does not make a difference. Either we write it as Kelvin or Celsius, does not make a difference. Why? Because as long as we are talking about the difference in the temperature, as long as we are talking about the temperature difference, it does not matter whether we take the difference in the temperature in Kelvin or degree Celsius. So the last point, if we write the last point in mathematical terms, then what we will get is, this is going to be very, very important. Look, this is the surface which is maintained at temperature Ts, and this is the fluid. This is the temperature of the fluid, bulk temperature of the fluid. T infinity is the bulk temperature of the fluid. Now in the no slip region, this is the no slip region, let us say. In the no slip region, the mode of heat transfer will be conduction. And outside this no slip region, here the mode of heat transfer will be conduction, and here the mode of heat transfer will be convection. So convection is combined effect of conduction in the no slip region and the bulk motion of the fluid outside. The fluid in the no slip region will have no relative motion. The fluid in the no slip region, it is very small region. This region is very, very small region. So if we write the energy equation, we can say Q conduction is equal to Q convection, isn't it? The rate of heat transfer by conduction will be equal to the rate of heat transfer by convection. So H, or conduction I am writing, so it will be minus K of fluid. Why K of fluid? Because we are applying the conduction in the fluid only. Thermal conductivity of the fluid into area perpendicular to the direction of heat flow. What is the direction of heat flow? Heat flow direction will be in y direction. This is y direction. The heat flow will take place in the y direction. So area perpendicular to y direction into dt by dy in the fluid at y tends to 0. That is called as no slip region. Y is equal to 0. No slip region is y tends to 0 or y is equal to 0. Is equal to convection is Newton's law of cooling, H into surface area available for convection. Do you agree the surface area available for convection is same as the area which is perpendicular to the direction of conduction into delta T? So if you calculate this H from here, so H will be written as minus thermal conductivity of the fluid into dt by dy, temperature gradient in the fluid at y tends to 0 or y is equal to 0 upon bulk temperature difference between the fluid and the surface. What is delta T? We can say delta T is equal to Ts minus T infinity here. That is how we can find out the convective heat transfer coefficient. For dt by dy, if we want to get dt by dy at y is equal to 0, we need a temperature profile. Without knowing the temperature profile, we cannot find out dt by dy. And how the temperature varies in the fluid, to get that information, we need to know the velocity variation in y direction. And that is how the fluid mechanics comes into picture. Then we can say, then we will jump to the heat transfer, and then we will find out the convective heat transfer coefficient. That is how it works. First of all, we will talk about the fluid mechanics, how to get the expression for u as a function of y. Then from here we will jump. What is the connecting link between the velocity profile and the temperature profile? Can you just let me know what is the connecting link? Which parameters connect the velocity profile with the temperature profile in the fluid? I hope this is clear. This is very, 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 very important. This is going to be very, very important. Sometimes they might give you temperature profile. You can find out dt by dy and put y is equal to 0, because it should be dt by dy should be taken at the surface. In case of conduction, the temperature gradient will be required. And for convection, the temperature difference, bulk temperature difference will be required. For convection, bulk temperature difference, and for conduction, the temperature gradient. So the temperature gradient must be taken at y is equal to 0. All the parameters are for the fluid only. Thermal conductivity of the fluid, yes, it is the Prandtl number. We will talk about that when we will discuss convection in detail. Very good. Good, Kartikeya, Manas, well done. Can we proceed further? And the next mode of heat transfer, I am just giving you the brief introduction about the various mode of heat transfer, which is going to help you to understand the detail about the various modes. The radiation mode of heat transfer without any material medium, the radiation can occur. And that is due to change in electronic configuration of atoms, molecules, and subatomic particles. And it is a wave phenomena. According to Maxwell's theory, it will be the wave phenomena. What is the governing law for radiation? Which law governs radiation? Which law governs radiation? Do let me know. The radiation is governed by Stefan Boltzmann law, which is defining equation for Stefan Boltzmann constant sigma. It is defining equation for Stefan Boltzmann constant. So according to Stefan Boltzmann law for radiation, the heat transfer rate due to radiation for an ideal black body is given by sigma into surface area of the black body, which is available for radiation. Radiation is also a surface phenomena. It is also a surface phenomena. We are talking about thermal radiation. Thermal radiation is the surface phenomena. Sigma into As into T to the power 4. That is the expression for radiation, where T is again the absolute temperature. It must be in Kelvin. I have told you absolute temperature in case of kinetic theory of a gas, as well as it is the temperature must be in Kelvin in case of radiation mode of heat transfer as well. Sigma into As into T to the power 4. And that gives the defining expression for sigma. What is the unit of sigma? What will be the unit of sigma? So sigma is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. We cannot have it degree Celsius to the power 4. We cannot have it degree Celsius. Why? Because T must always be in Kelvin. It is not the temperature difference. So that is how these are the three laws which governs the various modes of heat transfer. For conduction, Fourier law, which defines the thermal conductivity. For convection, Newton's law of cooling, which defines the convective heat transfer coefficient. And the third one is the radiation. For radiation, Stefan Boltzmann law, which is defining equation for Stefan Boltzmann constant sigma. That is for black body. For non-black body, for a non-black body, we can say Q radiation for a non-black body will be equal to epsilon multiplied by Q radiation for a black body. Or we can say epsilon into sigma into As into T to the power 4. That is, what is epsilon here? Epsilon is called as emissivity. We will discuss, or Suraj sir will be going to discuss more about the emissivity, that is also known as color factor. Emissivity lies between 0 and 1. Emissivity is a positive fraction. For emissivity, when it is 0 or almost 0, it can be treated as a white body. For emissivity to be maximum, that is 1, it is a black body. So that completes our general introduction for absolute 0 cannot be possible because molecular activities stops at absolute 0. Hello Sharma ji, what's up? क्या हाल चाल, नमस्कार, आदाब, सुप्रभात, good morning, सत श्री अकाल, अस्सलाम वालेकुम, वणकम. Good morning guys. Those who have joined me recently, we have just discussed the basic introduction about the various modes of heat transfer. Absolute 0 cannot take place in practical or in practice, because at absolute 0 the molecular activities stops. So that is impossible to achieve. All right. So there is a question on the screen. Can you just let me know the answer to this question? Everyone, please open your notebook. Try to solve the question and keep your keyboard handy. Try to write whatever you feel like, your suggestion, your doubts. The more you share, the more you communicate with me, the more energetic the session will become, the more fruitful the session will become. There is a question on the screen. Let me see who will be the first one. Fastest finger first, who will be giving me the correct answer for this. And then we will proceed to the next part of our analysis. That is going to be very, very interesting. Steady state conduction we will be starting next. Yes. Two spares A and B of same material. Same material means same emissivity. It is the property of a material. Same material means same emissivity. Have radii 1 meter and 4 meter and temperature 4000 Kelvin and 2000 Kelvin respectively. Which one of the following statements is correct? So we can say QA by QB, the mode of heat transfer will be radiation. The energy radiated by spare A and B. So we can say sigma getting cancelled out. AA into TA to the power 4, sigma into AB into TB to the power 4 into epsilon A into epsilon B. That will be the expression. These will get cancelled out. AA and get cancelled out. Surface area will be 4 pi r square. So it is RA square or RB whole square into TA by TB to the power 4. Temperature must be in Kelvin. What is the answer for QA by QB? What do you get? What is QA by QB? Are you getting 1? Are you guys getting 1 or not? 4 pi r square is the surface area because they are spare. Area is 4 pi r square. All right. So the correct answer is option C. Who had given the correct answer fast? Azmira. Well done. Sharmaji, Vinit, Bhaumik, Manas, Sujis. Good guys. Good. Keep it up. Now let us start talking about, now we will not be talking about conduction in case of liquid or gas. Conduction happens in liquid and gas, but only in the no slip region. So in solids, throughout the solid, the mode of heat transfer is conduction, and due to diffusion of energy, this is how the energy diffusion takes place. The molecules, this is let us say T1 temperature, this is let us say T1 temperature, this is let us say T2 temperature, and T1 is greater than T2, then the heat will flow like this. The molecules which are at high temperature vibrate, they transfer heat to their adjacent low temperature molecules. That is how energy diffusion takes place, and the heat flow is taking place in X direction. So there must be a temperature gradient in X direction. For the heat flow taking place due to conduction in X direction, dt by dx should be non-zero. What is the unit of dt by dx? Temperature gradient. What is the unit of temperature gradient? Either we write Kelvin per meter or degree Celsius per meter. Why? Because dt is the difference in temperature. Kelvin per meter or degree Celsius per meter. So let us start talking about the conduction in solid. Conduction in solid. But before that, we need to understand the basic energy conservation equation for any solid. The energy conservation equation for any solid. Look, if this is our solid system, this is our system. If we talk about the energy conservation equation for the system, there is the heat entering into the system. There is a heat generated in the system. There is a possibility of heat generated in the system. Plus there is a possibility of heat stored in the system. And there is a possibility of heat leaving from the system. So for this system to have the energy balance, what we can say, the heat entering into the system plus the amount of heat generated in the system per unit time is equal to the amount of heat leaving from the system per unit time plus Q stored. That is the basic energy conservation equation for any system, for any solid. There are 4 terms involved in the energy conservation equation. It is like your bank account. The system is like your bank account. So, money is getting credited in your bank account, that is Q in, and you also the salary get credited in your bank account, that is Q in, and you also generate some amount or some money by doing some extra work, that is generation of the heat in the system, and you are spending some amount, that is the heat leaving from the system, and the remaining portion will be your saving, that is stored. Stored will be your saving. Stored will be your saving. Q in is your salary, and Q generation will be your extra income. Extra income, like under the table. If you are in a government job, you can have some more income under the table, or you can do part-time job earning some extra income, and Q out is your expense plus saving. So this is how the conservation will take place. This is the energy conservation equation. What is Q generated? How the heat gets generated in the system. How the heat gets generated in the system. Heat generation, heat is a form of energy, isn't it? It is a thermal energy. And we have been studying from our childhood that energy can neither be created nor be destroyed. Then what is the meaning of heat generation? What is the meaning of heat generation? Heat generation is nothing but some other form of energy getting converted into heat energy. Like there is a possibility electrical energy gets converted into heat energy. In a current carrying wire, the electrical energy converts into heat energy. The heating of the wire takes place. Or it can be nuclear energy getting converted into heat energy. In nuclear reactor fuel rod. Or it might be some chemical reaction that also generate energy. Chemical energy getting converted into heat energy. So these are the various possibilities of generation of the heat in the system. Some other form of energy is getting converted into heat energy, that is called as heat generation. And what is the meaning of storage of heat in the system? Whenever the heat gets stored in the system, it increases the internal energy. Change in internal energy of the system. Change in internal energy of the system when the temperature start varying with time, or it is unsteady state system. When the internal energy starts changing in the system is said to be in unsteady state. When there is a change in internal energy of the system is called to be in a steady state. So heat generation, there is a term defined for heat generation that is called as Q dot. I will use Q dot. That is the rate of uniform heat generation per unit volume. Rate of uniform heat generation per unit volume of the system. And so the unit will be watt per meter cube. The unit will be watt per meter cube. That is the rate of uniform heat generation per unit volume. So if I write in mathematical terms for this energy conservation equation, so Q generation can be written as, this Q generation can be written as Q dot into volume of the system. Can we write Q dot into volume of the system? That is the heat generation rate. And Q stored can be written as M into C, mass of the system, into specific heat, into dt by d tau. M into C into dt by d tau. M into C into dt by d tau is the amount of energy storage in the system. Change in internal energy is MC delta T. Change in internal energy is MC delta T per unit time. That means MC delta by delta T, or dt by d tau. That is how we will use the energy conservation equation. Now, if we develop the heat conduction equation for a system along heat flow direction as x direction. So this is our system now. This is our control volume, or we can call it a system. This is our system. So there is the heat entering into the system in x direction. Qx, that is in. Qx plus dx can be written as Q. This is Q out. There is a possibility of generation of the heat. If A is the area of the system, normal to the direction of heat flow is constant. So Q generation is Q dot into A into dx is the volume. A into dx is the volume. So if we write, then we can say heat entering into the system plus heat generated in the system, Q dot into A dx is equal to heat leaving from the system, that can be written as Qx plus dx, plus heat storage. M, what is the mass? That is density into volume, A into dx into C into dt by d tau. That will be the expression. Are you able to see it? Are you able to see the black color? And this Qx plus dx can be written by using Taylor theorem expansion, that is Qx plus d by dx into Qx into dx. That is called as Taylor theorem expansion, and this Qx can be written by using Fourier law, because the mode of heat transfer is conduction. That is Fourier law, minus Ka dt by dx. Like this. So if you simplify, then you will get the conduction equation, heat conduction equation. dt by d tau means temperature is a function of time, or the system is in unsteady state. The system will be in unsteady state. When the system is in steady state, then we can say for system to be in steady state, then dt by d tau will be 0. Then dt by d tau will be 0. And if we generalize this expression, is the expression clear to everyone? Is this expression clear to everyone? Please give me thumbs up. Please give me yes through the comment section. This is how conduction equation can be written. And for three-dimensional Cartesian coordinate system, how to write? We can say Qx in x direction, heat conducted into the element, then Qy plus Qz. That is the heat conduction, plus our control volume is dx by dy by dz. Our control volume is dx by dy by dz. So we can say Q dot generation of heat into dx into dy into dz is equal to Q x plus dx plus Q y plus dy plus Q z plus dz. This is Q out. This is Q out from the system. This is heat entering into the system, and that is heat generated in the system. And then there will be plus change in internal energy, that is rho into dx into dy into dz into C into dt by d tau. That is Q stored in the system. If you simplify, Qx plus dx can be written by using Taylor theorem expansion. Qy plus dy can be written by using Taylor theorem expansion. Qz plus dz can be written by using Taylor theorem expansion. Qx plus dy dx can be written as Qx plus del by del x into Qx into dx. Similarly, Qy plus dy. Similarly, Qz plus dz. If we write all these parameters and simplify, then our governing differential equation for conduction in Cartesian coordinate system will look like this. Del by del x k into del t by del x plus del by del y k into del t by del y plus del by del z plus Q dot is equal to rho into C. C is the specific heat into del t by del tau. That is our governing differential equation for conduction. And if K is constant, if we take the thermal conductivity as average value, if K is constant, it is neither be a function of x, y, z and time. If it is not a function of, or neither be a function of x, y, z and temperature, is not a function of x, y, z and temperature, then our expression will be modified like this. Del square, this is the governing differential equation for conduction in Cartesian coordinate system. We can take this k outside, we can take this k outside, we can take this k outside, and if we divide by k, the whole equation, if it is divided by k, which one, Vinith? The previous expression you are talking about? Are you talking about this expression? Are you talking about this expression, Vinith? This is our system. We are writing the energy balance equation to our system. There is the heat entering into the system, that is Qx. At any x, the heat transfer rate is qx, and x plus dx, we are taking a small element dx, and the area of the element is a. So at small dx, the rate of heat transfer will be qx plus dx. The heat flow is taking place in positive x direction. So q in plus q generated in the system is equal to q out plus q stored in the system. This is the expression. This is heat entering into the system. This is heat leaving from the system. This is stored in the system, that is rate of change of internal energy, and this is generation in the system, the amount of heat generated in the system. Clear? That is how. And qx plus dx can be expanded by using Taylor theorem expansion. This is called as Taylor theorem expansion. This is called as Taylor theorem expansion. क्लियर? कौन सा ए? ये जो एलिमेंट है, द एलिमेंट इज लाइक दिस, द एलिमेंट इज लाइक दिस. यू कैन सी dx. A is this. A is this area which is perpendicular to x direction, and the thickness of the element is dx. So the volume will be A into dx. A into dx is the volume, isn't it? Volume. Clear? और यहां पे जो वॉल्यूम है, द वॉल्यूम ऑफ दिस एलिमेंट dv is equal to dx into dy into dz. This is the volume. Here we are talking about a 3-dimensional element. ये 3-dimensional element है, तो वॉल्यूम मैंने लिखा dx into dy into dz. यहां पे भी वॉल्यूम dx into dy into dz, और यहां q जनरेशन में भी जो वॉल्यूम आएगा वो dx into dy into dz है. And qx plus dx can be written by using Taylor theorem expansion. So the final expression is important. You need to understand this expression. When k is not constant, then this will be the expression. When k is constant, then this will be the expression. Or we can write this expression to be, like this: del square T plus q dot by k is equal to 1 upon alpha del T by del tau. Q dot is rate of uniform heat generation per unit volume. The unit of Q dot is watt per meter cube. So this will be the expression for conduction in Cartesian coordinate system, XYZ coordinate system. From here we can say temperature will be a function of x, y, z and time. Temperature will be a function of x, y, z and time. That is governing differential equation for conduction in Cartesian coordinate system. The same expression del square T plus q dot by k is equal to 1 upon alpha del T by del tau can be modified for different situations. This expression can be modified for different situations. The first condition, if there is no heat generation, q dot is equal to 0. If q dot is equal to 0, then the expression will be del square T is equal to 1 upon alpha del T by del tau. That is equation is called as Fourier equation or diffusion equation. When there is no internal energy change, it means unsteady state system. The system is in unsteady state. Temperature is not a function of time. Temperature will, or we can say Q stored will be 0. Temperature will not be a function of time. So if temperature is not a function of time, dt by dt will be 0. So it will be del square T plus q dot by k is equal to 0. This will be the mathematical expression. This equation is known as Poisson equation. When there is no change in internal energy, or q stored will be 0, or we can say dt by d tau will be 0. Here we can say q generation. There is a difference between generation of heat and storage of heat. So many people have doubt. They think generation and storage are same things. Heat generation and heat storage are not same, they are different. And when heat generation is 0 heat stored is 0. When both are 0, then we get Laplace equation, that is del square t, which can be expanded as del square t by del x square plus del square t by del y square plus del square t by del z square is equal to 0. This is called as Laplace equation. You are familiar with Laplace equation. You must be familiar with the Laplace equation. This equation is known as Laplace equation, right? Clear? Similarly, but what is alpha? Now, what is alpha? We have used a parameter alpha. Alpha is the property of the material that is called as thermal diffusivity, which is the ratio of K and rho into C. Alpha is a material property. It gives the relative ability of the material in conducting heat and storing heat. This is the conduction ability, and this is the heat storage capacity. The ratio of heat conduction ability and heat storage capacity is called as thermal diffusivity capacity. This is called as thermal diffusivity. The ratio of thermal conductivity and the heat storage capacity, rho multiplied by specific heat, is called as thermal diffusivity. What is the unit of thermal diffusivity? What should be the unit of thermal diffusivity? A high value of alpha implies more conduction ability and less storage capacity, whereas the low value of alpha implies the reverse. Low value of alpha implies more storage capacity and less conduction ability. What is the unit of thermal diffusivity? Can anybody let me know? What is the SI unit of thermal diffusivity? What will be the SI unit of thermal diffusivity? Tell me, everyone. Unit of thermal diffusivity. Meter square per second. It is like kinematic viscosity. It is like kinematic viscosity. The unit is meter square per second. Is the unit of thermal diffusivity. Because it is made up of properties, thermal conductivity, density, specific heat, all are properties involved in this expression. So, and that is why it is called as, it is a material property. That is the reason the thermal diffusivity is the property of the material, and for gases, the thermal diffusivity is more than liquid than solid. So that was the governing differential equation for conduction, general governing differential equation for conduction in Cartesian coordinate system, that is XYZ coordinate system. Now we will also talk about the governing differential equation for conduction in cylindrical coordinate system as well as spherical coordinate system, because we are going to analyze the conduction in plane wall, which will use the Cartesian coordinate system. We will analyze the conduction in case of cylindrical system, that will use the cylindrical coordinate system, and we will analyze the conduction in case of spherical systems, and that where there we will use the governing differential of conduction in cylindrical spherical coordinate system. So if we take an element, this is our element, let us say dr is the dimension, and this will be r into d phi. D phi is this angle in a horizontal plane, angle in a horizontal plane. So this is r into d phi, isn't it? And this is dz. So the volume is equal to dv is equal to dr multiplied by r d phi multiplied by dz. This is called as cylindrical coordinate system. So if we write the energy equation in cylindrical coordinate system, we will write qr plus q phi plus qz, this is q in, plus q dot into dv, that is q generation, is equal to q r plus dr plus q phi plus d phi plus q z plus dz. This is out, energy leaving from the system, plus density into volume, that is dv into c into dt by d tau, that is q stored. And these three terms can be written by using Taylor theorem expansion. If we write the value of QR plus DR, Q5 plus D5, QZ plus DZ using the Taylor theorem expansion, I am not going to waste your time in derivation of this expression. I will directly write for K is equal to constant. I am writing for K is equal to constant, that is the average thermal conductivity in the material. Then it will be the mathematical expression governing differential equation can be written as 1 upon R del by del R into del T by del R first term plus 1 upon R square then del square T by del square T by del phi square plus del square T by del Z square plus Q dot by K is equal to 1 upon alpha del T by del tau. This is the mathematical expression when K is taken as constant. Yes, Vinith, this is the mathematical expression which gives us the information T is a function of R, phi, Z and time. Sorry, tau. Time I'll be using tau. Tau will be used for time, T for time. And this first expression can also be written. This expression can also be written. This is another way of this writing the cylindrical coordinate system. We can write the expression in cylindrical coordinate system like this. Right? Similarly, the spherical coordinate system. dr is the radial distance. dr, then this will be r d theta. This will be r into d theta, and this will be r sin theta into d phi. So the volume will be equal to, the volume dV is equal to dr into r d theta into r sin theta into d phi. This will be the volume of our element. This is our element in cylindrical coordinate system. Phi is in a horizontal plane and theta is in a vertical plane. Theta is in a vertical plane. Phi is in a horizontal plane and theta will be in vertical plane. So if we write QR plus Q phi plus Q theta plus Q dot into dV is equal to QR plus dr plus Q theta plus d theta plus Q phi plus d phi plus rho into dV into C into del T by del tau. And if we write this using the Taylor theorem expansion, then let me write the expression directly. Governing differential equation when K is constant, the expression will be 1 upon R square del by del R into R square del T by del R first term plus 1 upon R square into sin theta, then del by del theta, then sin theta into del T by del theta plus 1 upon R square sin square theta into del square T by del phi square plus Q dot by K is equal to 1 upon alpha del T by del tau. That will be the governing differential equation of conduction in case of spherical coordinate system. In case of spherical coordinate system, the first term can be written as, this first term can be written like this also. One and the same thing. That is how the expression will look like in cylindrical coordinate system. Temperature will be a function of R, theta, phi and tau. So these are the governing differential equation for conduction in the 3 coordinate system. Cartesian, cylindrical and spherical coordinate system, right? You must memorize these expressions. So if I summarize, look, in Cartesian coordinate system, what I had written for k is equal to constant, I am writing for k is equal to constant. So if we summarize, the expression will be del square t by del x square plus del square t by del y square plus del square t by del z square plus q dot by k. This term and the last term will be same, 1 by alpha this. The second one is 1 upon r del by del r into del t by del r plus 1 upon r square del square t by del phi square plus del square t by del z square plus q dot by k is equal to 1 upon alpha del t by del tau. That is in cylindrical coordinate system. And the spherical coordinate system, 1 upon r square del by del r into r square into del t by del r plus 1 upon r square sine theta into del by del theta into sine theta del t by del theta plus 1 upon r square sine square theta into del square t by del phi square plus q dot by k is equal to 1 upon alpha del t by del tau. How many of you remember these three expressions? How many of you remember these three expressions? Give me thumbs up. Are you able to memorize these? Are you able to memorize? Even if you are not able to memorize the whole expression, at least first term for each and every expression you should at least memorize. At least memorize the first expression for each and every term. All right, ये important है because we are going to use these expressions in our analysis for conduction. ये वाला term, at least you should memorize this term because we will be talking about one dimensional conduction. So the second, third term will not be important. We will be talking about steady state conduction. The last term will be 0. And we will be talking about no heat generation. Then q dot by k term will be 0. So at least you should know these terms. Now let us start talking about the one-dimensional steady state heat conduction. One-dimensional means the temperature is a function of x only, or temperature is a function of r only. When do we have one-dimensional conduction? When there is no temperature gradient in other two directions. The conduction is one-dimensional when there is no temperature gradient in other two directions. When the other two direction or other two dimensions are very large. When other two dimensions are very large, then even if there is a temperature difference, the gradient of temperature will be negligible. So when the gradient is 0, it means there is no conduction. For conduction to take place, the gradient has to be non-zero. So one-dimensional conduction means the temperature or dt by dx is non-zero, dt by dy will be 0, dt by dz will be 0. Similarly, in case of cylindrical or spherical coordinate system, dt by d phi or dt by dz or dt by d theta will be 0. Steady state conduction means temperature is not a function of time, or Q stored will be 0, or rate of change of internal energy will be 0. Temperature is independent of time. dt by dt will be 0. These are the two assumptions we will carry throughout our discussion, one-dimensional steady state heat conduction. And what we are going to discuss is, the first one is the temperature profile. how the temperature varies with X, how the temperature will vary with R in case of cylindrical coordinate system, how the temperature varies with R in a spherical coordinate system. Then we will talk about the rate of heat transfer expression, and finally we will talk about the circuit diagram, how we can relate this with circuit diagram or electrical analogy. Shall we start? Look. First of all, I will be talking about the plane wall system. When the system is in the form of plane wall, it is Cartesian coordinate system and area will be constant. For a plane wall, the area which is normal to the direction of heat flow will remain constant. A will be constant. And there is no heat generation in the system, Q generation, and the thermal conductivity will be constant. That is the average thermal conductivity. We are talking about the average value of thermal conductivity. These are two more assumptions along with one-dimensional steady state conduction. So if we apply the Fourier law for a plane wall, then we can say Q is equal to minus Ka into dt by dx. Conduction is taking place in the x direction. Can you just let me know Q will be constant or variable? Hi Rashad, welcome. How are you? Do let me know Q will be constant or variable. Do you remember Q in plus Q generated is equal to Q out plus Q stored? With our assumptions, Q generation will be 0, Q stored will be 0. So it means Q in is equal to Q out. The rate of heat transfer is constant, isn't it? As long as the generation of heat will be 0, and the storage of heat will be 0. Heat stored will be 0. How? Because we have taken this assumption steady state. For a steady state, the storage of heat will be 0. And generation of heat 0 is taken here. So according to Fourier law, we can call it as constant, isn't it? That is our Fourier law, because Q generation and Q stored both will be 0. They are not same. There is a possibility that there is a generation of heat only without any storage. There is a possibility that there is a heat storage in the system only without any generation of the heat. There is no connection between them. They are two separate parameters. Sometimes the question says generation of heat will be 0. Sometimes the question says the storage of heat will be 0, right? So as long as the generation and storage both are 0, then Q will be constant. And if we write the governing differential equation for conduction, so we can say d square T by dx square is equal to 0. D square T by dx square will be 0 because there is no generation, there is no storage, isn't it? This will be the governing differential equation in Cartesian coordinate system. If we integrate twice, then we will get temperature as a function of x. But we need C1 and C2, two constant of integration. So if we put the constant of integration, then our final expression for temperature profile will be like this. To find out the C1 and C2, this is our plane wall, let us say. This is our plane wall. What is the nature of temperature profile? Here the temperature is T1, here the temperature is T2. This is x is equal to 0. This is the direction of heat flow. At any x, the temperature is T. This is x is equal to L thickness. A will be constant. So if we put the boundary condition at x is equal to 0, temperature is T1. At x is equal to L, L is the thickness of the wall, temperature is T2. And if T1 is greater than T2, then the direction of heat flow will take place from left to right. This is Q, which will be constant. Q will be constant, isn't it? So if we put the boundary conditions and calculate C1 and C2 at any x, temperature will be equal to T. So our temperature profile will look like this. What is the nature of temperature profile? T1 minus T upon T1 minus T2 is equal to x by L. L is the wall thickness. L is the thickness of the ball, A is the area, T1 is the temperature at the inlet, T2 is the temperature at the outlet. The nature of the temperature profile will be linear as long as the system is having one-dimensional conduction, steady state conduction, no generation of the heat, constant thermal conductivity and constant area. And we can also find out the rate of heat transfer. We can also find out the rate of, so this is T1, this is T2. This is how the nature of the temperature profile will be linear. It will be linear. Temperature as a function of X is linear. The temperature profile will be linear. This will be the mathematical expression. There are 1, 2, 3, 4, 5 parameters are given in the expression. Any 4 can be given to you and the fourth one can be asked. It is very easy. But you need to remember this formula for conduction in plane wall without heat generation, one-dimensional and steady state. These are the assumptions. We can find out Q, the rate of heat transfer, which is constant, by using the Fourier law. So if we use the Fourier law or governing differential equation, we can say Q is equal to K into A into T1 minus T2 upon L. This is T1 minus T2. This will be T1 minus T2. We can call it as delta T, T1 minus T2 by L is equal to Ka into T1 minus T upon X also, that will remain constant. T1 minus T2 can be written as delta T. This is the expression for rate of heat transfer through the plane wall. Right? Do you remember it? X is the distance from inlet plane. This is X is equal to 0. This is X is equal to L. X is any distance where the temperature is T. X is the any distance from the inlet plane where the temperature is T. This is the mathematical expression for heat transfer rate. And if we relate with this circuit diagram, Q is given by, as we know, Q is equal to K into A into delta T by L. That can be related with delta T upon thermal resistance. So if we equate this, then RTH is given by L by Ka. What is the unit of thermal resistance? That is called as conduction thermal resistance. That is known as conductive thermal resistance, RTH. What is the unit of thermal resistance? This is delta T. This will be delta T. T1 minus T2. Here the temperature is T1. Here the temperature is T2. So Q will be equal to delta T upon RTH. And RTH will be equal to L by Ka. What is the unit? The unit is RTH is delta T by Q. So Kelvin per unit watt or degree Celsius per unit watt. Kelvin per unit watt or degree Celsius. It is either Kelvin or it can also be called as degree Celsius. Conduction thermal resistance. All right. Conductive thermal resistance. And there is another parameter defined that is called as KTH. 1 upon RTH. That is Ka by L. The unit is watt per Kelvin. That is known as thermal conductance. That is known as thermal conductance. And one more term can be defined, A into RTH, that is L by K. The unit will be meter square Kelvin per unit watt. That is called as unit thermal resistance. So unit will decide what exactly the parameter given. Either it is resistance given, unit thermal resistance given, or the thermal conductance given. So this is the circuit diagram. Why we are calling it as electrical analogy? Because current is like Q. Delta V electrical potential is like thermal potential. Delta T is called as thermal potential. We can call it as thermal potential. Thermal potential. That is T1 minus T2. Degree Celsius or Kelvin. The unit is degree Celsius or Kelvin. and the electrical resistance is like thermal resistance. So from Ohm's law, we can say Q is equal to, or we know from Ohm's law, we know I is equal to delta V by R. That is what we are using. So to apply these formula, whatever the formula I have discussed, I have talked about the three formula: the temperature profile, temperature variation in X direction, then the rate of heat transfer, then the thermal resistance. To apply these formula, these assumptions should be taken into consideration. Steady state conduction, temperature should not be a function of time, Q stored will be 0, or dt by dt is 0. Rate of change of energy storage or rate of change of internal energy will be 0. One-dimensional conduction, temperature is a function of X only. Uniform thermal conductivity, K will be constant. It is the average value of thermal conductivity taken into consideration. No heat generation, Q generation will be 0. And the area will also be constant. Another is constant area. Because we are talking about the plane wall, area is also constant. So the formula which we have developed is T1 minus T upon T1 minus T2 is equal to X by L. That is one formula, linear. The second formula is Q is equal to Ka T1 minus T2 upon L, or we can write it as Ka T1 minus T upon X. One and the same thing. The third formula is that can be equated with delta T upon thermal resistance, delta T upon RTH. So the third formula will become the conduction thermal resistance is L by Ka, or thermal conductance is equal to Ka by L, or unit thermal resistance is equal to L by K. So we can write Q dash, the heat flux, which is equal to Q by A, that is equal to delta T, that can be written as delta T upon A into RTH. That is the heat flux. The unit will be equal to watt per meter square. These are the various formula for one-dimensional steady state conduction in case of a plane wall. I hope this is clear to everyone. All fine? Similarly, now very important. Now when the thermal conductivity is variable, the next is when it is having a variable thermal conductivity. Because thermal conductivity varies with temperature, we all know. Thermal conductivity varies with temperature. The previous formula were valid when the thermal conductivity used to be taken as constant. Now, my question to everyone is, when the thermal conductivity is variable, what will happen to the rate of heat transfer? When the thermal conductivity is variable, the rate of heat transfer, will it be constant or variable? C for constant, V for variable. Please do let me know, everyone. When the thermal conductivity is variable, what will happen to the rate of heat transfer? Will it be constant or variable? Please do respond. When the thermal conductivity is variable, heat transfer rate, will it be constant or variable? Will it be constant or variable? Variable thermal conductivity will make the heat transfer rate variable or constant. Everyone, please respond. Bataiye. It is the last lap, last moment of your preparation. Whatever you have studied throughout the year, we are going to revise everything in a single day for the heat transfer, so that you will be able to perform better and better in your exam. Q will remain constant as long as Q generation and Q stored will be 0. Only these two parameters are having the power to vary the rate of heat transfer. As long as there is no generation, as long as there is no storage of heat, there is no variation in the rate of heat transfer. नीतीश, बाकी सबने सही जवाब दिया. अजमीरा, variable thermal conductivity will not make the rate of heat transfer variable. The rate of heat transfer will remain constant as long as. आप यहां से देखिए ना, our energy conservation equation is Q in plus Q generation is equal to Q out plus Q stored. यहां से देखिए, ये 0 होगा और ये 0 होगा, तो Q in is equal to Q out. Q will be constant. Variable thermal conductivity will not make the rate of heat transfer variable. So from here we can say area is constant. So can we say dt by dx is inversely proportional to K? Can we say dt by dx will be? Can we say dt by dx is inversely proportional to K and negative? The temperature gradient will be negative. dt by dx is inversely proportional to K. Q is constant, A is constant. Both are constant. So the temperature gradient will be negative and inversely proportional to K. What does that mean? As K increases, dt by dx decreases. Or if K decreases, dt by dx increases. Temperature gradient will be inversely related to this, and the sign will be negative. Right? Is this clear? Now, there are two ways in which thermal conductivity can become variable. Thermal conductivity can increase with temperature. Where it happens? In case of a gas, in case of insulator, in case of non-metal. The expression can be like this. If this is the expression, it means temperature increases implies K increases, or if temperature decreases implies K decreases. That is the meaning. First expression. If temperature increases, thermal conductivity increases. If temperature decreases, thermal conductivity decreases. Now look, T1 is this temperature and T2 is this temperature. And the direction of heat flow is from left to right. This is X is equal to 0. This is X is equal to L. This is the direction of heat transfer. T is the temperature at X. Now look, if X increases, can you just let me know? Everyone, I want everyone to respond. If X increases, what is happening to the temperature? In the direction of heat flow, temperature always decreases. In the direction of the heat flow, temperature always decreases. So, as X increases, what is happening to the temperature? What is going to happen to the temperature? Because the heat flow is taking place in X direction, in the direction of decreasing temperature, so temperature will decrease. And if temperature is decreased, what is happening to K? According to this expression, thermal conductivity will also decrease. And if thermal conductivity decreases, what happens to dt by dx? Because thermal conductivity is inversely proportional to dt by dx. Do you agree dt by dx will increase? Dt by dx will increase and the nature will be negative. You need to draw a curve joining T1 and T2 in such a manner. You need to draw a curve joining T1 and T2 in such a manner that dt by dx, the slope will increase in magnitude and negative in sign. So do you understand? This will be the curve. Temperature profile. This is the temperature as a function of X we are drawing for K is equal to K naught 1 plus beta T. Do you understand this? And if this is the case, this happens in case of liquid, conductor, or metals. As if we increase the temperature, thermal conductivity decreases in case of gas, or if temperature decrease, thermal conductivity will increase. That is happening in case of liquid, conductor, or metals. I have already told you about the mechanism here. In case of liquid, molecular diffusion is the governing factor. In case of conductor and metal, the free electron flow is that governing factor. So now if you see here, what is happening is in X direction, as X increases, the temperature is decreasing, right? In the heat flow direction, the temperature decreases. And if temperature decreases, what is happening to thermal conductivity? it will increase, and if thermal conductivity will increase, dt by dx will decrease and the nature will be negative. So you need to join T1 and T2 in such a manner, you are supposed to join T1 and T2 in such a manner that the slope will be decreasing from 1 to 2 and should be negative in sign. So the joining will be like this. This will be for K is equal to K naught 1 plus beta 2. It will not be linear. The temperature profile will not be linear. The temperature profile will be linear only when K is equal to constant. If K is constant, then only the temperature profile will be linear. Do you understand? For average thermal conductivity, the temperature profile will be linear. Otherwise, it will be a different curve. The temperature variation will no longer be linear. Is this all clear to everyone? That is how the variable thermal conductivity can be analyzed. Because, is this clear? And you can easily find out. You can easily find out using the Fourier law, like Q is equal to. You can easily find out the expression for the temperature profile. How? Using Fourier law. Q is equal to minus K, which is a function of temperature, into A into dt by dx, which is constant. Whenever Q is constant, we always go for Fourier law. There are two ways to analyze the system, either going with the Fourier law or governing differential equation. When Q is constant, we generally go with the Fourier law. But when Q becomes variable, when there is the energy storage in the system. ऋषिकेश आप आए नहीं थे क्या? स्टार्टिंग में नहीं थे क्या कि टेम्परेचर और के डायरेक्टली भी हो सकता है, इनवर्सली प्रोपोर्शनल भी हो सकता है. जैसे गैसेस के केस में टेम्परेचर और थर्मल कंडक्टिविटी डायरेक्टली रिलेटेड होते हैं, लिक्विड के केस में टेम्परेचर और थर्मल कंडक्टिविटी इनवर्सली रिलेटेड होते हैं. सिमिलरली कंडक्टर के केस में इनवर्सली रिलेटेड होते हैं मेटल के केस में, और इंसुलेटर या नॉन मेटल के केस में डायरेक्टली रिलेटेड होते हैं. तो डिपेंडिंग ऑन द मटेरियल वी कैन हैव दिस टाइप ऑफ एक्सप्रेशन. तो जब भी Q की वैल्यू कांस्टेंट होगी, वी गो फॉर फोरियर लॉ. और अगर इसको दो बार इंटीग्रेट करें, इसको क्या लिख सकते हैं? देखिए, इसको लिख सकते हैं Q इंटू डी एक्स इज इक्वल टू माइनस के, विच इज ए फंक्शन ऑफ टेम्परेचर, इंटू ए इंटू डी टी. अगर इसको दो बार इंटीग्रेट करें, इसको इंटीग्रेट करें 0 टू x इंटीग्रेट करेंगे तो ये होगा T1 से T. तो ये बनेगा Q इंटू एक्स इज इक्वल टू K विच इज अ फंक्शन ऑफ टेम्परेचर इंटू A इंटू dt का इंटीग्रेशन T2 से T1 कर देता हूं क्योंकि नेगेटिव था साथ में. सिमिलरली अगर Q dx को इंटीग्रेट करें फ्रॉम 0 टू L माइनस K विच इज अ फंक्शन ऑफ टेम्परेचर इंटू A इंटू dt, limit will be T1 से T2. If you do, then Q into L is equal to integration T2 to T1. K is a function of temperature into A into dt. Sorry. Yes. If you divide these two, area getting cancel out, Q and Q getting cancel out, we can develop a relation between temperature and X. We can develop a relation between temperature as a function of X. Or if we integrate this only, second expression, we can find out the rate of heat transfer from this. Q can also be determined. This will give you the value of Q. Is this clear? So that is how, by using the Fourier law, we can develop the temperature profile. We can develop the expression for the rate of heat transfer. Clear? Are you getting it or not? Please do let me know. And when K is a linear function of temperature, I am not going to solve it. Without knowing the variation of K with temperature, we cannot solve it. But yes, this is the procedure. I am also sharing you the method to get the temperature profile, method to get the expression for the rate of heat transfer. The previous formula, standard formula, will not be applicable because K is not constant here. And because K is equal to K naught 1 plus minus beta T. If it is linear function of X, linear function of temperature, then we can say the average value of thermal conductivity is equal to K naught 1 plus minus beta into T average, where T average is the mean of T1 and T2. If it is linear, then the average temperature will be T1 plus T2 by 2. We can find out the average value of thermal conductivity like this. And Q is equal to K average into A into delta T by L. We can use this expression. That is how the expression can be used for linear velocity, for linear variation of thermal conductivity with temperature. If it is any other expression, we can accordingly find out the expression. Right? So this Q will be equated with this original expression. We can find out the expression for average thermal conductivity. We can develop the expression for average value of thermal conductivity. There is a question on the screen. If anybody is having any doubt, you can just let me know. Otherwise, I want your answer to this question. Please read the question and try to get me the answer to this. दो घंटे हो गए हमें, 2 hours. बताइए, what is the answer? I want everyone to respond. A, B, C, D. There are 4 options on the screen. One-dimensional steady-state heat conduction without heat generation in case of a plane wall. Yes, nobody is responding. बताइए, everyone please do respond. This at x is equal to 0, temperature is T1. At x is equal to L, temperature is T2, and T2 is greater than T1. पहले तो मुझे ये बताइए, Q will be constant or variable? Q will be constant or variable? Do you agree? Because it is steady state conduction, it means Q stored will be 0. It is without heat generation, it means Q generation will be 0. As long as heat generation and heat stored will be 0, then do you agree Q will be constant? Do you agree Q will be constant? Q will be constant, and if Q is constant, then dt by dx is inversely proportional to K. Do you agree or not? Isn't it? When Q is constant, dt by dx will be inversely proportional to K. Right? Now, because the expression is given by this, the variation of thermal conductivity, what does that mean? What this expression means? Do you agree this expression means as the temperature increases, K will also increase? Because B and K naught are positive constant, or if we decrease the temperature, thermal conductivity will decrease. Do you understand? K is equal to K naught plus BT. By increasing the temperature, K will increase. By decreasing the temperature, K will decrease. Now, in the direction, in X direction, can you just let me know what is happening to the temperature? In X direction, what is happening to the temperature? As X increases, what is happening to the temperature? T1 is less, T2 is more. So the temperature, what is happening to the temperature? Do you agree it is increasing? It is increasing. If we are going from 1 to 2, the temperature is increasing. And if the temperature is increasing, what is happening to the thermal conductivity? The thermal conductivity will also increase, isn't it? And if the thermal conductivity is increasing, what happened to dt by dx? What will happen to dt by dx? What is going to happen to dt by dx? Isn't it decreasing? Isn't it option D? Isn't it option D? Why you guys are saying increasing then? Why you guys are saying that is how the questions is going to be asked? Yes, that is the problem. The direction is the problem actually. That is how GATE is going to ask you the question. That is how GATE is going to ask you the question. Because the direction of heat flow will be negative x. If we talk about the direction of heat flow, the heat will flow in the negative x direction. But the question says as x increases, opposite to the direction of heat flow. As x increases, the temperature will increase and the thermal conductivity will also increase. That will imply there is a decrease in the... So if we draw the temperature profile, actually it will be like this. Can you let me know what is the sign of dt by dx, positive or negative? What will be the sign of dt by dx? Will it be positive or negative? Sign of dt by dx. Will it be positive or negative? The sign of dt by dx, will it be positive or negative? Quickly. Will it be positive or negative? It will be positive. Isn't it positive? If we draw a tangent, when x, if from here only we can say, as x increases, if the temperature is increases, it means dt by dx is positive. It is positive. Yes, it is positive. By increasing x, if the temperature increases, dt by dx will be positive. In x direction, dt by dx is positive. But in the direction of heat flow, dt by dx is negative. In the direction of heat flow, dt by dx will be negative. One more question and then we will proceed to heat generation case. Yes, I want you guys to let me know the answer to this, the next one. Then we will proceed to the generation of the heat in the plane wall. We have already talked about without heat generation with constant thermal conductivity. Then the second case, we have talked about the variable nature of the thermal conductivity. And the last and the final case will be when there is a heat generation in the system. Nitish, ye hai na? Q is equal to, I am using the Fourier law. I am using the Fourier law. Q is equal to minus k into a into dt by dx is equal to constant. From here I am developing the relation between dt by dx and k. dt by dx and k. Inversely proportional. Inversely proportional. dt by dx, if q is constant, if area is constant, then k into dt by dx will be constant. So dt by dx is inversely proportional to k, isn't it? What is the answer to this one? What is the answer to this question? This was asked in 2019. B for Bombay. Linear? Is it linear? Look, one dimensional, again steady state. Heat conduction takes place through a solid whose cross-sectional area varies linearly in the direction of heat flow. It means A is a linear function of x. A is a linear function of x, or we can say A is directly proportional to x. Area is variable now. Here area will be variable. Assume there is no heat generation. No heat generation means Q generation is equal to 0. As long as heat stored 0, heat generation 0, Q will be constant. Now thermal conductivity will be constant here. The thermal conductivity of material is constant. So from this expression, look, from this expression, can we say dt by dx is inversely proportional to area? Can we say dt by dx will be inversely proportional to area? Do you agree or not? dt by dx is inversely proportional to area and A is directly proportional to x. So we can say dt by dx is inversely proportional to x. If the question was about If the question would have been about the temperature gradient, then this would have been the relation. The question is about the temperature distribution in the solid. So if we integrate these, then dt by dx, if we integrate with respect to x, if we integrate with respect to x, do you agree dt is dx by x, dt is proportional to dx by x? What is the integration of dx by x? Isn't it ln x? Isn't it ln x? Isn't it logarithmic? Isn't it logarithmic? Isn't it logarithmic? Yes, it will be logarithmic. It will not be linear. The temperature will be a logarithmic function of x. Now, let us move to the next important part. The plane wall with uniform heat generation. The heat generation is uniform. What does that mean? Q dot is equal to constant. The rate of heat generation per unit volume, the unit is watt per meter cube, is constant. Plane wall with uniform heat generation. So in that case, Q will be constant or variable. When there is a heat generation, what about Q? Rate of heat transfer, will it be constant or variable? Everyone, please do let me know. And do share this session with all your friends. जो भी आपके friends हैं, juniors हैं, seniors हैं, who are preparing for GATE 2023, who are going to appear in GATE 2023 examination, ask them to be part of this session. It is going to help them in understanding the concept of heat transfer. When there is a uniform heat generation, Q will be variable. The rate of heat transfer will be variable. So in that case, we go for the governing differential equation. For one-dimensional steady state, the basic assumptions are one-dimensional steady state and constant thermal conductivity, constant area. So this will give rise to d square T by dx square is equal to, plus Q by K plus Q dot by K is equal to 0. This will be the governing differential equation. If we integrate it twice, if we integrate this expression twice, then we will get C1 and C2. And if we assume the temperature, the value of C1 and C2 at x is equal to 0, if I talk about this is the plane wall with heat generation, this is x is equal to 0, this is x is equal to L. If here temperature is Ts, here also temperature is Ts. At x is equal to 0, temperature is Ts. At x is equal to L also, if I assume temperature is Ts, same. Then if we integrate this twice, we can find out the value of C1 and C2. This is the special case, the temperature is same. At x is equal to 0 also temperature is Ts. At x is equal to L also temperature is Ts. The area is constant like this. This is the plane wall. So if we do the calculation, then T will be equal to, T is the temperature at any x. T is given by Ts plus Q dot x by 2K into L minus x. What is the nature of temperature profile here? What will be the nature of temperature profile? For variable, for heat generation in the plane wall, the temperature profile will be given by this expression. It is a function of, temperature is a function of x square. It is parabola. The temperature profile will be parabolic. Yes, it will be parabola because it is a function of x square. X multiplied by x. It is a function of x square. So the temperature profile will be parabola, and at x is equal to L by 2. At x is equal to L by 2, dt by dx will be 0. So temperature will be maximum. So at x is equal to L by 2, dt by dx will be equal to 0, q will be equal to 0, and T is maximum. This is how the parabola will be drawn. Look how to draw the parabola. This is the plane wall. This is the plane wall with the heat generation. This is the plane wall. This is x is equal to 0. This is x is equal to L. And this is x direction. So if TS and TS inner surface temperature and outer surface temperature are same, then the parabola will be like this. This point will have maximum temperature. This is how the parabola will look like. This is the center line, L by 2. At x is equal to L by 2, temperature will be maximum. This is how the parabola will be drawn. The heat will flow. The heat flow will take place in this direction. From the center, the heat will flow like this, Q1 and Q2. And here at Q at L by 2, Q is equal to 0 because dt by dx is 0. So if we write the maximum temperature expression, T maximum will be equal to Ts plus Q dot L square by 8K. That is the maximum temperature. And Q is equal to minus Ka into dt by dx. It is a function of dt by dx. And dt by dx is the linear function of x. So Q is a function of x that is linear. For parabolic temperature profile, dt by dx will be linear function, isn't it? For parabolic temperature profile, dt by dx will be linear. So Q will be a linear function of x. At x is equal to L by 2, Q will be 0 and it will be linearly varying with x. I hope this is clear. You need to memorize this formula. This is the maximum temperature at the center line or midpoint. The temperature will be maximum at the midpoint or mid plane. So these are the two expressions you need to remember. One is this temperature profile, but this is valid only when surface temperatures are same. Inner surface temperature and outer surface temperatures are same. This is valid only when inner and outer surface temperatures are same. And similarly, this expression is valid only when inner and outer surfaces are same. This is the maximum temperature or center line temperature. Temperature at the center. So this can be assumed as, the plane wall can be assumed as this is x is equal to 0. Let us say this is x is equal to L. TS1 is equal to TS. This is TS and this is also TS. Both are same. So the parabola will be like this. Q will be 0 at the center. Q will increase linearly like this. Linear function. This is maximum temperature. At the center, the temperature will be maximum. This is how it will look like. Or we can write it as this is L by 2. This is also L by 2. Isn't it? This is L by 2. So T maximum can be written as T maximum can also be written as Ts plus Q dot by 8K into twice of L by 2 square. Because at x is equal to L by 2, temperature is maximum. So this can also be written like this. But if T1 and TS1 and TS2 are not same, that is for TS1 is equal to TS2 is equal to TS. This expression is valid when TS1 and TS2 are same. Inner surface temperature and outer surface temperature are same. But if inner and outer surface temperature are not same, if TS1 is greater than TS2, TS1 is greater than TS2 like this. So the temperature profile will be like this. This is the point where the temperature is maximum. Let me call it as L1. Let me call it as L2. L2, and this is L1 plus L2 with heat generation. This is how the temperature profile will look like. This is T, So this is TS1. Yes, it's fine. This is the temperature TS1. This is the temperature TS2. Or there is a possibility that TS1 is less than TS2. TS1 is less, TS2 is more. Then the temperature profile will look like this. Then the temperature profile will be like this. This is TS1. This is TS2. TS1 and TS2. This is the point of maximum temperature. This is L1. This is L2. So the maximum temperature expression can be written. The maximum temperature can be written. If we write TS1, then Q dot by 8K into twice of L1 square. Or it can be written as TS2 plus Q dot by 8K into twice of L2 square. अगर TS1 TS2 के बराबर नहीं है तो, if TS1 is not equal to TS2, अगर TS1 TS2 के बराबर है, then the expression will be previous one. If TS1 is equal to TS2, then the expression will be previous one. But if TS1 is not equal to TS2, then this is how we can write the maximum temperature. If we are using TS1, then L1 will be taken into consideration. If we are using TS2, maximum temperature is not at the center. T maximum will not be at the center now. Right? So this completes our discussion for plane wall. This is all about the plane wall. Now we will be talking about the cylindrical system, then spherical system, and then we will be talking about the combined modes of heat transfer and composite system. Can you just let me know the answer to this one? Can you let me know the answer to this question? Please do let me know the answer. Solve this question and give me the answer for. Consider one-dimensional steady-state heat conduction along x-axis. X is lying between 0 to L through a plane wall with boundary surfaces x is equal to 0 and x is equal to L. Maintained at temperature of 0 and 100. Maintained at temperature of 0 degree and 100 degrees Celsius. Heat is generated uniformly throughout the wall. Choose the correct statement. There is a heat generation. It is a case of uniform heat generation and the surface temperature TS1 is not equal to TS2. Inner surface temperature and outer surface temperatures are not equal. Can you solve it? The direction of heat transfer from the surface at 100 to the surface at 0 degrees Celsius. Look, inner surface is at 0 degrees Celsius. Outer surface is at 100 degrees Celsius. This is how the temperature profile will be. Parabola. This is how the temperature profile. The direction of heat transfer will not be from 100 to 0. No. In one part, the direction of heat transfer will be towards right, and in another part, that heat will always transfer in the direction of decreasing temperature. Here, temperature is maximum. This is how it will be. The maximum temperature inside the wall must be greater than 0 and 100. Yes. T maximum is greater than 100. The temperature distribution is linear. No, it is parabolic. The temperature distribution is symmetrical about mid-plane. No, it would have been symmetrical about mid-plane if TS1 would have been equal to TS2. If TS1 and TS2 would have been same, then it would have been symmetrical about mid-plane. So the correct answer is option B. B is the right answer. Similarly, let us talk about cylindrical system. Conduction in case of hollow cylinder, the conduction is one-dimensional. Temperature is a function of R only. Steady state, temperature is not a function of time. Thermal conductivity is constant. K is constant. We are not talking about variable thermal conductivity. And Q generation will be 0. These are all the assumptions, but here area will not be constant. Area will be, A will be the area normal to the direction of heat flow, that is 2 pi RL. L is the length of the cylinder which is into the plane of the board. It is not constant. Area will not be constant here. It will be a function of R. Inner radius is R1, outer radius is R2. So at R is equal to R1, the temperature is T1. At R is equal to R2, the temperature is T2. And if T1 is greater than T2, then the direction of heat flow will be from inner to outer surface. Q will be constant because heat generation will be 0, steady state system. So Q, heat transfer rate, will remain constant. And at any R, temperature is T. What is the nature of temperature profile? If we use the governing differential equation, what is the governing differential equation we are supposed to use? 1 by R, d by dr. What is the nature of temperature profile? Anybody is having any idea? D by dr into R into dt by dr is equal to 0. That is the governing differential equation. If we integrate twice and put these conditions to find out the value of C1 and C2, we will get the temperature profile. What is the nature of temperature profile? So if I write the temperature profile, it will be logarithmic. T1 minus T upon T1 minus T2 is equal to ln of R by R1 upon ln of R2 by R1. That is how the temperature profile will look like. That is the logarithmic. The temperature profile will be logarithmic. If I draw the temperature profile, it will be like this. This is T2, this is T1. The direction of heat flow will be, Q is constant. The nature of temperature profile will be logarithmic. We can find out the temperature at any R. Or we could have written R1 by R upon R1 by R2. Because R2 is greater than R greater than R1. That is how I have written. This is how the temperature profile will look like. The rate of heat transfer Q, using the Fourier law. We can use the Fourier law. So if we use the Fourier law, rate of heat transfer Q is given by 2 pi KL delta T upon ln of R2 by R1. That will be the temperature profile, that is constant. That is the rate of heat transfer. That is the expression for rate of heat transfer. That is how the heat transfer rate, and that can be equated with, we can equate this with delta T upon thermal resistance. So the thermal resistance can be, what is the thermal resistance for conduction? In case of hollow cylinder, it will be ln of R2 by R1 upon 2 pi KL, and the unit is Kelvin per unit watt. All right, this is how we can find out the heat transfer rate. These are the formula you not need to remember. One parameter we define here for, in case of hollow cylinder, we define the logarithmic mean area. Logarithmic mean area of a hollow cylinder. Logarithmic mean area. If we replace it with a plane wall, equivalent plane wall, it is defined to develop the equivalent plane wall. Logarithmic mean area is defined. So the thickness, this is LR, radial thickness, LR. LR is equal to R2 by R2 minus R1. Radial thickness LR is equal to R2 minus R1. That is called as radial thickness. This is the radial thickness. And this, the area will be logarithmic mean area, and the temperature difference is delta T. Like this. So the logarithmic mean area of a hollow cylinder is given by A2 minus A1 upon natural log of A2 by A1. That is called as logarithmic mean area. And logarithmic mean radius can also be written as R2 minus R1, because 2 pi L getting cancelled out. ln of R2 by R1. That is called as logarithmic mean radius. Logarithmic mean radius. So these are the various formula for hollow cylinder. These are the assumptions. You need to carry these assumptions: steady state, one-dimensional uniform heat generation, uniform thermal conductivity, no heat generation. These are the various. For this we can write, shall I write again? I don't think there is a need. T1 minus T upon T1 minus T2 is equal to ln of, we can write R1 by R upon ln of R1 by R2 as well. That is the temperature profile. Q is equal to 2 pi k L delta T upon ln of R2 by R1. That can be equated with delta T upon thermal resistance, and the thermal resistance will be equal to ln of R2 by R1 upon 2 pi k L, and logarithmic mean area is equal to A2 minus A1 upon natural log of A2 by A1. It is natural log. These are the formula used when these conditions or these assumptions are valid. See, in similar manner, we can talk about the hollow sphere. In case of hollow sphere, again area will be given by 4 pi r square. That is not constant. Area will be 4 pi r square. Inner radius is R1. Outer radius is R2. Q will remain constant. At R1, temperature is T1. At R2, temperature is T2. At any R, temperature is T. These are the conditions we are supposed to use, and T1 is greater than T2. What is the nature of temperature profile? Tell me, what should be the nature of temperature profile? If we put these conditions, the governing differential equation will be 1 by R square d by dr into R square into dt by dr will be equal to 0. This is the governing differential equation. If we integrate this, then we get the temperature profile. What is the nature of temperature profile? The temperature profile will be hyperbolic. The nature of temperature profile will be hyperbolic. It will look like logarithmic only. This is T1, this is T2. But the nature is hyperbolic. T1 minus T upon T1 minus T2 can be written as 1 upon R1 minus 1 upon R is the numerator. 1 upon R1 minus 1 by R2 is the denominator. That will be the temperature profile. That is how the temperature profile will look like. Hyperbolic. And we can also find out the rate of heat transfer using Fourier law. The heat transfer rate using Fourier law. Q is equal to 4 pi k R1 R2 into delta T upon R2 minus R1. That is the mathematical expression, that is constant. And that can be equated with delta T upon thermal resistance. So if we equate with thermal resistance, then thermal resistance for conduction in hollow sphere will be equal to R2 minus R1 upon 4 pi k into R1 into R2. Kelvin per unit watt. These are the various formula. And along with that, we talk about the geometric mean area to find out the equivalent plane wall. The area of the equivalent plane wall will be the geometric plane area. Equivalent plane wall. The temperature difference is delta T. So we can say Q is equal to K into geometric mean area into delta T by LR. LR is the radial thickness. This is LR, which is same as the thickness of the hollow sphere. That remains constant. And what is delta T? Delta T is T1 minus T2. Delta T is T1 minus T2. So what is the geometric mean area? That is under root of A1 and A2. That is the geometric. And geometric mean radius can also be written as under root of R1, R2. These are the formula for hollow sphere. So these are the various cases: plane wall, hollow cylinder, hollow sphere. with the simplest assumptions taken into consideration. These are the assumptions which are supposed to be taken into consideration. Steady state, one dimensional uniform heat generation, uniform thermal conductivity, no heat generation in the plane wall. Clear? Anybody is having any doubt? You can just let me know. So that completes our conduction in plane wall, conduction in hollow cylinder and hollow sphere. Ashutosh, for cylindrical system, if we analyze, if we equate, look how we are getting this. You need to understand. If we talk about, if we talk about hollow cylinder, this cylinder, so what we can write is Q is equal to, Q is equal to K into mean area into delta T upon LR, that is R2 minus R1. That is how Q can be written. That is equal to 2 pi KL delta T upon ln of R2 by R1. Isn't it? That is the expression. Now, if we multiply and divide, if we multiplied by and divide R2 minus R1 here, if we multiply and divide by R2 minus R1 here, so R2 minus R1 will make LR, and this, and again what we can do is, if we multiply here 2 pi L and divide by 2 pi L in this ln term, it will not make any changes because numerator is multiplied with R2 minus R1, denominator is also multiplied with R2 minus R1. Similarly, ln R2 by R1 can be written as ln R2 2 pi L upon R1 2 pi L, because we know A1 is equal to 2 pi R1 L and A2 is equal to 2 pi R2 L. We are actually finding out the mean area, because the area is variable. That is why we define the mean area. Ashutosh, that is for you. So what we can write is 2 pi L into R2 minus R1 is A2 minus A1 multiplied by L delta T, K delta T upon R2 minus R1 can be written as LR. This is LR into ln of A2 by A1. Now, if we compare these two, then the mean area will be equal to A2 minus A1 upon ln of A2 by A1. And that is the reason we call it as logarithmic mean area, because it is the logarithmic function we are getting. This will be the area. This will be the area. K mean area into delta T upon L. So that, because we are getting a logarithmic function, that is why it is called as logarithmic mean area. In similar manner, we can talk about a spherical system also. For a sphere also, this can be written as, for a sphere also we can write Q, K into mean area into delta T upon LR, that is equal to 4 pi K R1 R2 into delta T upon R2 minus R1. R2 minus R1 is LR. So what we can do here is, we can take square and under root. Look, because 4 pi R1 square is, what we can write here is K into delta T, then under root of 4 square pi square R1 square into R2 square. Can we write this way? Upon LR. So under root of 4 pi R1 square is A1, 4 pi R2 square is A2. So it will be K into delta T into under root of A1 into A2. Because A1, A2 is the geometrical mean. Under root of A1, A2 is geometric mean. That is why it is called as geometrical mean area. Equate these two, you will get mean area will be equal to under root A1, A2. Is this clear, Ashutosh? So for cylindrical system, mean area will be logarithmic function, and for spherical system, mean area will be a geometric function. That is why it is called a geometrical mean area. Now uniform heat generation. The next part is uniform heat generation in case of solid cylinder and in case of solid sphere. First of all, let us talk about a solid cylinder. So solid cylinder, the governing differential equation will be governing differential equation. Whenever there is a heat generation, Q generation is not 0. So we can say Q will be variable, isn't it? The rate of heat transfer will be variable, and because the rate of heat transfer will be variable, then we cannot have the Fourier law. We will use the governing differential equation for cylinder 1 by R, d by dr into R into dt by dr plus Q dot by K is equal to 0. That is the governing differential equation. If we integrate this, if we integrate and use the boundary condition, so the condition is at R is equal to capital R. It is a solid cylinder. The temperature is Ts. And at any R, the temperature is T. So if we integrate and put the boundary condition, then we will get the temperature profile. What will be the nature of temperature profile? Whenever there is a heat generation, the temperature profile will be. What will be the nature of temperature profile when there is a heat generation? बताइए, what will be the nature of temperature profile? Solid cylinder with heat generation. Solid cylinder with heat generation. The nature of temperature profile. Yes, whenever there is a heat generation, the nature of temperature profile will be parabolic. So T is given by Ts plus Q dot by 4K. It will be 4 here into capital R square minus small r square. That will be the nature, or that will be the expression, that is parabola. The temperature profile will be parabolic, and at the center, there will not be any logarithmic term. लॉगरिथमिक नहीं आएगा. There will not be any logarithmic term, right? This is the temperature profile, and at the center the temperature is maximum. If we draw the temperature profile at the surface, temperature is Ts, the temperature profile will be like this. This is temperature Ts, this is temperature Ts. Here the temperature is maximum at R is equal to 0. This is radial direction. This is R is equal to capital R. This is how the temperature profile will look like. So T maximum can be written as, when R is equal to 0, so it will be Ts plus Q dot capital R square by 4K. That is the maximum temperature. That is the maximum temperature. And the rate of heat transfer, Q is equal to minus K into 2 pi RL into dt by dr. This is how we can find out the temp. Because temperature is a parabolic function, so dt by dr is linear function of R, and 1 R is already there. Then we can say Q is proportional to R square. Q will be proportional to R square because dt by dr is directly proportional to R because of parabolic nature of temperature profile. When the temperature profile is parabolic, then the slope will be linear. So Q will be function of R square, and Q will be 0 at the center. At the center, Q will be 0, and Q will be variable like this. This is variation of Q with R. For solid sphere, again the governing differential equation, if we write heat generation, Q generation is not 0. So Q is variable. So governing differential equation 1 upon R square d by dr into R square into dt by dr plus Q dot by K is equal to 0. Then if we integrate this, the boundary condition is again at R is equal to capital R, the temperature is Ts, and at any R, the temperature is T. So if we do the analysis, then we will get T is equal to Ts plus Q dot by 6K. It will be 6K into capital R square minus small r square. It is also parabolic. That is the only difference. For a sphere, it will be 6K. For a cylinder, it will be 4K. And the temperature will be maximum at the center. The temperature profile will look like this only. This is Ts, this is Ts. R is equal to 0, temperature is maximum, and the maximum temperature is given by Ts plus Q dot by 6K into capital R square. You need to memorize this. You need to memorize this. All right. Is this clear? And Q is given by minus K. Area will be 4 pi R square because it is a sphere into dt by dr. Because dt by dr is the linear function of R and there is R square, so Q will be proportional to R cube. Q will be proportional to R cube. The rate of heat transfer is cubic function of R. The rate of heat transfer will be cubic function of R. Is this all clear to everyone? Is this all fine with everyone? Anybody is having any doubt, you can just let me know. Bataiye, is this all clear? If anybody is having anything to ask, you can just let me know. Now my last part is pending, that is composite system and combined modes of heat transfer. Then Suraj sir will be there to discuss about the critical insulation, fin theory and unsteady conduction. All right. So I will take around 30 to 45 minutes next to discuss the composite system, including having the combined modes of heat transfer. Shall we start? Or if anybody is having anything to ask, you can just let me know. Hi Shreyas, welcome. आशुतोष बताइए क्या? Heat generation in hollow cylinder, that is not important. Heat generation in hollow cylinder will not be important. That will make the analysis more and more complicated. So heat generation we will be talking about only in case of solid cylinder and solid sphere. Otherwise the analysis will become so complicated. So that is why it is not there in your syllabus. Nobody is going to ask you the condition for heat generation, because you need to have the two boundary conditions, and then applying the two boundary condition, the analysis will become complicated. क्यों आशुतोष, आप कहां प्रॉब्लम हो रही है मैं बताता हूं आपको. देखिए आप क्या कर रहे हैं, देखिए 1 by r into d by dr into r into dt by dr plus q dot by k is equal to 0, isn't it? Multiply whole expression with r, so it will be d by dr into r into dt by dr plus q dot r by k is equal to 0, isn't it? I have just multiplied, then integrate. So it will be r into dt by dr plus q dot by k into 2r is equal to 0, isn't it? So if we take r common, then it will be dt by it will be constant. If we integrate, then it will be constant, right? If we integrate, then dt by dr plus 2q dot by k is equal to constant, isn't it? Now because left hand side is looking like a function of r and right hand side is constant. Right hand side is constant and left hand side is a function of r. So this expression can be true only when this term is 0. The expression can be true only when this term is equal to 0. Then only the left hand side is the constant and the right hand side will be constant. So from here what we can find out, or what we can say, from here we can say dt by dr, what we can say, dt by dr plus 2q dot by k is equal to 0. क्या लिख दिया मैंने? सॉरी, मैं इट शुड नॉट बी लाइक दिस ना. इंटीग्रेट कर रहे हैं ना, r स्क्वायर बाई 2. इट शुड हैव बीन r स्क्वायर बाई 2. इट शुड हैव बीन r स्क्वायर बाई 2. q dot into r by 2k, like this. It should have been like this. So here dt by dr plus q dot r by 2k is equal to 0. Now if we integrate again, then t plus q dot r square by 4k is equal to constant c. This is how it will be integrated. And then at r is equal to capital R, at r is equal to capital R, temperature is Ts. We can find out the value of C. This is the expression. And at r is equal to capital R, the temperature is Ts. Then find out the value of C, and then this is how the integration will be done. Then you will get T is equal to Ts plus Q dot by 4k into capital R square minus small r square. Right? Ashutosh, is this clear? Acha Raghu. No problem, you can watch the recording. Which second term you are talking about? What I am saying is, this bracket has to be 0 because it is multiplied with r. This bracket has to be 0 because it is multiplied with r. If the bracket is non-zero, then it will become a function of r. So the bracket has to be 0. This is the bracket I am talking about. The constant will be 0. The value of constant will be 0 when the bracket will be 0. If the bracket is non-zero, then definitely the left hand side will be a function of r and right hand side is a constant. Then it will contradict. Right? Getting it? Ashutosh? The bracket has to be 0. Now let us move to the combined modes of heat transfer. What is the meaning of combined modes of heat transfer? When two or more modes of heat transfer are taking place simultaneously. Let us say this is the system. When two or more modes of heat transfer are occurring simultaneously, there might be a convection here, there might be a radiation here, there might be a conduction, then there might be convection and radiation, like this. When multiple modes of heat transfer are taking place through the system, then it is called as combined modes of heat transfer. So as long as we are talking about, so what we can say, there is no generation of the heat and there is no storage of the heat. As long as these two conditions, no heat generation and the system is in a steady state. If this is the condition, then we can say Q remains constant. Q in is equal to Q out. We are talking about no heat generation case. So Q in is equal to Q out is equal to constant. The rate of heat transfer will remain constant, that is Q. The rate of heat transfer will remain constant, that is Q. So the analysis will be done by using the circuit diagram. The analysis will be done by using the circuit diagram. We have already discussed about when this is Q, conduction. When the mode of heat transfer is conduction, then we have already talked about the thermal resistance due to conduction. Thermal resistance due to conduction. If the system is a plane wall, let me write once again. If the system is a plane wall, what is thermal resistance for conduction? Do you remember the formula L by Ka? If it is a hollow cylinder, then the thermal resistance due to conduction will be equal to Ln of R2 by R1 upon 2 pi KL. And if it is a hollow sphere, The thermal resistance is given by R2 minus R1 upon 4 pi K R1 R2. This is what we have already discussed. Conduction. Then if there is a convection, the mode of heat transfer is convection. For convection, we can say Q convection is equal to HA delta T. Q convection is equal to HA delta T. And that can be equated with delta T upon thermal resistance by convection. We can use circuit diagram. So from here we can say R thermal resistance for convection will be, convective thermal resistance will be equal to 1 upon H into A, surface area available for convection. The unit will be same, that is Kelvin per unit watt or degree Celsius per unit watt. Kelvin per unit watt or degree Celsius per unit watt. For radiation, because the thermal resistance expression will become complicated because of Stefan-Boltzmann law, because the radiation is also a surface phenomena, because the radiation can also be treated as a surface phenomena, thermal radiation can also be taken as a surface phenomena, and that is why we can write Q radiation to be like this: HR into surface area into bulk temperature difference, HR into A. So delta T upon thermal resistance, if we equate, then we can write the thermal resistance for radiation to be 1 upon HR into A, surface area. So here HR will be equal to radiative heat transfer coefficient. Radiative or radiation heat transfer coefficient, similar to convective heat transfer coefficient. The unit is watt per meter square Kelvin or watt per meter square degree Celsius. HR is the radiation heat transfer coefficient. So these are the thermal resistances we are going to use for drawing the circuit diagram. So when do we have the combination of resistances in series? These are the thermal resistances R1 and R2. Bulk temperature difference will be this. This is delta T. This is delta T overall thermal potential. This is, let us say, delta T1. This is, let us say, delta T2. This is Q, rate of heat transfer. When the resistances are connected in series combination, when will we have series combination? When the heat transfer occurs simultaneously. Modes of heat transfer occur simultaneously. Sorry, one after another. When mode of heat transfer takes place one after another. Or when the resistances are connected one after another. Series combination of resistances is when resistances are connected one after another. When the resistances are connected one after another. Right? Like this. First resistance, second resistance. So for this, we can say Q is equal to Q1 is equal to Q2 is equal to so on. That remains constant. The rate of heat transfer will be constant if the resistances are in series combination. And the delta T overall thermal potential is equal to delta T1 plus delta T2 plus delta T3 and so on. Overall thermal potential will be equal to delta T is overall thermal potential. That is called as overall thermal potential. Overall thermal potential. And with this we can say equivalent thermal resistance is given by R1 plus R2 plus R3 and so on. Equivalent thermal resistance will be given by this, and we can also write Q is equal to delta T overall upon equivalent thermal resistance is equal to delta T1 by R1 is equal to delta T2 by R2 and so on is equal to, because Q will remain constant as long as we are talking about no heat generation and steady state system. These are the various parameters we can apply for series combination of thermal resistances. It is like circuit diagram. We are using the circuit diagram similar to electrical circuit. In case of electrical circuit, if they are connected in series, the current remains same and the voltage potential, electrical potential keeps on adding, and the equivalent resistance is R1 plus R2 and so on. For parallel combination, when do we have parallel combination? When connected simultaneously. When the heat transfer takes place simultaneously. When they are connected simultaneously. And they are connected simultaneously like this. This is the rate of heat transfer. Here it will be Q1, here it will be Q2. This is delta T overall, or we can call it as delta T1 or delta T2, like this. So when the resistances are connected in parallel, so Q will be equal to Q1 plus Q2 plus Q3 and so on. Q will be Q1 plus Q2 and so on. Delta T overall is equal to delta T1 is equal to delta T2 is equal to so on. And 1 upon equivalent thermal resistance is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. We can write this. For two resistances, equivalent resistance will be R1 into R2 upon R1 plus R2. And because delta T1 is equal to delta T2, so delta T overall is what? So we can write here Q into R equivalent will be equal to Q1 into R1 is equal to Q2 into R2 is equal to so on. Or from here we can say Q1 by Q2 will be nothing but R2 by R1. The ratio of Q1 by Q2 can be calculated. Q1 by Q2 will be equal to R2 by R1. This is how the parallel combination of resistance can be analyzed. And if we talk about the composite system which is made up of more materials, the system which is made of more than one material, that is called as composite system. And if the materials are joined one after another, then it will have a series combination of resistances. If the materials are connected one after another, then it will give the series combination R1, R2. What is R1? If I write R1, R1 is equal to L1 by K1 into A. Area will remain same. Area will remain constant. And R2 will be equal to L2 thickness upon K2 into A. Like this. So R equivalent can be written as R equivalent can be written as 1 upon A, then L1 by K1 plus L2 by K2. R equivalent will be equal to R1 plus R2. That is the equivalent resistance. We can find out Q either from here, Q1 is equal to Q2 is equal to Q2 and so on. That is composite plane wall or composite system. And if the composite system materials are arranged simultaneously, connected simultaneously, if they are connected simultaneously like material 1 and material 2, this is the direction of heat transfer. This is Q1, this is Q2. So for parallel combination, we all know what is R1. R1 will be equal to L1 by K1 into A1. What is A1 and A2? Here A1 is the area which is perpendicular to direction of conduction. This is A1 and A2 will be the other area. This is A2. This is A2. A1 and A2 are the area which is perpendicular to the direction of heat flow. So R2 will be equal to L2 by K2 into A2. L1 and L2 can be taken same. Here L1 is equal to L2 is equal to L. L1 and L2 are same. So for parallel combination, R equivalent can be written as R1 into R2 upon R1 plus R2. Isn't it? Q1 by Q2 will be equal to R2 by R1. That is how we can analyze. Now let us talk about composite plane wall with convective environment. There is convection in inner fluid and outer fluid. Now let us talk about this type of system. There is system 1, material 2. This is L1 and this is L2. There is convection, inner fluid. There is a convection in outer fluid. Outer fluid temperature is T0. Inner fluid temperature is Ti. Here the temperature is T1. Here the temperature is T2. Or let me write. Here the temperature is T1. Here the temperature is, let us say, T2. Here the temperature is, let us say, T3. Ti, T0 and convective heat transfer coefficient is Hi, for outer fluid H0. So if we draw the circuit diagram for this, there will be 4 resistances in series, isn't it? How many resistances will be there? For this situation, if there is only convection, so 2 thermal resistances for convection and 2 thermal resistance for conduction. The total number of thermal resistance will be, there will be 4 thermal resistance. This is R1, R2, R3 and R4 which are connected in series. What is R1? 1 upon Hi into A. What is R2? L1 by K1 into A. What is R3? L2 by K2 into A. Isn't it? What is R4? That is 1 upon H0 into A. So equivalent resistance is equal to R1 plus R2. What is equivalent thermal resistance? That is R1 plus R2 plus R3 plus R4. So if we write this, then it will be 1 upon A, 1 upon Hi plus L1 by K1 plus L2 by K2 plus 1 upon H0. That is the equivalent thermal resistance. And delta T overall will be, delta T overall thermal potential will be Ti minus T0. Ti minus T0. That is the overall thermal potential Ti minus T0, right? So for n layers, if we generalize it for n number of layers, then how to write? There will be n plus 2 resistances. Isn't it? N plus 2 resistances. 2 resistances for inner convection and outer convection, and n is the number of resistances for conduction. So we can write the equivalent thermal resistance as 1 upon A, which is common, 1 upon Hi plus summation of Lj by Kj and the limit of J is equal to 1 to N plus 1 upon H0. That is our equivalent, and Q will be equal to delta T overall upon R equivalent, or we can write it as Q delta T1 upon R1, or we can write it as delta T1 by R1 is equal to delta T2 by R2 and so on, because Q will remain constant. That is how we can write equivalent thermal resistance for n layers, isn't it? It is not a new topic actually. It is the application of the things which we have studied so far. It is only the application. It is only the extension of the topics which we have studied so far. We have already discussed about the thermal resistances. So if they are connected in series, according to that series combination concept will be applied. And if they are connected in parallel, the parallel concept can be applied. Now there is another parameter defined that is called as overall heat transfer coefficient, which is defined for composite system and combined modes of heat transfer plus combined modes. If there is a composite system involving combined modes of heat transfer, then we define overall heat transfer coefficient. What is that? The rate of heat transfer per unit surface area per unit overall thermal potential. So we can say Q is equal to, if we are using U into A, then we should use delta T overall. Or we can say delta T, or we can say U is equal to Q upon A into delta T overall. That is how it is defined. The rate of heat transfer per unit area per unit overall thermal potential. The unit is watt per meter square Kelvin or watt per meter square degree Celsius. To analyze it, to analyze the conduction or the heat transfer, considering it is a single system, we can define the overall heat transfer coefficient U. U is the overall heat transfer coefficient. And how to find out the value of U? Look, we can say as Q is also equal to delta T overall upon R equivalent. So by comparing these two, what we can say, if we compare these two, from this, we can say U into A into R equivalent is equal to 1. Or we can say U is equal to 1 upon A into R equivalent. If we put the value of R equivalent in the denominator and multiplied by 1, multiplied with A, then we will get the expression for U. Look, this is R equivalent multiplied by A getting cancelled out, and that is in the denominator. So the expression for U can be written as 1 divided by 1 upon Hi plus summation Lj by Kj plus 1 upon H naught. That is how we can write U. That is the mathematical expression for U. So if we want to write Q is equal to, if we are using Hi, then we will use A into Ti minus T1. Then we will write Ti minus T1. If we are writing using the conduction, then it will be K1 into A into T1 minus T2 by L1. Or if we use for second material K2 into A into T2 minus T3 upon L2. And if we are using U into A, then it will be Ti minus T naught. That is the difference. If you are using Hi, then the corresponding temperature difference will be taken into consideration. But if we are using U, then it will be overall temperature difference, or we can write it as delta T overall upon R equivalent as well. That is the meaning of defining U, overall heat transfer coefficient. That is the expression. Clear? Now, another important concept, when two materials are joined with one another to make a composite system, when we join two materials with one another to make a composite system, there is a fair possibility that air might be trapped in between the surfaces. If the air is getting trapped, then that contact will develop a resistance to the heat flow. That resistance is known as contact resistance. If the joining surfaces are very smooth, if we are joining the surfaces which are very smooth, okay Raghu, definitely we will do. If the joining surfaces are very smooth, then the contact resistance will be negligible. But if we join two surfaces which are having rough surfaces, if we join the two surfaces which are rough, then due to roughness of the surfaces, the air might get trapped and that will develop a resistance, extra resistance to the heat flow. That is known as contact resistance. Contact resistance will be 0 if there is a perfect contact or smooth contact. We have not talked about any contact resistance. For an example, what we have discussed so far is, this is, let us say, T1 temperature. I have taken the temperature T2. This is the interface, and the interface temperature is taken as T2, and this is T3. So there will be two resistances. The temperature profile will be like this. The temperature profile will be linear. This is T1, this is T2, this is T3, let us say. These are the two materials joined with one another. This is the interface. If the contact is smooth, then the interface temperature T2 will be shared by both the materials 1 and 2. The temperature will be same for both the joining materials 1 and 2, right? So there will be two resistances, R1 and R2. R1 is L1 by K1 into A, and R2 is equal to L2 by K2 into A. So there is no problem when the contact is smooth. This is Q. But whenever the contact is not perfect, when the contact is not perfect, then there is a temperature drop at the interface. When the contact is not perfect, if it is imperfect contact, or if it is rough contact, if there is a rough contact between the surfaces like this, there is a roughness here. The joining surfaces are not smooth. There is a roughness between the joining surfaces. Then there is an extra resistance developed. That is called as contact resistance. This is developed. The contact resistance is the resistance. The contact resistance is the resistance that an interface offers. The resistance that an interface offers to the heat transfer. That is called as contact resistance. The resistance offered by the interface to the heat transfer. So here the temperature is, let us say, T1. Look, the temperature profile will be like this. This is T1, this point is T2, this is T3, and this point temperature is T2 dash. There is a drop in temperature here also. There will be a drop in temperature here also. So that will provide an extra resistance to the heat flow. That will provide an extra resistance to the heat flow. That is called as, this will provide an extra resistance to the heat flow. So here it is R1 as usual, L1 by K1 into A. Here it is R2, that is L2 by K2 into A. And here this is called as contact resistance. And this temperature difference is delta T at the interface. Delta T at the interface, which is equal to, what is delta T at the interface? Delta T at the interface is equal to T2 minus T2 dash. So we can write Q dash, let me call it as Q dash, which will be less than earlier Q. Q dash will be less than earlier Q. This was Q, and here, sorry, Q dash will be more than earlier Q. Here Q is equal to delta T overall upon R1 plus R2. Q was, and here Q dash will be equal to delta T overall. There is no change in delta T overall. R1 plus RC plus R2. So Q dash will be less than Q, isn't it? That is called as contact resistance. What is the unit of RC? We can find out RC like this. Q dash is equal to delta T interface upon RC. So RC will be having the unit. What is the unit? Kelvin per unit watt. That is called as thermal contact resistance. That is called as thermal contact resistance. There is another term defined, that is called as contact conductance. RC is called as thermal contact resistance. The unit is Kelvin per unit watt. So the various points about the thermal contact resistance, try to understand. It comes into effect due to imperfect contact between the surfaces. it is undesirable because it reduces the heat transfer rate. Why? Because equivalent resistance increases. It increases the resistance. So that is why it is undesirable. So it can be minimized by increasing the contact area by making surfaces smooth. The more is the contact area, the contact resistance will become less, and it becomes insignificant in mechanical applications because of large heat transfer rates. But it is very, very important to understand the concept of contact resistance in case of electrical systems, electronic applications due to low heat transfer rates. So look, RC is called as thermal contact resistance. There is the term defined that is called as thermal contact conductance. 1 upon RC. HC. Just a second. RC is thermal contact resistance. Shall I add one slide? Look, RC is called as RC is called as thermal contact resistance. The unit is Kelvin per unit watt. And A multiplied by RC, that is called as unit thermal contact resistance. Contact resistance. The unit will become meter square Kelvin per unit watt. That is called as unit thermal resistance. And 1 upon A into RC, that is equal to HC. That is called as unit thermal conductance. The unit will decide whether it is thermal conductance given or thermal resistance. This is called as unit thermal conductance. The unit will be watt per meter square Kelvin. So if we want to write RC, so RC is equal to 1 upon HC into A, isn't it? Isn't it? So that is how we can write. Unit thermal conductance, watt per meter square Kelvin. It is similar to 1 upon HA. That is called as contact resistance, 1 upon HA. But here it is the contact conductance. HC is the unit thermal contact conductance. Contact conductance. So let us solve one question and then we will proceed to the cylindrical system and spherical system with combined modes of heat transfer. Sorry. Yes, there is a question on the screen. Can you solve this one? There is a question on the screen. Look, the thermal contact conductance, the question says, the thermal contact conductance at the interface of two 1 centimeter thick, there are two copper plates, 1 centimeter thick. This is also 1 centimeter. There is a contact resistance between this. There is a copper plate. This is also a copper plate. So the thermal contact conductance at the interface of two 1 centimeter thick copper plate is measured to be 18,000 watt per meter square degree Celsius. What is this? This is HC, 18,000 watt per meter square degree Celsius. This is HC, unit thermal conductance, isn't it? This is the unit thermal conductance. Determine the thickness of the copper plate whose thermal resistance. You need to find out the thickness of a copper plate whose thickness we need to find out, whose thermal resistance is equal to the thermal resistance of the interface between the plates. So if we equate what is the thermal resistance for this copper plate, L by K of copper into A, that is the thermal resistance, is equal to 1 upon Hc into A, isn't it? That is the thermal resistance Rc. This is Rc, thermal contact resistance, and this is the thermal resistance for conduction in a copper plate. If you simplify this, area getting cancelled out, then you need to find out L. L is equal to thermal conductivity of copper upon Hc. Can you do the calculation? Thermal conductivity of copper is 386 and Hc is given as 18,000 watt per meter square degree Celsius. What is the answer? Are you getting 2.14 centimeter or not? Are you getting 2.14 centimeter or not? Please check and do let me know. बताइए 2.14 सेंटीमीटर. All right. The next one is composite cylinder with convective environment. This is the composite cylinder. Inner fluid Ti, outer fluid H0 and T0. So if the heat is flowing from inside to outside, Q will be constant. There will be 4 resistances in series, R1, R2, R3 and R4. 4 resistances in series, and the equivalent resistance will be R1 plus R2 plus R3 plus R4. What is R1? 1 upon Hi into 2 pi R1L. Isn't it? What is R2? Ln of R2 by R1 upon 2 pi K1L. What is R3? Ln of R3 by R2 upon 2 pi K2L. And what is R4? 1 upon H0 into 2 pi R3 into L. This will be the resistance. So if we write R equivalent from here, what will be the R equivalent? R equivalent is equal to 1 upon 2 pi L. Then it will be 1 upon Hi plus, or if we generalize it, ln of R2 by R1 upon K1 plus ln of R3 by R2 upon K2 plus 1 upon H0 into R3. This will be the expression for n layers. For n layers, there will be n plus 2 resistances. For n layers, there will be n plus 2 resistances. So R equivalent will be equal to 1 upon 2 pi L if we take common, 1 upon Hi plus, it will be R1 also. So Hi into R1 plus summation of ln of Rj plus 1 upon Rj upon Kj plus 1 upon H0 into Rn plus 1. This will be the expression for n layers, R equivalent. We define overall heat transfer coefficient because Ai is not equal to A0. Ai is equal to 2 pi R1L and A0 is equal to 2 pi Rn plus 1 into L. So A1, Ai and A0 are not equal. So there are 2 overall heat transfer coefficients are defined. We can write Q is equal to, if I write Ui, then we will write Ai into overall thermal potential is equal to U0 into A0 into a overall thermal potential, or we can write overall thermal potential upon equivalent resistance. That remains constant. So from here we can say Ui into Ai into R equivalent. So I will take 10 minutes more, 10 to 15 minutes more, and then Suraj sir will be coming and he will discuss the remaining part of the conduction. All right, or Suraj sir might give you a little break to you. R equivalent is equal to U naught into A naught into R equivalent will be equal to 1. Or we can say Ui into R1 is equal to U naught into Rn plus 1 is equal to 1 upon 2 pi L into R equivalent. So if we multiply R equivalent with 2 pi L, then we can find out Ui, and so what we can write here, Ai is equal to 2 pi R1L, A naught is equal to 2 pi Rn plus 1 into L. So from here we can easily find out Ui and U naught. So Ui into R1 is equal to U naught into Rn plus 1 is equal to 1 upon, it will be 1 upon Hi into R1 plus summation ln of Rj plus 1 upon Rj upon Kj plus 1 upon H naught into Rn plus 1. No need to memorize this. No need to memorize. If we want to find out Ui, then divide this right hand side expression with R1. If we want to find out U naught, then divide the right hand side with Rn plus 1. From here we can find out the expression for Ui and U naught. This will give you the expression for Ui and U naught. All right. Similarly, composite is paired with convective environment. Ai is equal to 4 pi R1 square and A naught is equal to 4 pi R3 square. For 2 layers, this is R3, this is R1, R2, R3, R4. If we write R1 is 1 upon Hi into 4 pi R1 square. This is R2 minus R1 upon 4 pi K1 R1 R2. This is R3 minus R2 upon 4 pi K2 into R2 into R3. Then this is 1 upon H naught into 4 pi R3 square. Like this. Again, Q is equal to Ui into Ai into delta T overall is equal to U naught into A naught into delta T overall is equal to delta T overall upon R equivalent. That is constant. So from here we can write Ui into Ai into R equivalent will be equal to U naught into A naught into R equivalent will be equal to 1, and Ui into R1 square is equal to U naught into Rn plus 1 square. I am writing general expression. I have not written R equivalent, general expression for R equivalent is equal to 1 upon 4 pi into R equivalent. What is R equivalent general expression? That is 1 upon 4 pi into 1 upon Hi into R1 square plus summation of Rj plus 1 minus Rj upon Kj into Rj plus 1 plus 1 upon H naught into Rn plus 1 square. This is R equivalent. If we multiply with 4 pi, if we put the value here, then we can find out Ui and U naught separately. We can find out Ui and U naught. Malaise conduction, steady state conduction, composite system is completed. Next, Suraj sir will be coming and he will discuss the insulation method, pin theory and unsteady state conduction. That will complete our conduction part. That is 60% of your syllabus. So remaining 40% will be convection, radiation and heat exchanger. 3 topics will be left, and once Suraj sir completes this whole conduction, then I will be coming back and we will discuss, I will discuss the convection part. All right. If anybody is having any doubt, you can just let me know. Anybody is having anything to ask? Will you be able to write UI and U naught? I have already written overall heat transfer coefficient. Right. So that is all from my side. So let us welcome Suraj sir.
So I think you are pretty much excited also, and you have learned about the entire topic of conduction. So I think let's take a lunch break of 10-15 minutes. I don't want you to be completely वो हो जाए कि आप थक जाओ, है ना? So it's up to you. We can take a 10 minutes break or 15 minutes break. So after that we'll be continuing with our session. So I think it's 1:38. Let's resume at set 45. ठीक है, 45 पे resume करते हैं, right? और चलो 50 पे कर लेते हैं. Fine. So now let's start continuing our discussion of the critical radius of insulation. Now, what is the critical radius of insulation? Why we are studying this critical radius? Why we are seeing this as critical radius? And I would say that this is a most important topic in the conduction part. If you see the last year trends, if you talk about the engineering surveys, if you talk about gate examination, you always expect a question from this topic. Okay, so it's very important that you should be having a clarity, because students do commit mistake in this topic of critical radius of insulation. So let us understand what is this critical radius. Now, if you see on your screen, there are two images on the left hand side and right hand side. We are having a air conditioning duct over here, and we are having a electric wire. In both cases, we are using an insulation, right? But can you tell me, are we doing insulation in AC ducts to reduce the heat transfer or increase the heat transfer? This is an air conditioner duct. This is an AC duct. Quickly, tell me one thing. We are doing insulation over here to increase the heat transfer, decrease the heat transfer. Yes, quickly. Yes. Very easy. We are using this insulation. There is a duct over which I am having a coating of some insulator material. Definitely we need to reduce the rate of heat transfer, right? Heat transfer should be decreased, right? Our main agenda, the main objective of using an insulation over here is to reduce the rate of heat transfer. Okay, but over here, if you try to see, we are having an insulation. This is an insulation, right? This is an insulation. We are having a current carrying wire, right? This is an electric wire. Okay, this is an electric wire. So my question to all of you is, so if you are applying an insulation over an electric wire, through electric wire current is flowing, and we know in our basic electrical, you might have studied about V into I. What is V into I? This is the amount of heat that is being generated when current is flowing through the wire. And I want this heat to be dissipated as quick as possible. But the problem over here is, you are using an insulation, then how we can say the heat transfer will be increasing? It has to decrease. Then ideally, you should not be using an insulation in electric wire. Yes, but it's not that happening. Are we not using insulation? Let us imagine a situation. You are having an you're having a mobile charger, right? And you have charging your phone, and the wire is live. There is no insulation. And in sote in the dream, you are thinking about heat transfer, and suddenly you touch that live wire. You'll be thinking about this concept. We could have did some insulation in order to have some safety condition. In order to have that safety condition, right? So here insulation we are using to do the safety, right? But if I talk about over here, we are using the insulation to decrease the heat transfer. But the problem here is, if you are using insulation, then definitely your heat transfer is going to decrease or increase. For that, you should be knowing about the concept of critical radius of insulation, right? So let us take one wire. Let us take one wire, right? This is a wire, and over which I'm using an insulator. Over which I'm using an insulator which is having a thermal conductivity of K, right? I'm taking a internal radius Ri and external radius is Ro. Like it's something like this. If you try to see, it is something like this. This is your Ri, and from the center point till this point, right? It is something like this. This is the wire and this is the insulation that we are doing, and the outer radius is this one. So if you try to visualize, Chandra sir have discussed one very important concept about the combined mode of heat transfer, where we're having a hollow cylinder, and from the hollow cylinder, from the surface, we're having a convective heat transfer, right? So let us suppose if I'm talking about two resistances over here, right? Let's say this is R1, this is R2. That means your R1 is nothing but your conduction resistance, and R2 is your convection resistance. So can you tell me what kind of we can say temperature drop is happening in a hollow cylinder? You might have studied right now. What kind of temperature profile you are seeing in a hollow cylinder with no heat generation? We have studied it's a logarithmic. Huh? We have already seen that this is a logarithmic temperature profile. So can we write it like the total resistance is equal to the summation of conduction plus convection, right? So what is conduction resistance? That is ln of the outer radius divided by the inner radius divided by 2 pi k of the insulator, right? K of the insulator into L plus 1 upon H into 2 pi Rho into L. Okay, fine, right? So you can see that in one term, in conductive term, if you try to increase the value of the outer radius, what will happen to the conductive resistance? Anyone? If you try to increase the outer radius, what will happen to the conductive resistance? Sir, it is in the numerator. It is guaranteed it will be increasing. Okay, but if you see in the convection heat transfer, it is in the denominator. So if you try to increase the Rho, your convection resistance is going to decrease, right? Fine, that means one parameter is increasing, second parameter is decreasing. So if I talk about R total, which is the summation of these two resistances, it is being observed that up to certain limit, up to certain value, this R total is going to decrease. Okay, up to certain value, this R total is going to decrease. Beyond that, this R total is going to increase. So what is the, we can say the relation between the R total and heat transfer? We have already studied that heat transfer is nothing but, it is inversely proportional to the resistance, or we can say total resistance. Okay, so if your Rho is increasing in the first region, the R total is decreasing, and when R total decreases, the heat transfer or Q is increasing. And after that, in the second region, what happens? Your R total is increasing, and due to this, the heat transfer will decrease. So if I try to plot a graph between the outer radius and the heat transfer, right, we are getting a graph something like this. Okay, that means if I divide this into two regions, this is region number 1, this is region number 2. In region number 1, when you add insulation, the heat transfer, instead of decreasing, it is increasing. If you try to visualize, let's say this is the initial radius. Okay, after insulation, the radius has increased because this is the outer radius on the x-axis. So once you are increasing the your insulation or radius, so your heat transfer, instead of decreasing, it is increasing. But beyond that, what is being observed that when I try to add insulation, let us suppose this is the initial outer radius. After insulation, the outer radius is going to increase. So if you clearly see that your heat transfer has been decreased. So now you can clearly see that this is two regions. In region number 1, if you try to add insulation, the heat transfer is gonna increase. In region number 2, if you add insulation, the heat transfer is gonna decrease. And that is the reason you might have observed that whenever I'm designing any kind of electric appliances, whenever I'm designing any kind of electric appliances, right, I'm designing in this particular region. All the electric appliances is the wires or electric wires, instead of appliances we can say electric wires, is being designed in this particular region because I want a safety factor. and if I add insulation, it should not be decreasing heat transfer, it should be increasing the heat transfer. And beyond this, in this particular region, region number 2, it is being observed that all the refrigeration system is being used in the second region, right? So this is your RO, this is your heat transfer. So if you see, there is one point at which your heat transfer is maximum, and that radius we call it as the critical radius. That radius we call it as the critical radius. Critical radius of insulation. Okay, fine. Now the next step is how to calculate this. It's very easy. If I want to have maximum heat transfer, if I want to have this to be maximum, then means R total should be minimum. If R total is minimum, so you can clearly visualize R total is nothing but the summation of these two resistances, right? So I need to differentiate this equation with respect to RO. So let us differentiate this equation. That means for minimum total resistance, we can simply say that the differentiation of R total with respect to the outer radius equal to 0, because the only outer radius is the factor or is the parameter which we can change. You cannot change the radius of the wire. You cannot change the K value of the wire. You cannot change the length of the wire, right? You cannot change the ambient condition. The only thing that you can change is you can increase the insulation. So if you try to increase the thickness of insulation, what is happening? You are increasing the RO value, right? So now RO is the only factor or only parameter that you can change. So now we can say that if you try to differentiate, we are getting RO is equal to K insulator by H. And this outer radius is that radius at which we are having the maximum heat transfer, and this radius we call it as the critical radius of insulation. Critical radius of insulation, right? This is, I'm talking about a cylinder, that means I'm talking about for a wire or cylinder, right? I'm discussing for a wire or cylinder. Now we can have a situation that we can have a spherical system, something like this. We can have the critical radius for the spherical system also. Let me write in the next slide. We can have a critical radius for a spherical system also, or a spherical element, right? So for a spherical system, we can say that if I say this is a metallic body over which I am having a coating of an insulation. Okay, this is a sphere. This is a sphere, right? This is an insulation. This is K insulator, right? So we can have still two resistances over here. This is your conductive resistance. This is your convective resistance. So can you tell me what is the formulation of conductive resistance for a hollow sphere? Already you might have studied that. For a sphere, your R conduction, precisely a hollow sphere, R conduction is nothing but, we can say it is equal to 1 upon Ri minus 1 upon Ro divided by 4 pi K of the insulator. Right? What is the convective resistance? Your convective resistance will be equal to 1 upon H into what is the surface area of a sphere? That is 4 pi Ro square. Okay. So again, same concept will be applied, and it is being observed that when you try to differentiate the total resistance, here you are getting the critical radius as twice of K by K insulation by H. Okay. Whenever we are discussing about for a spherical system, I am getting the critical radius as twice more than that of the cylindrical system. Okay. Now here the confusion always lies is, sir, sometimes they are asking some thickness of insulation, sometimes they are asking a radius of insulation. Let us take an example. Let us suppose I am having a wire, a radius of a wire is, let's say, 5 mm. Okay, let's take an example. Fine. And the thermal conductivity is of the wire. Let's take all the possible values. Wire is 200 watt per meter Kelvin. Okay, and your K of the insulator is 0.1 watt per meter Kelvin. Okay, and your H value is 1000 watt per meter square Kelvin. Okay, let's take it as 0.8, right? It is 100. Fine. Now, can you tell me? This is a we can say this is a hollow sphere. For an insulation, this is a hollow sphere. Inside this, we are having a solid sphere. No problem. I'm not taking it that into consideration. I'm taking a hollow sphere. That's it. That is the reason I'm taking only one resistance, that is of this offered by this particular hollow sphere. Okay, Surinder, are you able to understand? Because we are having a, let us take an example. We are having a ball, okay, a Costco ball. If you try to have an insulation, and if you try to remove that Costco ball, we are having a hollow sphere. Similarly, like this, right? So now let us take this example. So tell me that if you add insulation, what will happen? Heat transfer increase, heat transfer decrease, heat transfer increase, then decrease, or heat transfer decrease, then increase. Can you tell me what will be the possible answer for this? What will be the possible answer for this? Quickly. What could be the possible answer? Now, if you try to understand, we are having a wire, okay? We are having a wire, right? Whose radius is 5 mm, right? We need to add an insulation. We need to add an insulation. So, can you tell me what is the critical radius? Very good, perfect. Sir, critical radius is K by H. Now here I am having two K values. One is of wire, second is of the insulator. Always remember that. We always take the thermal conductivity of the insulator, not the wire. If while discussing also I have written KIN by H. So from here I can say 0.8 by 100, that is equal to 8 mm. That means what is the meaning of this? Your critical radius is 8 mm. That means if you try to add an insulation, can you tell me what should be the thickness of insulation for maximum heat transfer? What should be the thickness of insulation for maximum heat transfer? That means they are saying you should be having a critical radius. So if I want to have a critical radius of 8 mm, so I need to have an insulation of how much? 3 mm. So 3 mm will be called as the critical thickness of insulation. Critical thickness of insulation. Is this clear? Fine. Please remember this. Students do commit mistakes. So here, what is happening? Initially, we were having a 5 mm radius. We added insulation till 8 mm, right? That means 3 mm thickness of insulation we have did. So after that, what will happen? The heat transfer is going to decrease. So final answer will be heat transfer first increase to maximum, then it will decrease. If you try to understand from a graphical perspective also, this is the critical radius, which is equal to 8. Initially, you were at 5. So when you add insulation, the heat transfer is going to increase. Beyond 8, the heat transfer is going to decrease. Okay? Is this clear? Simple logic. Very simple logic. Fine. The concept of critical radius of insulation. Okay? Fine. Okay, let me ask you one more question. Let us suppose if this would have been, let us suppose dia of wire to be 8 mm. Now, can anyone who can tell me what will be our answer? What should be the critical thickness of insulation? Can anyone who can tell me the answer? Let us suppose instead of radius, they are giving the dia of the wire is 8 mm. What should be the critical thickness of insulation? Anyone? Yes? Okay. 4. Okay, anyone else? It's very easy question. Or will it be 0? Sir, RC is equal to 0. It's equal to 8 mm and it is exactly equal to the dia of the wire. So will it be equal to 0 or will it be having some another value? Perfect. Very good. It will be 4. Why it will be 4? Because now if you try to see, they are giving you the diameter. Okay. That means the radius is 4 mm. Critical radius is 8 mm. So what is the thickness of insulation? 4 mm. Is this clear? The thickness of insulation will be exactly equal to 4 mm. Okay. Done. So this basically winds up your critical radius of insulation. I hope so now this is clarified. So can we proceed to the next topic? Fins. Very interesting, very important. Because if you see the recent trend, they have now started asking the question for the fins topic also. Okay. Now what is the meaning of this word fins? Fins is basically the extended surface which is used to increase the heat transfer rate. Okay, we call it as extended surface or fins, which is basically used to extend surface. Okay, if radius would have been 8 mm. Okay, very good question from Surender. He is saying, sir, if radius was 8 mm, then that means you are at the critical radius. If you add insulation, what will happen? You are already at this point. When you add insulation, you are going in the region number 2. What will happen to the heat transfer? Will it increase or decrease? It will increase or decrease? It will decrease. Okay, you are already in the you are at the, we can say, limiting value. This is the 8 mm, right? So when you try to add insulation, you are moving toward this side. The heat transfer is going to decrease. Okay. Fine. So now let's discuss about the fins topic. Now in fins, basically we are using the fins to increase the rate of heat transfer by adding some extended surface. Just like this, if you see on the back of the refrigerator also, you can see some extended surface, we call it as fins. On the engines also, you can see some extended surface, we call it as fins. Okay, fine. Now, there might be some properties on which the fins will be depending, and it's very important from any examination perspective that you should be knowing what are the different properties of the fin. Okay, so for that you should be knowing a simple fin analysis. We'll be doing, I won't be going for derivation, but I'll be telling you some basic concepts that is being required for solving any question from the fins topic. Let us suppose I'm having a rectangular fin. Now this is, we call it as the base material. This is, we call it as prime surface or base surface or root surface. Okay, this we call it as prime surface, base surface or root surface. That means initially it was a surface like this. If there was no fin, it was a surface something like this. In order to increase the rate of heat transfer, I have added some extended surface so that I am enhancing the rate of heat transfer. Okay, now by doing this, what is a basic mechanism? What kind of mechanism is going on in a fins? If you try to visualize, this is your, we can say, root or base, that is x equal to 0. This is x equal to 0, right? And the heat is entering the system at this point. If you take any elemental strip, let's say I'm taking any elemental strip, what is happening? Whatever heat will be entering in form of conduction, same heat will be leaving in form of conduction from leaving the elemental surface. Some amount of heat will be lost in form of convection and in form of radiation also. But here we are not considering the radiation part because we are not dealing with at 1000 degrees Celsius or 5000 degrees Celsius. We are dealing at some nominal temperature near about to, let's say, 80 to 120 degrees Celsius or 150 degrees Celsius, right? So here radiation effects is basically nullified. We only consider that whatever heat, if I say a steady state condition, whatever heat is entering to this element should be equal to whatever heat is lost due to convection. This is your Q conduction. Okay, an amount of heat that is being stored inside the body. Fine. So now we have understood that fins are basically used to increase the rate of heat transfer. Now under fins, we are discussing three important we can say topics, or we can say condition. First condition is when the fin is infinitely long. Okay, that means your L will tending to infinity. Fine. Second condition is when the fin is finite but the tip is insulated. Tip is insulated, right? And third condition is the fin is finite and the tip is uninsulated. Now, the question over here lies is, we could have taken only two conditions. One is the fin is having infinite length. Second is the fin is having a finite length. What is the fundamental of using this particular term as insulated tip? Are you able to understand? You could have taken only two conditions. One is infinite and second is a finite length. That's it. Why we are taking a concept of tip is insulated? Let us have one discussion over here. Let us have one discussion over here. Let us take this example. Let us suppose the ambient condition, or let me take this. Yeah. Let us take this example. Let us suppose this is the root. This is your root or base, right? Whose temperature I'm keeping it as T0. Fine. And there's an ambient fluid at temperature T infinity having a convective heat transfer coefficient of H. Okay. Tell me one thing. As you're moving along the length of the fin, what is happening to the temperature? Is it decreasing or increasing? As you are moving along the length of the fin, let's say here we're having 300 degrees Celsius. Here it is 30 degrees Celsius, right? Fine. Can you tell me at this point, at the extreme tip, we can say, this is, we call it as tip. What will be the temperature at the tip minus T infinity? Whether it will be having a higher value or lower value? It will decrease, and definitely this temperature difference will be tending to zero. Ideally, it should be zero. In infinitely long case, this temperature difference, because infinitely long means the temperature at the tip is achieving the ambient temperature. That is the basic fundamental of using the infinitely long fin. Okay, so we have seen that what will be the heat loss from the tip. If I want to calculate what is the heat loss from the tip, that is equal to H into the area of the tip into T of the tip minus T infinity. You already know that this temperature difference is small. You know that. This temperature difference will always be having a small magnitude. Area, this is a cross-section area. Definitely this cross-section area is also very small. For 5 to 10 minutes, let us assume that the H value of the ambient air is also small or low. So when you try to multiply three small values, this heat transfer through the tip is almost negligible. And that is the reason we are taking the case of the tip is insulated. Is this clear? Fine. Why we are taking this condition of the tip is insulated? Because you should be knowing there are very important conditions that we are understanding over here. The convective heat transfer coefficient, we are normally taking it as a low value. The cross-section area of this particular fin is very less. The temperature difference from this particular tip to the surrounding condition will be very, very less. Okay, fine. So now we have able to understand this particular condition. Now let us take the analysis part. Let us take the first condition when the fin is infinitely long fin. Fin is infinitely long. Okay. So when I'm taking the fin as infinitely long, there are very important three important discussion that we have to do. One is what's the kind of temperature variation happening along the fin. Second is what is the rate of heat transfer through the fin. Third is what is the properties of the fin. That means what is the effectiveness and efficiency of the fin. These three important parameters we need to calculate for all the three cases. Okay. So what we have seen that for infinitely long fin, the temperature profile is T minus T infinity upon T0 minus T infinity is equal to e to the power minus m into x. This is the temperature distribution that we are getting. That means if I take a fin over here, okay, a rectangular fin over here, right? It is being observed that, let's say, I'm taking at any distance x. I'm taking at any distance x, right? Okay, the temperature is T at particular distance x. Okay, so it is being observed that the temperature is decreasing in an exponentially decreasing way. That means if I try to draw the temperature profile over here, okay, we can say this is your length x, this is your temperature T. It is decreasing in an exponentially decreasing way, and it will be tending to T infinity. Initial temperature is T naught, and it is decreasing in an exponential way. Okay, and what is this m? M is a constant that is equal to under root of pH by K into A. What is P? P, we call it as the cross-sectional perimeter. Cross-sectional perimeter, right? AC is cross-sectional area. H is convective heat transfer coefficient. And your K is the thermal conductivity of the fin. Thermal conductivity of the fin. Okay, fine. Under root of pH by K. Can you tell me what is the unit of this? Anyone who can help me out? What is the unit of this m? The unit of this m is per meter. The unit of this particular m, which is a constant, which we call it as per meter. Okay, fine. So if I try to visualize this particular diagram, right? If I try to visualize this particular diagram, I can say what is the cross-sectional perimeter for a rectangular fin? It is equal to W. Let's say this thickness is T, right? This thickness is small t. I can say this is equal to twice of width plus thickness. What is cross-section area? That is W into T. Okay? We are only considering the cross-sectional part of the fin. Fine. Is this clear? So we have observed that the temperature is varying in an exponential decreasing way. So next task is calculate the rate of heat transfer. So how to calculate the rate of heat transfer? It is being seen that whatever heat is entering the system at x equal to 0, can we say that is a rate of heat transfer? That means we can say the heat transfer through fin is nothing but, we can say that is equal to minus K cross section area del T by del X at x equal to 0. Yes, whatever heat is entering the system at the root, same heat will be traveling through the fin. If I say this is the fin and 100 watt is entering, so can I say 100 watts is the rate of heat transfer through the fin? Okay, fine. So how we can calculate this? We know this relation. We can take this T and we can calculate. So if I differentiate, and after differentiating, I'm getting the heat transfer through fin equal to under root of PHK cross section area into T0 minus T infinity. So this is the expression that you have seen for an infinitely long fin. For an infinitely long fin, we have seen that the heat transfer through the fin is root of PHKA into T0 minus T infinity. Fine. Okay, let's do one thing. Let us try to calculate the same thing for the second case when the fin is having insulated tip. Right? So when the fin is having insulated tip, right? So we can say that if I try to draw the diagram, this is insulated. Okay, fine. So it is being observed that the temperature distribution that we are getting T minus T infinity upon T0 minus T infinity is equal to cos hyperbolic m into L minus x divided by cos hyperbolic m into L. Okay, fine. This is again an exponential decreasing manner. This is not convective heat transfer coefficient. Please make sure that this is a hyperbolic function. Okay, this is a hyperbolic function. Fine. Okay, and we know that cos hyperbolic is nothing but again a negative distribution. So when you try to calculate the rate of heat transfer through the fin, it is coming out to be under root of PHK cross sectional area T0 minus T infinity into tan hyperbolic m into L. Tan hyperbolic m into L. Okay, fine. So this is the second case when we were discussing about the fin is having an insulated tip, right? Let us talk about the third, a general case, because this is actually we are using in a real life scenario. Fin with uninsulated tip. It's very important because many students are having a doubt over here when we're discussing about the fin with uninsulated tip. That means if I say I'm having a rectangular fin, okay, I'm having a rectangular fin, fine. Yeah, I'm having a rectangular fin which is having a length of L, having a width of W and a thickness of T. Fine. Is this clear? Fine. So now what we are doing is, now in this case the heat will be lost from the tip also. This is an uninsulated condition. So uninsulated tip condition, can we say the heat loss from the tip is not equal to 0? Right? Yes or no? Fine. So what we are doing is, let us try to have a very interesting, we can say parameter. We call it as corrected length. Let us try to have a discussion of this particular segment. What is this corrected length? Corrected length is nothing but it is equal to cross-sectional area by perimeter. And what is the meaning of this, or why we are using this corrected length over here? The meaning of corrected length is, I can assume this system is exactly equivalent to a system which is having a same fin, right? Same width, okay, same thickness, right? Same width, but the length has been changed to LC. The length has been changed to LC, and by changing this length from L to LC, I have converted this into a insulated tip. Now it is an insulated. Case number 2, and we have already had a discussion of an insulated tip. So now can I use the same relations that we have used over here? Same relation, instead of L, it will be LC. So still I'm not able to get how we are getting this. Actually what is happening is, if you try to visualize, what will be the corrected length? The corrected length will be equal to L plus cross-section area by perimeter. That means I am increasing the length. I am increasing this length. Let's suppose I'm increasing this length like this. This is an hypothetical length that I'm increasing, and assuming this is an insulated, and this portion that is being increased, that is equal to cross-section area by perimeter. Is this clear? Understood? What is the basic fundamental of using this corrected length? What I'm doing is, because I have already analyzed the insulated tip, I'm converting my case number 3 into case number 2 by introducing a concept of corrected length. Okay, because let us assume there is a fin having a length LC, tip is insulated. So can we say that the temperature profile will be equal to T minus T infinity upon T root minus T infinity is equal to cos hyperbolic m into corrected length minus x divided by cos hyperbolic m into corrected length. And if I want to write what is the heat transfer through fin, that is equal to under root of PHK cross section area T0 minus T infinity into tan hyperbolic m into LC. Is this clear? Fine. Why we have introduced this corrected length is, so can you tell me what is the corrected length value for a rectangular fin? What is the corrected length value first for a rectangular fin? Anyone who can tell me for a rectangular fin what is the value of the corrected length? If I say W is the width and T is the thickness. Anyone? So it's very easy. We have just now seen that corrected length is equal to L plus cross section area by perimeter. What is cross section area? W into T. Perimeter is 2 into W plus T. As we know that width is having a larger value than that of this. So we can say this is almost equal to W. So W into T by 2 into W. So L plus T by 2 is the corrected length. That means I am extending this particular fin by a length of T by 2, and by doing so now I can assume this to be an insulated tip. And this way I'm converting my case number 3 uninsulated to an insulated tip. Okay, now we can have a circular fin also. Let us suppose I'm having a circular fin like this. Okay, having a diameter of D, having a dia of D. This is length L. So what will be the corrected length? Anyone? Corrected length will be equal to L plus cross section area is pi by 4 D square and your circumference is pi D. So it will be what? D by. That means if I try to increase this length by D by 4, now you are having this particular concept of corrected length. Is this clear? Fine. This is the concept of corrected length. So now let us talk about the effectiveness and efficiency of the fin. Very important questions you can expect from this efficiency and effectiveness. First one is we call it as fin efficiency. What is fin efficiency? Fin efficiency is the actual heat transfer which is possible through a fin divided by the maximum possible heat transfer which can happen ideally through a fin. Okay, the efficiency of the fin is actual heat transfer to the maximum possible heat transfer. So if I try to take, let us suppose I'm taking any one case. Let us suppose I'm taking a case of let's say infinitely long fin. Okay, case number 1, fin is infinitely long. Okay, let us take this example. So in this case, let us suppose I'm taking a case of a circular fin. I'm taking a case of a circular fin. Okay, fine, right? So now in this particular circular fin, what is the actual heat transfer? Actual heat transfer is under root of PHKA T0 minus T infinity. Now the problem is how we can calculate the maximum possible heat transfer. What is the condition for maximum possible heat transfer? For maximum possible heat transfer, I should be having that the entire surface is kept at the same temperature. Let's say the base temperature, that is T naught. And how we can attain this particular condition? Anyone? How we can attain this condition that the entire surface is at the same temperature that we call it as the root or base temperature? Anyone, please write in the comment section. How we can attain this particular condition that the entire surface is at the root or base temperature? Because this is, you are having less than a month for the GATE examination, I think. Very good, Malish. You can only achieve this when your thermal conductivity is tending to infinity. Exactly. You can achieve this condition when the fin is having infinite thermal conductivity. Okay. So now let us take an assume one condition. We are having a fin which is having K tending to infinity. So heat will be lost from the entire surface. Heat will be lost from this entire surface. I'm taking an infinite long fin, so I won't be taking the tip. Okay. So now I can say H into the entire surface will be, what will be the entire surface? We can say this is pi into, or we can say P into the perimeter P into L, right, into T0 minus T infinity. Can I write it like this? P into L is entire the perimeter into length, that is the total surface area. Okay. So if I try to take the ratio of this Q actual by Q maximum, so what we are getting, T0 get cancelled out. So ultimately what we are getting is 1 upon M into L. 1 upon M into L. Very important, very interesting. That means I can say that the efficiency of the fin is inversely proportional to M. Okay. And what is M? M is equal to PH by K into A. So from here, can we say efficiency of the fin is inversely proportional to root H, directly proportional to K. Very important. So from this, what we can infer that a fin, if I'm having two different fins, okay, same length, same ambient condition, one is having a larger thermal conductivity, second is having a lower thermal conductivity, which will be having a larger efficiency? The fin which is having a higher thermal conductivity will be having higher efficiency. Is this clear? Fine. Many times question is being asked like this. We are having one fin, okay, and we are having another fin, right? And it is being seen that both are having the same H value, okay. Fine. Efficiency is given. Let's say the efficiency of fin number 1 is, let us suppose, 80%, and fin number 2 is, let's say, 60%. They're asking what is the ratio of K1 and K2? What is the ratio of thermal conductivity of 1 and 2? You can easily calculate now. Rest all parameters are same dimension, same configuration, same ambient condition, that means same H. Okay, so by this way, now you can calculate what is the relation between K1 and K2. Fine. This is one set of question that is being repeatedly asked in the examination. Second set of question that you can expect is, let us suppose I'm having a fin which is made up of, let us suppose, aluminium, and having second fin which is made up of copper. Okay, both are connected with a same material, same root base which is having temperature T0. They are saying that at a distance x1 the temperature is T, and at a distance x2 the temperature is T only. So what is the relation between x1 and x2? Consider an infinitely long fin. Consider infinitely long fin, same configuration. So can we solve this kind of situation, this kind of problem? Very easy. For aluminium fin, we can say T minus T infinity upon T0 minus T infinity is equal to e to the power minus m1 into we can say x1. And for the second fin, it is T minus T infinity upon T0 minus T infinity is equal to e to the power minus m2 into x2. So from this two, we can say LHS is same. We can simply say m1 x1 is equal to m2 x2. And can you tell me why I have deliberately kept, why we have deliberately kept x2 more than that of x1? Can you tell anyone in the comment section? Why we have deliberately kept the value of x2 more than that of x1? Is there a specific reason, or just we have kept it like this only? Anyone? Why I have kept x2 more than that of x1? Perfect, Sujesh. The reason being, we know that the thermal conductivity of the copper is more than that of aluminium, and that is the reason we will be getting, let us suppose if I say this is 300 degrees Celsius, this is, let us suppose 100 degrees Celsius, so same 100 degrees Celsius will be obtained a bit more length. You will be obtaining the 100 degrees Celsius at bit more length. Is this clear? Because the thermal conductivity of the copper is more than that of aluminium. Okay, one set of question expected in your GATE examination. Very easy, direct formula based. Okay, fine. So now what we were discussing about infantile long fin, and we have calculated the efficiency of the fin. So we can take the second case. We can take the second case over here. Let me use this slide. Second case for fin is finite and insulated tip. So fin efficiency is equal to Q actual by Q maximum. So here you can say this will be equal to tan HML divided by M into L. This is the formulation for the efficiency of the fin for a finite length insulated tip. For an uninsulated tip, it will be coming out to be same formulation. Instead of L, it will be LC. Instead of L, it will be LC. This is for case number 3. Okay, this is for case number 3. Fine. This is one parameter that we are discussing, the characteristic parameter for a fin, that is efficiency. But very important parameter that we need to discuss right now is effectiveness. Effectiveness of the fin. That means the heat transfer that we are using by taking a fin divided by the rate of heat transfer if we are not at all using a fin. This parameter will be telling us about whether it is required to install a fin in that particular system. If I say this effectiveness value is coming out to be less than 1, is this a good sign to install a fin in that particular scenario? Anyone? If this effectiveness value, if it is coming out to be less than 1, is this advisable to use a fin in that particular system? Yes or no? Definitely no, sir. If I try to install a fin, if this is, let us suppose it is equal to 0.5. So that means heat transfer with fin equal to 0.5 times of without fin. That means after installing the fin, the rate of heat transfer instead of increasing, it is decreasing. And that is not our objective. We are using the fin in order to increase the rate of heat transfer, right? So this particular parameter will be helping us out to identify whether fin needs to be installed in that particular system or not. So let us calculate this particular effectiveness one by one. Let us take case number 1 only, infinite long fin. Infinite long fin. Okay. Let us take one example. Let us suppose this is a cross section. We can say this is a fin which we are using. Okay. So here we can say Q actual will be equal to under root of PHKA into T0 minus T infinity. Right. Now, if we are not using a fin, we will be having a scenario something like this. So I need to calculate what is the rate of heat loss from this surface. This is your heat loss without fin. Because in that cross section only I'm using an extended surface. If I'm not using an extended surface, I'll be getting a blank surface like this. So I need to calculate what is the value of this heat transfer without fin. So can we say this will be equal to, this will be, now what is this area? Anyone? What is this small area? Can we say this is the same area that we have taken, that is a cross section area? This is the cross section area. So we can say that heat transfer without fin is equal to H into the cross sectional area into T0 minus T infinity. Simple. Simple, very easy to understand. Is this clear? Fine. So now we can say that now if we take the ratio, effectiveness is equal to Q actual by Q without fin. Right? So it is coming out to be, this get cancelled out. So this will be coming out to be 1 upon under root of H cross section area P into K. This is your effectiveness. Very, very important conclusion we are coming. We are coming to a very important conclusion. That is your effectiveness is equal to 1 upon H into cross sectional area by P into K. Effectiveness inversely proportional to root H. Effectiveness inversely proportional to cross sectional area. Effectiveness directly proportional to root K. So we can have some conclusive statement over here. One conclusive statement is we will be always be using a fin where the convective heat transfer coefficient is low. Okay, so if anyone is asking you a question, if there are two situations, one is a forced convection, second is a free convection, where you will be installing a fin, forced convection or free convection. Let's see, we'll be giving the answer. Who will be, where you will be installing a fin? Forced convection case or free convection case? They're very easy. Free convection or a forced convection. देखो, forced convection H value is more or free convection H value is more? My question is, we know that the forced convection is having a very, very higher than that value of free convection. That is the reason majority of the cases, we will be installing a fins where we are having or where we are dealing with a free convection. Okay, fine. So if H value is low, that is actually good for the system. Okay. Second important conclusion, that cross section area should be less. That means we should always be taking a thin fin. Low H, thin fin, low H, high K. Thin fin, low H and high K. These are three very important distinct feature of using any fin. And one more is closely packed. Closely packed. Why closely packed? Let us take one example. Let us suppose I'm having a base, a root or base, whatever we call it as, right? Let me take a 2D view. I'm having a base or root. Okay, I'm installing fin like this. This is case number one. Second case is I'm using this much red number of fins. So which will be more advisable? Previously in the same cross section, we were using only 3 fins. Now I'm using 1, 2, 3, 4, 5, 6 number of fins. So definitely more number of fins will be increasing the more extended surfaces or more area will be exposed. That means your rate of heat transfer will be increasing. And that is the reason we always take that the fins should be first low value of H, high value of K, thin cross section, and fourth one is closely packed. so that you can accommodate more number of fin. So that you can accommodate more number of fin. Okay, fine. And if you remember, when we were starting the fins, I told you in 5 minutes I'll be telling you why we are taking this H value to be low. Remember? Now I think that statement is being justified. And that is the reason, if you consider the heat transfer through tip also, that will be very, very negligible. Okay, so if in the examination, if they're going to ask you what is the heat transfer through fin, okay, by default take it for the heat transfer for an insulated tip. If nothing is mentioned, then you have to take the insulated tip. Okay, if they're specifically mentioning that calculate for an uninsulated tip, then you have to calculate. But 99% of the time, if they are not mentioning, right, or 100% of the time if they are not mentioning, then you have to by default take it as insulated tip only, provided they are giving the length. If length is also not given, then you have to take it infinitely long. There's a technique, if they're using a word as long, if they're using a word as long fin, then understand that they're talking about this case. If they're using this word as long fin or very long fin, understand that they're basically talking about this case. Okay, so if I try to have a quick recap of fins topic in a one go, what we have discussed right now is, for case number 1, the temperature profile we have seen as T minus T infinity upon T0 minus infinity is equal to e to the power minus mx. What is the heat transfer through fin? Under root of PHKA. You can write as under root of PHK cross section area T0 minus T infinity. Okay. Efficiency of the fin is 1 upon ml. Effectiveness of the fin is under root of 1 upon under root of HA by P into K. Fine. If I talk about case number 2, what we have seen that T minus T infinity is T0 minus infinity is equal to cos hyperbolic ml minus x upon cos hyperbolic m into L. Let's take in this bracket. Okay, fine. If I talk about the heat transfer through fin, root of PHK cross section area T0 minus T infinity into tan hyperbolic m into L. Fine. And if I talk about the fin efficiency, root tan H hyperbolic ml, and if I talk about the effectiveness, that will be equal to tan hyperbolic m into L divided by under root of HA by PK. Okay, for case number 3, just only you have to write is, instead of L, it will be corrected length, that is this. Okay, understood? Fine. Okay, now in fins, we can have a situation like this also. Like we can have one relation between the effectiveness and efficiency of the fin. Can we have a relation? Let's check. We know that what is efficiency of the fin? That is equal to 1 upon m into L. What is effectiveness? That is equal to 1 upon under root of HA by PK. Right? If you take this ratio, efficiency by effectiveness, this is equal to 1 upon under root of PH by KA into L into, this will be going in the numerator. Okay, so we can simply say this is equal to under root of HA by PK. So H get cancelled out, K get cancelled out. So ultimately what we are having is efficiency by effectiveness is equal to your cross-sectional area, this is A, cross-sectional area divided by P into L. Okay, or we can say that efficiency by effectiveness is equal to cross-sectional area upon, what is P into L? What is perimeter into length? If I say, if you're having a circular fin, if I say this is your perimeter into length, what will be that? In terms of area, tell me, what is perimeter into length? If I say this is the cross-sectional perimeter into length, that will be surface area, right? So I can simply say now, very interesting thing, your efficiency by effectiveness is equal to the ratio of cross sectional area divided by the surface area. Is this clear? So in the examination, if they're going to ask you some questions related to directly by giving some values of they're giving efficiency and they're giving some cross section, right? You can directly calculate what is the effectiveness. Directly you can use this relation to get the formulation between efficiency and effectiveness. Okay. Right? Perfect. Now after this, there is an interesting segment that we need to have a discussion where we'll be using the concept of fin. What is the heat loss when a bar is connected with two heat sources? What will be the heat loss when a bar is connected from two heat sources? Something like this. Let's say this is source 1, this is source 2. What is the heat loss, or what is the temperature profile? What is the temperature profile that we need to have a clarity? Okay, fine. So if I say, let us take one example, we can have a different possibilities. Let us suppose we're having a same source, like this is TS1, or let's say this is TS and this is also TS. I'm having the same source kept at both the end. We can have one equal also. Let us take one criteria when two source which is at the same temperature kept at the extreme ends of the bar. Then can you tell me what kind of temperature profile you will be expecting? If I try to forget about this TS, this right hand side, can I say this is nothing but a concept of fin only? Right? If I try to visualize that, let us suppose this is your TS. Okay, fine. If you forget about this, this is our same condition that we have already studied in case of fin, and it is having an exponentially decreasing temperature like this. Yes. And let us forget about this, as they are at the same temperature, same height we will be having. Okay, same height. Fine. So if I try to forget about the left hand side, if I try to see, this is a root, this is a fin, so we'll be having a same kind of heat loss. Okay, so can you see, if I try to club and if I try to plot the temperature profile, we'll be getting a temperature profile. Something like this. And at this point, what is happening? You are getting the minimum temperature. At this point, I'm getting, and this is exactly the center point, because this is the same, we can say, sources. So we'll be getting this mean temperature exactly at the midpoint. Yes, we'll be getting the mean temperature exactly at the midpoint. Now, if the temperature is minimum, what is the rate of change of temperature with respect to length? Yes, this is the combined effect of the two temperature profile. Can you tell me what is the value of del T by del X at this point? Anyone? The rate of change of temperature with respect to X. I'm taking this as X. Sir, 0. Because this is the minimum temperature, so definitely this will be equal to 0. Or can we say, if I try to eliminate this, and I'm assuming that if I say this is having a length of L in between, right? So can we say I'm having a fin, right, having a length of L by 2, and whose tip is insulated, because when the tip is insulated, what will happen? There is no heat convection. So we can say at tip Q conduction is equal to Q convection is equal to 0, or we can say del T by del X equal to 0. This is the condition for a tip condition, right? So can we say, if I try to forget about this particular condition, if I try to convert this into a fin system having a length of L by 2, so can we say the heat transfer, whatever analysis that we have done for an insulated tip, same we can do for half the length. Is this clear? Same we can do for half the length. If I say, let us suppose I'm having a condition, we're having same heat sources, and they're saying what is the temperature at the midpoint. Okay, they're asking you what is the temperature at the midpoint, and they're saying that there is one more we can say rod, right, whose base is kept at the same temperature, whose length is half of this length. It's kept at this temperature, and the temperature, let us suppose 50 degree. Then what is the value at the midpoint of this bar? Can you tell me? There are two rods. One rod is having a length of L, and it is kept at both the sides. We're having the same source of heat. And there's one more rod which is having a length of L by 2. Okay, having the source temperature same as that of this one. And they're saying the temperature at the end of this rod is 50 degree. So can you tell me what is the temperature at the midpoint of this bar? Simple, sir. Simple logic. It's very easy. We have seen that when I try to had the analysis, I'm getting the minimum temperature exact the midpoint, right? If it is exactly the midpoint, can we simply say that it is nothing but an equivalent system of this? So if this is having the temperature of 50, this will also be having a temperature of 50 degrees Celsius. Simply the replica of that. Simply the replica of that. Clear? Okay. Simply the replica of that. Okay. Now let us suppose second one, this one insulated. This is given. This is insulated. The temperature at the insulated tip is 50 degree. The temperature at the insulated tip is 50 degree. This is given a second bar. Okay. Because then only we can have a correlation. Then only we can compare. If this is not insulated, then how we can compare this and this condition? Right? This is an insulated tip. That's the reason we are able to compare this particular case with this particular condition. Okay. Clear? Fine. Expected question that is you can expect from this particular topic. Okay. Now there's one more segment in the fins that we call it as the corrected length or proper length. Corrected, not corrected length, it's a proper length. What is the concept of this proper length of the fin? If I take the ratio of we can say finite length to infinite length, what will be this? I'm taking, let us suppose, insulated tip. All the parameters are same. Only distinguished parameter is tan hyperbolic m into L. Right? Tan hyperbolic m into L. So if I say, let us suppose, if this tan hyperbolic m into L is coming out to be 1, can we say at that moment the finite length will be behaving as an infinite length? If I say tan hyperbolic m into L is having a value of equal to 1, can we simply say that at that moment our finite length will be behaving like an infinite length? Okay, fine. So for that, let's take one table which will be taking as a reference for values. What I have said that this is m into L value and corresponding tan mh value. I've taken a table where we're having ml and corresponding tan mh value. It is being observed that when ml value is equal to 5, at that moment it is equal to 1. Okay, so if I say I'm having a fin, okay, this is your finite length, okay, and we are having this as an infinite length. Okay, infinite length, there's no ending point. Fine. And this finite length is having a length of approximately, it is having ml equal to 1. Now in this case, what has happened that the temperature will be decreasing and almost it is equal to T infinity, because that is the condition for infinite long fin. Okay, but if you try to visualize, when I'm having ml equal to 1, because m is the factor which is depending on the configuration and the ambient condition, only distinguished factor is this length. That means if you increase or decrease the length, then only we can vary this value. Okay, fine. So now if you say when ml is equal to 1, we are having 0.76. That means your heat transfer when ml equal to 1, your heat transfer for finite length is approximately equal to we can say 76% of the infinite. Okay, if you try to double this value, that means if you are increasing the length by 2 times, it is going from 76 to 96. So is it a better solution that in order to double the length of the fin, because the fin is made up of a metal, okay, it will be definitely costing you some value. It is not economic perspective, it's not a wise decision to go for a twice the length and only to increase how much? 20%. Only to increase how much heat transfer? 20%. So it is being observed that in order to have economic point of view, the heat transfer, we always keep near about to 1. Okay, if you want, you can go till 1.5, but not beyond that, because beyond that, your heat transfer increment rate is very less. Length increment rate is very high. Okay, if you try to see, when you are going from 1 to 2, your heat transfer is percentage going from 76% to 96. But when you are going from 1 to 5, 5 times increased length, you are increasing the heat transfer from 76% to 100%. So it's not a wise decision, because one is your, let us suppose 10 mm, second is your 50 mm. So definitely increasing a larger size of fin won't be giving you a wise or economic solution, because more the length, more will be cost, and definitely the weight of that particular system will be increasing. Okay, we try to reduce the weight as less as possible, and that is the reason you might have seen that the length of the fin is not that high, right? So that it is not being, it is very difficult to, we can say, maintain and manage that kind of fins. Okay, so we always try to achieve near about to 1 value, and this is, we call it as the proper length of the fin. Okay, if you want to have 100% heat transfer, then you can opt for ml equal to 5, because when ml equal to 5, tan HML is equal to 1, and this will be your situation. Okay, fine. So proper length of the fin is, you should be knowing, at least from your MSQ perspective, you can get a question from this. Okay, a simple direct of concept based problem. So now this completes your fin topic. Okay, so now let's begin our transient heat condition. Okay, shall we begin? Transient heat. Yes. Okay, so let's start having the discussion of transient heat. What's the meaning of this word transient? Anyone? Till this point of time, you have covered the conduction topic, and you have seen that your temperature was not varying with respect to time. Till this point of time, the temperature variation with respect to time was not happening. We were only taking a steady state condition. But now, as we can see, there's a hot cup of coffee, right? Black coffee, I think, right? And definitely with the time, this coffee will be decreased. The temperature of this coffee will be decreasing. Okay, so now we can say the temperature will be now a function of time, and this is, we call it as the unsteady state or transient state. Unsteady state or transient state. Now we can say that the temperature will also be changing with respect to time. So this is a very important discussion, because this is a case that we are discussing, which we are actually dealing in a real life scenario. It's not like this. If you're having a cup of tea, you say that this is steady condition, please tea, do not change your temperature. It's a practical, it's a realistic condition that the temperature is going to decrease. Okay, we'll be having some loss of heat from the surface of the coffee to the surrounding. Okay, in form of conduction, in form of convection, in form of radiation. Okay, so we need to have a clarity what will happen if I try to introduce the concept of unsteadiness in our system, because till this point of time you were only discussing about the steady state condition, right? So now let's talk about a transient heat condition. Now transient heat means the temperature will be a function of time. Okay, so let us suppose I'm having a body, right? Initially, let us suppose at time t equal to 0, it was having a temperature of Ti. Okay, fine. Ti is the initial temperature, having some mass m, density rho, Cp, K, right? All the values. Fine. Volume V. Okay. So at any point of time, let's say at any instant of time, at any instant of time t, let us suppose the temperature is T. That means let us suppose we are having a rod, we are increasing the temperature of the rod inside a furnace. Let us suppose this temperature reached till 2000 degrees Celsius, and I'm making this rod outside the furnace. So definitely at time t equal to 0, it will be having 2000 degrees Celsius, and with the time it will be losing the heat. So let us suppose after some point of time it is having a temperature of T. At that moment, if I try to apply the energy balance, can we say the rate of convection heat transfer from the body will be exactly equal to the rate of decrease of internal energy with respect to time? Yes. Can I say whatever heat is being lost from the body, same amount of heat, same amount of energy decrease will be happening with respect to time at that particular moment? This is only I'm talking about at a particular instant. Okay, so from here, if I try to have a clarity, I can say that del T by 1 upon T minus T infinity is equal to minus, this is, we can say, this will be giving HA into T divided by rho V Cp. Okay, instead of mass, we can say density into rho into V. Okay, fine. So this is small t. So integrating both sides, now we are getting a very interesting formulation that T minus T infinity upon T initial minus T infinity is equal to e to the power minus HA by rho V Cp into T. Now you can see that our temperature is varying in a negative exponential way. Negative exponential way, the temperature decreasing or increasing, it is happening. So if I try to plot a graph, let's say, let me draw it over here. Let's say I'm taking a cooling of a body. Cooling of a body, right? So if I say cooling of a body, initially it will be having a very high temperature. So let us suppose it is having a temperature of T naught or Ti, and with the time it will be decreasing exponentially, right? And this T infinity is the ambient temperature, because the body will be cooling till the last limiting value will be the surrounding temperature. If I say this rod is being heated till 1000 degrees Celsius and ambient temperature is 30 degree, so this body will be going till 30 degree. It won't be going beyond 30, right? So here we can see that, here we can clearly see that the rate at which this is decreasing. Can you visualize what is this? This is del T by del small t. What is the meaning of this? The rate of change of temperature with respect to time. Can you see? Initially it is having a larger slope. After some point of the slope is decreasing. What is the meaning of that? What is the meaning of that? That initially the temperature drop is more and after that temperature drop is less. Do you have a visualization? Let us suppose you are having a cup of tea. In the starting 1 minute, the drop in temperature will be very fast. And after, let us say, half an hour, the drop in temperature will be very low. Understood? So can we say the rate of cooling, this is nothing but the rate of cooling. And definitely this will be a negative because it is going in a negative way. So this is minus sign. So rate of cooling in this case initially will be very fast, but after some point of time it will be slowly decreasing. Is this clear? Initially the drop in temperature per second will be very high, but after some point of time the drop in temperature per unit time will be very, very less. Okay, if you're having a cup of tea, in the starting 1 second the drop in temperature, let us suppose, is 50 degrees Celsius. After 1 hour, the drop in temperature in 1 second is only 1 degree Celsius. Are you able to visualize what is happening? That is, we call it as rate of cooling. Fine. This is I'm talking about for a cooling of a body. The same situation we can understand for a heating of a body. Heating of a body, right? That means if I say initially it was having a low temperature and starting with temperature increment will be very quick, and after that it will be reaching a very low value. Okay, this is your temperature, this is your time. So if you see over here also, the rate of heating is high in the starting case and it is slowly decreasing. So del T by del T over here represents the rate of heating. And both way we are talking about an exponential distribution, and we have proved that this is an exponential distribution, right? If we can say, instead of using negative exponential, we can say simply an exponential temperature distribution. Okay, we are having an exponential temperature variation or distribution with respect to time. So from here, we can say the cooling of a body and heating of a body very easily. Now, there's one very, very important thing you have to please make sure whenever you are getting, and usually if you are getting a question from this topic, it will surely carries a weight of 2 marks. It will surely be carrying a weightage of 2 marks. So if I say T minus T infinity upon T initial minus T infinity is equal to e to the power minus HA by rho V Cp into T, right? Fine, where T is the temperature at any instant, any time T. Okay, T infinity is the ambient temperature of fluid. Ti is the initial temperature of the body, right? And anything else? Very important thing that you have to always keep in mind, maximum number of time this Cp value, that is specific heat, right? They are giving in kilojoules. And if they are giving in kilojoules, make sure you are converting into joule. Very important point. There are two things you have to observe, that they might give you this in kilojoule. You have to convert into joule. Second thing is, they should be in joule per kg Kelvin. Okay. Second thing is, the T value that you are seeing, that should always be in hours. They will be giving you in minutes or even in seconds. Make sure you are converting this in hour. Oh, sorry, second, not hour, second. Opposite bol diya. Always remember that the SI unit of the time is seconds. So always remember that you have to make sure that you are using the unit of time as seconds, not hours. They'll be giving you after 1 hour what is the temperature of the body. So make sure you are converting this into seconds. Okay, make sure you're converting this into seconds. If you're not converting, then your answer will be wrong. And the wrong answer, guaranteed I can say, it will be available in the option. Whatever wrong calculation you are doing, that same wrong value will also be available in the option. And that is the best part of GATE examination. Okay, fine. Is this clear? Okay, now tell me one thing. What will be the unit of HA by rho V Cp? Anyone? What will be the unit of this HA by rho V Cp? By looking at this expression, you can tell me quickly. Yes. What will be unit of this HA by rho V Cp? Anyone? Array. This is seconds. This will be per second. Hai per second. This will be per seconds. Right? So can we say that T initial, T minus T infinity upon T initial minus T infinity is equal to e to the power minus T. I am now introducing a very important term, that is tau. And what is this tau? Tau we call it as time constant. That is, we call it as rho V Cp upon H into A. Rho V Cp upon H into A. What is the significance of this tau? Definitely this tau will be having a unit of seconds. What is the significance of this tau? Let us take an example of a very interesting term. We call it as thermocouple. Have you heard about this term? Thermocouple. What is a thermocouple? Thermocouple you might have used in different experimentations to calculate the temperature of a fluid. Okay, if I say there is a pipe, if I want to measure what is the temperature of the fluid which is moving, so what we'll be doing, we'll be using a thermocouple, right? And it will be having a digital meter. It will be showing us the temperature over here. So this is your thermocouple, and this is, we call it as the bead of a thermocouple. So what is this time constant is coming into the picture? It is being seen that, let us suppose I'm having a condition. This thermocouple is having a very high value of time constant. Okay, if it is having a very high value of time constant, then what will happen? Let us suppose the fluid is moving. The fluid is moving inside the pipe. Initially it was at 100 degrees Celsius, and after 1 minute the temperature of the fluid moving is 50 degrees Celsius. As the time constant value was high, it is taking more time to analyze, to adjust that, okay, it is 100 degrees Celsius, slowly it will be analyzing and will be showing 100 degree after some point of time. And at that instant, already 50 degrees Celsius fluid is moving. So definitely in that case, there is a huge error in the measurement, because initially when it was 100 degrees Celsius, it is not responding quickly because its time constant is having a higher value. So in order to have a quick response, right, we always prefer a low time constant. MSQ problem you can expect. You can expect an MSQ problem. If you want to have a quick response, we always prefer a low time constant. That means your tau value, that is your rho into rho V Cp upon H into A, this should be having a low value. This should be having a low value. That means, and how we can get the low value? By we can say we can have a we can say having a low time constant HA by rho V Cp. हाँ ठीक है. Yes, understood. Okay, so now in this case, if I want to have this a low value, we always prefer a high value of H. We always prefer high value of H, and we always prefer V by A to be low value. What is the meaning of V by A? That means the size should be small, not small, very small. If I want to have this V by A to be having a low value, I want this size to be very small, and that is the reason you might have observed that the size of the thermocouple is very, very low, very, very small, because its V by A value should be very, very less. And that is the reason, if it is not having a less size, then it won't be having a low time constant. If it is not having low time constant, it won't be responding quicker. It is being seen that you might have seen thermometer that we are using to measure the body temperature. It is having a value of approximately 70 to 80 or 85 seconds. 70 to 80 seconds is the value of time constant. That is the reason you might have seen that when you are measuring the body temperature by using thermometer, at least you are keeping the thermometer for a minute. Yes, so that it is taking some time to measure the temperature accurately. If I take a thermometer and keep it for only 5 seconds, and if I try to remove it, you won't be getting the correct time, because its time constant is having a range of approximately 60 to 80 seconds, near about that value. Is this clear? Understood the meaning of time constant? Right? So in order to have a quick response, we always try to keep the time constant value as low as possible. Is this clear? Okay, if I said 60 seconds means it will be taking 60 seconds to get that optimum value. Okay, fine. If I take 2 seconds as a time constant, that means it will be taking 2 seconds to measure that temperature. That is very quick. So we always try to keep the time constant value as low as possible in order to measure or in order to have a quick response to the temperature variations. Is this clear? Fine. Now, one assumption we have assumed without even discussing. Try to understand that we are discussing, let's say this is a body. Fine. We are saying that at time t, the temperature of the body is T. Is that so that the entire surface is having the same temperature? We can have a possibility that this side is temperature having T1, this is T2. We can have a different temperature. That means the temperature can be a function of space. Yes, we can have that kind of situation. But while deriving this expression, we have not taken that particular possibility. We have taken, if I say after 10 minutes, the temperature of this body is 10 degrees Celsius. That means the 10 degree will be at any point. If you take at this point also, if I take at this point also. But that assumption I have not assumed while deriving. Okay, so now you have to understand that one thing that we are understanding, while we are doing this analysis, we are taking one assumption that the temperature is not a function of space. That means throughout the body, the temperature any instant of time, it will be same. That means at t equal to 20 seconds, the temperature here will be same. T equal to 1 minute, the temperature will be at every point will be same. That is the assumption that we are using. And what do we call this type of body whose temperature is not a function of space? This type of body, we call it as lumped body. Okay, and the expression that we have used, which one? T minus T infinity upon T initial minus T infinity is equal to e to the power minus HA by rho V Cp into T is only applicable to a lumped body. It is only applicable to a lumped body. Let me use L like this. Okay. If there is a non-lumped body, then you cannot apply this expression. And in our syllabus, we are having only lumped body analysis. So the next question coming to the mind is how we can identify whether the body is a lumped body or not. What is the criteria to identify lumped body? What is the criteria to identify the lumped body? That we need to have a clarity. Yes. So for that, there is a very, very interesting number. Can you tell me in the comment section? What is that number called, which is basically helping us to identify the lumped body? Anyone? Exactly. Very good, Malesh. That is, we call it as a Biot number, denoted as BI, and that is equal to HLC by K of the solid. HLC by K of the body or of the solid. Okay. Sir, okay, fine. You have understood that, but how we can still understand that this body would be lumped body? There might be some value, that should be some range which you need to have a clarity. It is being observed that when Biot number is less than 0.1 or less than equal to 0.1, we can say this body will be a lumped body. Okay. You have given one range for that. That is also okay. But how we can say this body will be a lumped body? Just only by remembering this number, or do we have any concept? Let us try to understand what's the concept behind this. Can I write this Biot number like this? We can say LC by K into A divided by 1 upon H into A. What is LC by KA? What do we call this particular term? Length by thermal conductivity of the solid by area. This is nothing but your conductive resistance. Yes, This is nothing but your conductive resistance on the, we can say, the internal conductive resistance, and 1 upon HA is the external or the surface convective resistance. So we can now define that the Biot number is equal to the ratio of conductive divided by the convective resistance. Still, sir, not able to understand how we can achieve the same temperature throughout. Okay, let us suppose I'm having a body. Biot number is equal to the internal conductive resistance, internal conductive resistance to the external or surface convective resistance. Yes. Okay. So Biot number less than 0.1 means the Biot number is having a very low value. Yes, Biot number is having a very low value. Okay. Ideally, if I say, if the body is having entirely the same temperature, when this kind of situation you can get, when you can get this kind of situation, when the entire surface of the body is at the same temperature, remember the concept of fin. In fin also we have used that concept. When K will be tending to infinity, then only we can say that the entire surface is at the same temperature. Okay, so when K is tending to infinity, what's the conductive resistance? When K is tending to infinity, what is the value of conductive resistance? It will be tending to 0, right? That means your Biot number is tending to 0. That means it's an ideal situation. Okay, ideally the Biot number should be 0, right? But it is not practically feasible that you will be getting an ideal Biot number to be 0 or K value to be infinity. So we are taking all the possibilities. We are taking, okay, if you are having slight variation along the surface, it's perfect. So that is the reason we are taking the Biot number to be a low value, because if Biot number is having a low value, we can simply say the conductive resistance is far lesser than that of the convective resistance. And if this is happening, that means your body will be considered as a lumped body. The body will be considered as a lumped body. Is this clear? The body will be considered as a lumped body. Understood? Okay. Clear? So now if I rewrite our expression, and this is now, you can say this is only applicable to the lumped body. T minus T infinity upon T initial minus T infinity is equal to e to the power minus HA by rho VCP into T. One thing that I have skipped out is, what is this LC? LC, we call it as the characteristic length. LC, we call it as a characteristic length. And what is this LC value? That is equal to the volume of the body divided by the surface area. Volume divided by surface area will be representing about the characteristic length. Okay, volume divided by surface area, that will be giving us the information about the characteristic length. So now if I try to rewrite this expression, E is equal to minus H by rho LC into Cp into T. Fine. So we can say this is equal to minus HLC by K into, we can say alpha T by LC square. What is alpha? Alpha is your thermal diffusivity. Alpha is thermal diffusivity, right? So now I can represent, this is your Biot number. This is one more number that we need to understand. This is your Biot number and this is your Fourier number. Okay. So now I can say that our expression has been introduced in a very interesting term, T minus T infinity upon T initial minus T infinity e to the power minus Biot number into Fourier number. Okay, so we can have this kind of expression also in our discussion. Now the next question coming to the mind is, sir, what is this Fourier number? This FO basically means that is a Fourier number. Fourier number. Okay, which is equal to alpha T by LC square. What is the where alpha is thermal diffusivity, that is K by rho Cp. Alpha is thermal. I hope so. You have already this one. It's very easy. Just we have just placed try to multiply LC on numerator and denominator. Okay, fine. Is this clear? Yes. Anyone having any doubt over this? It is K by rho Cp, right? I have multiplied LC in the numerator because it is LC in the this one. Okay, so what I've did, I multiplied divide HLC by K. Now okay, HLC by K. Multiply divide by LC. If I'm still having confusion, look, HA by rho V Cp into T. I can rewrite this as H by rho into LC into Cp into T. This is equal to H into LC by K into I've multiplied K by LC square into T divided by rho Cp. Yes? Can I write it like this? Multiply divide by LC, multiply divide by K. So what is this? HLC by K, Biot number. What is this? K by rho Cp, alpha T by LC square. The same thing I've written over there also. Okay. And what is this alpha T by LC square? That is your Fourier number. Okay. Is this clear now? Yes. Fine. The same thing I've written over here. Okay, so now the question rises is, what is this significance of this Fourier number? If you try to have a clarity, let us suppose I'm having a rod. Okay, I'm keeping a lighter for 1 second. I'm keeping the lighter for 1 minute. In which case the penetration of heat will be more? When I'm keeping the lighter for 1 second or 1 minute? In which case the penetration of heat will be more? Definitely, sir, if you increase the time, there the penetration of heat will be more, and the Fourier number basically tells us about that only. It tells us about the degree of penetration of heat. Fourier number basically, which is equal to alpha T by LC square, it basically tells us about the degree of penetration of heat. If you are having a more value of Fourier number, that means heat will be going into the body, it will be penetrating into the body to a more value. Okay, fine. If I say Fourier number is having a larger value, that simply means that the degree of penetration of heat inside the body will be more. And that is the significance of this Fourier number, very important. This was asked in ESC multiple number of times, so you can expect gate may, because now if you see MSQ question, they could very rare possibility that they'll be asking you numerical from MSQ. MSQ is basically a gateway to all the theoretical segment in all the chapters on all the subject. Earlier they were not able to ask, gate examination were not able to ask the theoretical portion, right? But due to the introduction of this MSQs, now they can ask you any question from any topic, at least a theory part or at least a conceptual theory part. So for that you should be having a complete knowledge of the subject. Okay, fine. Chalo. So now we have seen that our expression is now reduced to a very simpler format, that is minus Biot number into Fourier number. Okay, clear? Fine. So now if I say, if let us suppose if Biot number, if it is more than that of 0.1, then what will happen? If Biot number, if it is more than that of 0.1, then what will happen? In this case, this is not a lumped body, non-lumped body. This is a non-lumped body analysis. And whenever I'm dealing with a non-lumped body, what we will be using? Anyone who can have a, exactly. So in a non-lumped body, how we can do the analysis? For lumped body, we have seen the expression. T minus T infinity upon T initial minus T infinity is equal to e to the power minus HA by rho V Cp. We will be using an Hessler chart. Hessler chart. That means there is a chart from which I can easily able to calculate the magnitude of the temperature for a slab, for a sphere, for a cylinder. I will show you a sample graph, something like this. What is basically happening here? We're having a temperature ratios. On the x-axis, we are having the Fourier number, or in this way, we are having 1 upon Biot number. A question was asked again from ESE that on the x-axis, which parameter or which dimensionless number is present. So now we can simply say that a normal Heisler chart, this is a Heisler chart. Okay, a normal Heisler chart will be comprising of the temperature profiles, and on the x-axis we are having Fourier number, and inside the graph we'll be having 1 upon Biot number. Okay, these values that they have written, this is basically for 1 upon Biot number. Okay, so it is different for slab, different for sphere, and different for your cylinder. And for center line, we're having different graph. For a particular distance, we'll be having different graph, right? So it's very difficult to do the analysis. For that, they have to give the chart. So that is the reason in examination, numerical perspective, you never ever get a question from this. But yes, you should be knowing how an Heisler chart basically looks like. Okay. Fine. So that is the reason I showed this particular graph, which is taken from the standard textbooks. Okay. Clear? Fine. If you are having a non-lumped body, then we have to use this chart over here. Okay. Is this clear? Fine. So now we are entering into the last segment from my side. Then Chandra sir will be joining with the heat exchanger part, very, very important. Convection part, very, very important. Okay. So now we are starting a very important topic, radiation heat transfer. Okay. Yes. Radiation heat transfer. I think by 5:30 I'll be making you free, or 5 o'clock I'll be making you free from this radiation. Then Chandra sir can join around 5 o'clock. Okay. Okay, fine. So now let's talk about the radiation process. Now let us talk about the radiation process. Now what is radiation? Anyone? Malay, Sujesh, Surinder, Baumek, what is the meaning of this word radiation? So it's a mode of heat transfer where the heat is propagating in form of electromagnetic wave. And if the energy or heat is propagating in form of electromagnetic wave, that means it does not require any medium. We know that electromagnetic waves does not require any medium for propagation. So we can simply say that radiation, it is that mode of heat transfer in which the propagation is in form of electromagnetic waves. That means no medium is required, and it is being observed that it is a strong function of absolute temperature. It is a strong function of absolute temperature. Now, remember very important thing. In conduction, in convection, we are always discussing about temperature differences. So there it was immaterial to talk about whether we are using degrees Celsius or Kelvin, because temperature difference always have the same value if I go for degrees Celsius or Kelvin. But here I'm talking about the absolute temperature. So make sure you always keep in mind to change the unit of temperature to Kelvin. It's very, very important. Why? Because I think you already studied when Chandra sir was taking the starting modes of heat transfer. He has talked about the Stephen-Boltzmann equation. Yes? Stephen-Boltzmann equation. What is this? This is the governing equation for the radiation. It said that the emission from a black body is directly proportional to the 4th power of the absolute temperature. This will be in watt per meter square. That means if the temperature is having a higher value, the 4th power of the temperature will be giving us the emissions. And that is the reason we need to always convert the temperature unit to Kelvin, because this way I'm talking about the absolute temperature, and we have seen that it is a strong function of absolute temperature. Means if the temperature is more, it will be having high emissions. If the temperature is less, it will be having less emission. If I say this is a high temperature, so we'll be having more emissions from here. This is a low temperature, we'll be having a lesser emissions from here. And this is a vacuum. This is a vacuum. Okay, fine. There is no medium inside. So if you take two plates, which is one at higher temperature, second at the lower temperature, so higher temperature will be having more emissions, the lower temperature will be having a lesser emissions, right? Okay, so now let us try to have a quick discussion. There are some terminologies that we should be having. I hope so you know about that, but I'll be having a quick recap of that particular terminologies. The first one we call it as the hemispherical total MSV power. Total hemispherical MSV power, which we are denoting it as capital E. Now, what is this? Why we are saying this as hemispherical? Because if I say I'm taking up on a surface, I'm taking a surface, right? On a surface, if I take a point, so the emissions will always happen in all the directions in 3D. If I say I take a point, if I take this point over here, the emissions will be happening in all the direction, right? And it will be forming a hemispherical shape like this. Okay, so always remember that whenever we are talking about emissions, if I take a point, the emissions will be happening in all the directions. Okay, and that is the reason we are calling it as total hemispherical MSV power, which we do it as, which we are having a unit of watt per meter square. Okay, fine. Is this clear? So after this, there is a very interesting term that you should be knowing, that is emissivity. Emissivity, which we do it as epsilon. Emissivity. What is emissivity? Emissivity is the ratio of the total hemispherical MSV power of a non-black body to the total hemispherical MSV power of a black body. So now you should be having a discussion. What is the meaning of this word black body? What is this black body? Black body is having three distinct properties. Black body is having three distinct properties. It is an perfect absorber. It's an ideal emitter. And it's a diffusive surface. What is the meaning of this word individually? Let us try to understand. If I say perfect absorber, that means whatever, if I say this, my hand is black body, so whatever radiation is incident on this surface, it will be absorbing. It will always absorb, right? Fine. Or we can say, if it is having a high absorption capacity, it will be having a high emission capability. Yes. If you are having, let us suppose I'm having a particular body. If I'm taking energy from I'm taking energy from outside, I'm not giving any energy. So definitely, in order to maintain a stability, in order to maintain an equilibrium condition, I need to emit a lot of energy, right? Or else I'll be having an unstable condition. So if I absorb a lot of energy, I have to emit a lot of energy. That is the reason we are calling a black body is a perfect absorber, an ideal emitter. Now talk about diffusive surface. What is the meaning of this word diffusive surface? Now normally the surface we are having is categorized into few segments. What is we call it as spectral surface. Okay, one is your diffusive surface, and third we call it as real surface or real body. What is spectral surface? In this case, if you are having an emission, an incident radiation, you will be having only one reflection like this, just like a mirror. Just like a mirror, you're having one incident and only one direction we're having the emission. In diffusive surface, if I say there is one emission, we can say radiation which is incident on this surface, okay, we will be having emissions. we will be having emissions, and that will be equal in all the direction. The emissions will be equal in all the, this is equal emissions, EB, 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 like this. Okay, let's say, or we can say I, we can say any parameter like I, anyone. Okay, real surfaces is, let us suppose if I say this is the real surface, there is some incident radiation. In this case, we will be having, let's say this is E. In this case, we will be having emissions, but that will be unequal in every direction. E1, E2, E3, E4, E5. Some will be having larger magnitude, some will be having small magnitude, like this. Okay, fine. So spectral means one incident and will be having one emission in one direction only. Diffusive means we'll be having equal emissions in all the direction. Real body means we'll be having emissions but unequal in the different directions. Okay, so now if I try to come back, black body is a diffusive surface, means whatever emission is happening, it will be equal in all, it will be equal in every direction. Okay, if I say this is I units in this direction, it will be I units in this direction also. Okay, fine. So that particular surface, we call it as a black body. So can we have a black body? Can we have an example of a black body? Let us suppose I'm having a big cavity and very small opening. A big cavity, very small opening. So when a radiation is coming inside this cavity, hollow, very small opening cavity, this particular radiation or energy will be trapped inside. It won't be able to go outside. That means whatever radiation is coming, it is absorbing, and this could be considered as an example of a black body. Because black body is having a tendency that whatever energy is incident on the surface, it will be absorbing all the energies. So same thing is happening over here also. Energy is coming inside the body and it is not able to leave that particular cavity. Okay, we can say this is a cavity having small opening. Cavity having a small opening. There we can use this concept of black body. That we can say this is a similarity or analogy from the black body concept. We can take the example of the sun, solar radiation, also the example of a perfect black body. Like the sun, we can take the example of a perfect black body. Okay, fine. Is this clear? So now let us try to understand next point. Now let us suppose if I am having there is a surface at temperature T Kelvin, there is an identical surface at T Kelvin, right? And this is a black body, this is a non-black body. So tell me, which body will be having larger emissions, black body surface or non-black body surface? Both at the same temperature, both are kept at same temperature T Kelvin. So which will be having the larger emissions? Sir, quite obvious, because it's at the same temperature. So we can say this is EB and we can calculate EB. EB is equal to, we can say EB was directly proportional to T to the power 4. If I try to remove this proportionality sign, we can say EB is equal to sigma T to the power 4. And by this relation, we can easily calculate the black body emissions, right? But if I want to calculate, if I say this is E for a non-black body, how we can calculate? There we have seen that emissivity is equal to E by EB. From there, I can calculate E is equal to emissivity into EB. That is equal to emissivity into sigma T to the power 4. This is the emissions for a non-black body, and always we are calculating per meter square. If I want to calculate for the entire area, you have to multiply this area. If I say this is having an area of A, so E, we can say total emissions will be equal to total emission will be equal to epsilon A sigma T to the power 4 from the entire surface, okay, and definitely it will be more than that of this one. It will be more than, because emissivity always is having a range between 0 to 1. It's always is having a range between 0 to 1. Okay, it is always having a range between 0 to 1. Is this clear? Now, here, now we'll be talking about the next important terminology that we call it as monochromatic emissive power, which we are denoting it as E lambda. If I say black body, so that will be black body monochromatic emissive power. Or let's say only monochromatic emissive power, that will be E lambda. Okay, fine. What is the basic significance of E lambda? If I try to integrate the value of monochromatic emissive power from 0 to infinity, that means for all the wavelengths that we are having in the spectrum, if I try to integrate, that will be giving us the value of total hemispherical emissive power. Total hemispherical emissive power. You are getting questions from this. They will be giving some range of values of monochromatic emissive power for different ranges of wavelength. From there, you can, they are asking you what is the total emissive power. Let me take one question. If I say from 0 to 2 micrometer, E lambda is equal to 10 watt per meter square. From 2 micrometer to, let's say, 50 micrometer, that is E lambda is equal to 0. From 50 micrometer, greater than 50 micrometer, your E lambda is equal to, let's say, 20 watt per meter square. So can you tell me what will be the total hemispherical emissive power? It's quite easy. We just need to take from range from 0 to 2 micrometer E lambda D lambda, plus from 2 to 50 E lambda D lambda, plus 50 to infinity E lambda D lambda. So from this case, you can now easily calculate what is the value of total total emissive power of a non-black body. If you want to have a black body, then we can have over here as important concept E B lambda is equal to E lambda upon E B lambda, and this is, we call it as monochromatic emissivity. Monochromatic emissivity. And there is an important significance of this monochromatic emissivity. There's a very important significance of this monochromatic emissivity. That is, if I say that monochromatic emissivity is equal to E lambda by E B lambda, and emissive power is equal to E by E B. I can rewrite this as, emissivity is equal to integration of E lambda D lambda divided by, we can say, monochromatic emissive power into integration of EB lambda into D lambda. Now, instead of this, I can write it as monochromatic emissivity into EB lambda into D lambda divided by integration of EB lambda into D lambda, right? So if I assume that if your monochromatic emissivity is not a function of lambda, then I can take this as outside. So in that case, I can get emissivity is equal to EB lambda, and this particular condition, can you tell me which body is having this kind of situation where the emissivity is not a function of wavelength? This kind of body, we call it as a gray body. This kind of body, we call it as a gray body. And why this is important? Because practically you cannot achieve a black body. You can have a closer to black body, but you cannot achieve a black body. So if I try to have an understanding, when I plotted a graph between E lambda and we can say wavelength at a particular temperature at temperature T, it is being found that when I plotted for a black body, we had a graph like this, and when I plotted for a gray body, we had a graph like this. That means your gray body and black body is showing the same trend. This is for a gray body, right? This is for a black body. So as black body and gray body is showing the same trend, if I want to analyze this body, if I say this is your at lambda 1, this is at lambda 2, I can simply say that E B lambda 1 by E lambda 1 is equal to E B lambda 2 by E lambda 2. That means if I want to calculate what is a black body MSE power at any particular wavelength, and if I know the we can say the monochromatic MSE power of a gray body, I can easily calculate now this, because this ratio will always be constant. And if I talk about the rest of the bodies, if I say the real bodies, it will always be like this. This is basically for the rest bodies or real bodies. Okay, it can be less than gray body, but it would never ever be more than that of a black body energy. Black body is having always the highest power, highest energy, right? So if I try to plot, now I can easily identify the physical significance of a gray body is just by knowing the gray body monochromatic MSE power, I can easily calculate the black body if I only know this particular value. Okay, fine, because this ratio of the black body MSE power to the monochromatic power of a gray body will always have a constant ratio. Okay, this is the significance of the gray body. Very important. Right? So now let's quickly talk about the different laws of radiation, because sometimes question is being asked. We won't be taking much time to discuss laws of radiation, because we need to have a discussion in the radiation network. Very, very important. Radiosity, what is space resistance, what is surface resistance there, and what is the concept of shielding. That is very, very important. And before that, we'll be talking about the important concept of shape factor also. So if I talk about the laws of radiation, first law is your Kirchhoff's law. It simply said that when the body is at thermal equilibrium, whatever will be the absorptivity, the same will be the emissivity. That means from this, I can say that a good absorber is also a good emitter. We can simply say that a good absorber is also a good emitter by using or by understanding this Kirchhoff's law. That means the absorptivity will be exactly equal to emissivity at thermal equilibrium. Okay, next is a very interesting and very important law. We call it as Planck's law. And why I'm saying this is important, because all the derivations, all the formulations that we are studying in radiation is being derived from this Planck's law. And Planck's law, what is suggested, that he has given a relation between the black body monochromatic MSE power of a black body is a function of wavelength and absolute temperature. He has given a relation. He has given a relation of black body MSE power is equal to C1 lambda to the power minus 5 E C2 by lambda T minus 1. Okay, so it is being seen that when you try to plot, if I try to draw it manually over here, this is your EB lambda, this is your lambda. If I say this is for one temperature, let us suppose 1000 K. This is for a temperature, let us suppose 800 K. This is 800 K. And if I talk about the third temperature, let's suppose 500 K. Okay. That means when a body is kept at 1000 Kelvin, at different wavelength, we'll be having a monochromatic MSE power for black body like this. At 800 Kelvin, we'll be having like this. So can you visualize very important significance that if I talk about the wavelength at which it is having the maximum energy, let's say this is lambda M1. let's say this is lambda m2, lambda m3. This is your T1, this is T2, this is T3. So when the temperature is decreasing, what is happening to lambda m? Can you tell me by looking at the graph? When the temperature is moving from T1 to T3, what is happening to the lambda m value? Yes, the lambda m value is basically increasing. Yes, this is the observation that was made by a very famous personality. We call it as Wiens. His name was Wiens, and from there he has given a very interesting we can say Wiens displacement law. What is this Wiens displacement law? Wiens displacement law. Wiens displacement law basically suggested that the product of, because we can say that lambda m and t are inversely proportional, we can say lambda m is inversely proportional to the absolute temperature. We can say from this, right? So from this we can simply say lambda m into t is always a constant value, and it is being observed that it is approximately equal to 2898 micrometer Kelvin. This was the observation given by the Wiens displacement law. This was the observation given by the Wiens displacement law. That means the product of the lambda. What is lambda m? Lambda m is that wavelength at which you are getting the maximum temperature at that maximum energy monochromatic MSE power at that particular temperature. Okay, if I say lambda m2, this is the wavelength corresponding to the maximum monochromatic MSE power at 800 Kelvin. If I say lambda m1, this is the maximum monochromatic emissivity power of a black body. I'm always discussing about black body. I'm not talking about the non-black body. Okay, the Planck's law, your Wiens displacement law, all these we are discussing about the non-black black body, right? Fine. So Wiens displacement law, it is being stated that lambda m into t is equal to 2898 micrometer into Kelvin. Stephen Boltzmann, already we have discussed sigma. This is for a non-black body. For a black body, we can simply say epsilon will be equal to 1. That is this. Okay, fine. The next one is Lambert cosine law. So for understanding the Lambert cosine law, let us have a clarity, that is intensity of radiation. Intensity of radiation, which I am denoting as I. Now, what is intensity of radiation? For that, you should be knowing what is a solid angle. Let us suppose if I say a 2D plane. If I take a 2D plane, right? If I take a 2D plane, if I take an arc, then we call this as an angle theta. We call this as an angle theta. So this is, let us suppose r. So this will be r theta, right? Fine. So what we are saying, what will be this length? This is r into theta. Okay, fine. In 3D plane, in 3D body, we are calculating the angles by using a very interesting term. We call it as the solid angle. Solid angle. Okay, fine. Solid angle, right? So what is this unit of theta? Theta is having a unit of radian. What is the angle of what is the unit of this solid angle? That is equal to stir radian. The unit is stir radian. The unit of the solid angle is stir radian. Is this clear? Fine. So now we can say how we can calculate this omega. If I try to see, if I take this as the normal area, this is the normal area AN, and if I say this is the radius R, we can say the solid angle is equal to the normal area divided by R square. Here, how we are calculating this theta? Theta is equal to L by R. What is L? This is L. This is L. Okay, fine. From 2D and 3D plane, we are calculating. Now, what is intensity of radiation? Intensity of radiation is basically equal to the hemispherical MSE power per unit wavelength. the hemispherical MSE power, hemispherical MSE per unit solid angle, okay, I can say this is the emissive power per unit solid angle. Okay, emissive power per unit solid angle is basically the concept of intensity of radiation. What is the meaning of this? The meaning of this is, let us suppose if I say there's a surface, right? And if I say this is a particular direction in which I'm calculating intensity of radiation, and it will be comprising of all the wavelengths. Definitely, I'm not talking about per unit wavelength. This particular energy, it's in only in one direction. Okay, so intensity of radiation is nothing but we are talking about in terms of the directional property. If I talk about per unit wavelength, that will be called as a monochromatic MSE power. Okay, so the major difference between intensity of radiation and monochromatic MSE power is intensity of radiation is defined for per unit, we can say solid angle. That means in the direction, in which direction we are discussing. If I say per unit wavelength, that will be called as the monochromatic MSE power. So now, if I say, if I take a plane which is making an angle of theta, and if I say this is the normal, right? So Lambert cosine law stated that I is equal to In cos of theta. This is your Lambert cosine law. If this I say this is In, this is I, if I say this is theta, so we can say I is equal to In cos of theta. Fine. But if I talk about a black body, we know that for a black body is a diffusive surface. It is a diffusive surface. What is the meaning of diffusive surface? That means in all the direction will be having the same intensity of radiation. That means in all the direction we have the same intensity of radiation, right? It will be having the same magnitude. Yes or no? So if I want to calculate what I've written, I is equal to dE by d omega. So if I write, this is for black body, so DEB is equal to integration of I d omega from 0 to pi, because I'm going from 0 to pi. So this will be equal to pi into I, because in every direction I is same. Integration of solid angle from 0 to pi will be pi. So this is your black body, right? So I can say that for a black body, the intensity of radiation is nothing but EB by pi. Direct formulation. Okay, for a black body, we can simply say EB by pi is nothing but the intensity of radiation. What is EB? Sigma T to the power 4. Sigma T to the power 4. Is this clear? Yes. Okay. Yes, we have calculated, right? How we have calculated? Look. If I say this is a point, okay, this is the emission I, right? So what is happening? I am going from 0 to pi, okay? So integration, and if it will be forming a cone-like structure like this. If it will be forming a cone-like structure, so if I try to integrate this d omega from 0 to pi, this will be giving us a pi. This is the total, we can say, solid angle in 3D, exactly in 3D. This is the total solid angle, which is basically forming a hemisphere. Right? So we can say that for a black body, the intensity of radiation is equal to the black body MSE power divided by pi. And that will be having a unit. What is the unit of this? Watt per meter square stir radian. Watt per meter square stir radian will be the unit of the intensity of radiation. Okay, so these were the different laws of radiation. Now let us talk about a very, very important one question almost every year you are getting from the topic of shape factor. almost every year you're getting a question from the shape factor. So let us try to understand what is a shape factor. There are different laws of radiation. There are different theorems that we are using to calculate shape factor, and there is one hotel crossing method also that we'll be discussing, right? So let us quickly understand what is the meaning of this shape factor. Let us suppose I'm talking about shape factor. Okay. Let us suppose I'm having a surface, okay, at some temperature T1, emissivity E1, and we are having a second surface at temperature T2 and emissivity E2. Let us suppose 100 units is leaving surface 1. 100 units is leaving surface 1. So is it mandatory that entire 100 will be reaching surface 2? Is it mandatory that entire radiation which is leaving surface 1 will be reaching surface 2? It is not mandatory. Only a portion or a fraction will be reaching. Only a fraction. Let us suppose, let's say only 30 units is reaching surface 2. We can have a vice versa analysis also. Let us suppose from this surface, let us suppose 70 units is leaving from this surface, and out of 70, only 50 units is reaching surface 1. So can we say that the fraction of radiation which is leaving surface 1 and reaching surface 2, that fraction, we call it as the shape factor. Like in this case, can we say what will be the fraction out of 100, 30 units is leaving, reaching surface 2. So that will be called as the shape factor, that is fraction of radiation which is leaving from surface 1 and reaching surface 2. That is we call it as a shape factor. Okay. I can say vice versa also. 70 units is leaving surface 2. Out of 70, only 50 is reaching surface 1. So I can say out of 70, only 50 is reaching surface 1. So shape factor F21 will be equal to 5/7. Let's say we can say the fraction. Okay, it is not always mandatory that the entire radiation, if I say if I'm having some radiation from my body, it is not mandatory that the radiation will be reaching a particular body which is in the adjacent room. Okay, fine. So it is very much important that you should be having a understanding what is the meaning of this shape factor. Okay, clear? So shape factor is nothing but the fraction of radiation which is leaving from one surface and reaching the second surface. That fraction of radiation, we call it as the shape factor. Now, for calculation of the shape factor, there are some basic understanding that you have to keep in mind, and there are some theorems also that you have to have a clarity. So let us suppose I'm having a flat surface, which is I'm calling it as surface number 1. So can you tell me what will be the self-shape factor? What is self-shape factor? Self-shape factor is the radiation which is leaving its surface and hitting its own surface. So for a flat surface, is that possible? The radiation which is leaving the surface and it will be hitting its own surface. Is that possible for a flat surface? Yes or no? It is not possible. So we can say the self-shape factor for this surface, which I'm denoting as 1, is equal to 0. Right? The self-shape factor for this surface F11 will be calling it as 0. Coming to a concave surface. If I talk about concave surface, let's say this is surface number 2. Okay, then what will be F22? What will be F22? 22 means leaving surface 2 and hitting its own surface. So in this case, there is a possibility that it can hit its own surface. So we can surely say this is not equal to 0 for a concave surface. If I talk about convex surface, we can say in this case, it is not possible that it will be hitting its own surface. Shading should be inside, right? It is something like this. Okay, this is surface number 3. So it is not possible to have the fraction of radiation which is hitting its own surface. So I can say F33 is equal to 0. Okay, F33 is equal to 0. Fine. So to have better understanding, now what we have seen that shape factor can never ever be more than that of 1. Shape factor will always be ranging between 0 to 1 only. Either it could be 0, either it could be 1, or it between 0 and 1. Okay, so from here we need to have some important discussion about some theorems. The first one we call it as reciprocity theorem. What is this reciprocity theorem? It states that F12 into A1, 122 into A1 is equal to F221 into A2. Always keep in mind that if you're having multiple surface, reciprocity theorem it is always applied between two surface only. If I say, if you're having multiple surface, like say the surface 1, surface 2, surface 3, so at a time you can apply between 1 and 2 or 1 and 3 and 2 and 3. Okay, please keep in mind the reciprocity theorem is always applied between two surfaces at a time. Okay, multiple questions you are solving by using this reciprocity theorem. Okay, the second theorem that you should be having a clarity is summation rule. Summation rule. What is the summation rule? Let us suppose I'm having surface 1, surface 2, surface 3, surface 4. We're having n surfaces. We're having total n surfaces. So it is being observed that F11 from surface 1 to the rest of the surfaces 1, 2, 1, 3 till 1n is always equal to 1. This is called as the summation. That means the shape factor calculated from one surface to the rest, all the surface, n number of surface that we are having, the summation will always be equal to 1. If I say in a general perspective, Fn1 plus Fn2 Fnn is equal to 1. Is equal to 1. Okay, the summation of all the shape factors. Yeah, last time I think they have not asked, so you can expect 2023 May they can ask a question from shape factor. 90% or 95% of chances you can get a question from the shape factor. Okay, because almost every alternate years they are asking. If you see the trend also, they are always they're asking a question from this, and very easy question. I think you can easily calculate now. Fine. Reciprocity theorem, your summation rule we have covered. Now there is one more theorem that we are using. Many of the students, yes, you will be getting this after the session. Okay, that we call it as the view factor between infinitely long surfaces. This we call it as cross string method or Hotel cross string method. That means if I say this is surface 1, this is surface 2, right? Fine, they could be parallel, that could be non-parallel, right? In the Telegram channel, there's a Telegram channel in the description section. You can get that over there. Fine, if I say this is surface 1, this is surface 2, let's say this is L1 and this is L2, and its width is very, very large, right? One of the dimension is very, very large. So if I say view factor between infinitely long surfaces, that means one of the surface is very, very high. In this particular case, I can use this expression that is very easy. The summation of the cross string minus summation of the uncrossed string divided by 2. So if I say over here, if I try to apply over here, if I join, let's say this is point A, this is point B, this is point C, this is point D. Okay, so cross string matlab join the extreme two edges. Okay, so I can say F12. I can say F12. What is F12? F12 equal to summation of the cross string. Cross string means you have to join the diagonals. So AD plus BC minus uncross matlab join the other two edges, that is AC plus BD divided by twice of the originating length. It is basically called as originating. What is originating length? I am calculating the shape factor from surface 1 to surface 2. So you have to see L1. Okay, if I want to write F21 will be numerator will be exactly same, only will be having the changes in the denominator, that is 2 into L2. F21 will be equal to AD plus BC minus AC plus BD divided by 2L2. Is this clear? We can use this particular relation to get a one question was asked like this. Let us suppose this is a plate. One of the dimension is having infinite and this is having a same length L, making an angle of alpha. So what is, let's say this is surface 1, surface 2. What is the shape factor 1 to 2? Can anyone who can tell me this answer in this particular comment section? We are having a surface 1. We are having a surface 2. What will be the shape factor? Apply the hotel cross-string method. One length is the width is infinite. The width is one length is infinite. The width is infinite. Inside the board is having a larger dimension. Okay. One dimension is not always length. We can take width also as one of the length. Right. So here the question is, what will be the shape factor? So just now we have seen that if I say there are two surfaces L1, L2, A, B, C, D. So let us try to write the same dimension over here. For plate 1, this is A, this is B. For plate 2, the same point is C and this is D. Okay. So what is the shape factor? Sir, equal to cross string AD plus BC minus uncrossed AC plus BD divided by twice of L1. Now, what will be the length AD? Tell me. Use this expression over here. F12. What is length AD? Anyone who can tell me in the comment section. What is the length AD? Sir, it is equal to L. What is length BC? L. Minus. What is length AC? AC is equal to 0. What is length BD? Now I need to calculate this length BD. Very good, Sujesh. So if I try to join this, can I say this is an isosceles triangle? If this is an isosceles triangle, if this is apex, this will be 90 degree. Okay. So can we say what will be this length? Anyone? If I say this is alpha by 2, okay. So this will be L sine alpha by 2. So this is L sine alpha by 2. This is again L sine alpha by 2. So this is plus 2L sine alpha by 2 divided by twice of L. So 2L minus 2L sine alpha by 2 divided by 2L. 2 get cancelled out. So we are getting an expression of F12 is equal to 1 minus sine alpha by 2. This expression you are using directly. I think you might have solved some previous year questions. So there you might have observed this kind of one question. It's a previous year question, right? So definitely you should be knowing from where this expression you are getting. We are using this concept of hotel cross-string method. Okay, is this clear? Hotel cross-string method. Right? Now we can apply this particular concept anywhere, wherever required. But the condition is one of the dimensions should be having a very, very large size. Okay. Perfect. Now let us talk about very interesting concept, that is radiation network. So here we need to understand two concepts, that is radiosity written as J and second is irradiation denoted as G. What is radiosity? Tell me in the comment section what is the value, what is the meaning of this word radiosity? Anyone? Radiosity is basically the amount of radiation which is leaving the surface. Amount of radiation that is leaving the surface, that we call it radiosity. Irradiation means the amount of radiation which is incident on the surface. Okay, so let us take one example, and it's a very important discussion, because from this concept we will be now trying to understand the concept of radiation resistances. Okay, fine. So now let's try to understand. Let us suppose I'm having an opaque surface. I'm having an opaque surface at temperature T, and over which there is some radiation which is incident, which we call it as irradiation, denoted as G. It is having some emissivity E. Okay, so definitely, because this is having some emissivity, so can we say this is a non-black body or a black body? It is having a emissivity E value which is not equal to 1. So definitely this is a non-black body. If it is a non-black body, it will be having some amount of reflection. Let's say rho is reflectivity, rho times G will be the reflected part. Okay, or you can say this as the reflected part, right? Will be having some reflection. Fine. And definitely it is having some temperature. It will be having some emission. Let us say this is your emitted part from Stephen Boltzmann. Emitted part, which is I'm denoted as E, and this is your rho times G. So can we say the total radiation which is leaving the surface, that is radiosity, the total radiation which is leaving the surface, which would as radiosity, can we say this is equal to the reflected part plus the emitted part? Right? What is reflected part? That is rho times G. Emitted part is E. Right? I can write, because this is an opaque surface, can we write it as because we know that alpha plus rho plus tau is always equal to 1. Alpha is absorptivity, rho is reflectivity, and tau is transmissivity. As this is an opaque surface, tau is tending to 0. We can say rho is equal to 1 minus alpha. If rho equal to 1 minus alpha, I can write it like this: 1 minus alpha into G plus emissivity into EB. Okay, fine. Now, as we know that Kirchhoff's law, what does this Kirchhoff's law stated? Kirchhoff's law stated that absorptivity will be exactly equal to emissivity. So we can say that your 1 minus emissivity into G plus EB into emissivity. This is your value of J. Okay, this is the value of J. So now if I rewrite this expression over here, J is equal to 1 minus emissivity into G plus emissivity into EB. G can be written as J minus emissivity into EB by 1 minus emissivity. So what was happening was, we are having a surface, right? So can we say what is the net heat exchange? What is the net heat exchange between surface to surrounding? Can we say net amount which is incident, net amount which is leaving, the difference of that will be called as a net heat exchange. If I'm saying I'm getting 4 units, I'm giving 100 units, so net heat exchange will be 100 minus 4, that is 96. So I can say that the net heat exchange will be equal to J minus G into A. J minus G into A, because I have to calculate for the total area. This is, we call it as the net heat exchange from surface to surrounding, right? What is G? G, we know that, place it over here. J minus G is J minus E into EB upon 1 minus E into A. So after solving it, if you try to solve, it will be J get cancelled out. We'll be having EB minus E into J. Okay, E into J divided by 1 minus E into A. Right? So if I rewrite this expression over here, that Q from surface to surrounding is equal to EB minus J divided by 1 minus emissivity upon emissivity into A. 1 minus emissivity upon emissivity. Now, if I try to write in a electrical analogy perspective, if I write from a resistance perspective, if I say this is EB, this is J, right? This is your heat exchange or heat transfer. So this particular we can say V is equal to, or I is equal to change in voltage by R. If I say this is I, this is R, this is voltage change. So can we say this is nothing but, we call it as a resistance, and this resistance, because this is I'm talking about on the surface, so this is we call it as a surface resistance. This is we call it as a surface resistance. Okay, fine. So I can say R surface resistance, R surface. Now we can simply say that the surface resistance will be equal to 1 minus emissivity upon emissivity into A. Okay, 1 minus emissivity upon emissivity. Now can you tell me what is the surface resistance of a black body? What is the surface resistance of a black body? Anyone? What is the surface resistance of a black body? Yes, for a black body, as we know that emissivity is equal to 1, so the surface resistance is equal to 0. The surface resistance is equal to 0, and that is the reason when I was discussing about this example, I'm having a black body, I'm having a non-black body, same temperature T being kept. From here we are having EB, right? Here we are having E, right? So definitely this EB will be more than that of E, because on the black body there is no surface resistance which is trying to decrease the emission, but on the non-black body, due to the surface resistance, it is not able to have that amount of emissions, right? So if I say this is your total J, so we can say EB to J, this will be called as the surface resistance. Surface resistance. Okay, fine. And black body will be having a 0 surface resistance. Is this clear? Fine. Very simple, very straightforward. Clear? Here if I try to draw, it will be directly EB. It will be starting from EB, right? It will be having a direct starting from EB. Won't be having any surface resistance. Okay, fine. So now this was, I'm talking about only from the surface perspective. But let us take one more example. Let us suppose I'm having one plate over here and one more plate over here. Okay, fine. Let's say this is temperature T1, emissivity E1. This is temperature T2, emissivity E2. Now let us suppose from this surface, J1A1 is the total radiation leaving from this entire surface. And it is not mandatory that all the radiation will be reaching this surface too. Can we say from this J1A1, only a fraction is reaching surface 2, that is F12 J1A1. Same applies over here also, that if I say J2A2 is the total emissions leaving from surface 2, only a fraction will be reaching to this F21 J2A2. So what is the net heat exchange between the surfaces, between the surface? Can we say from Q1 to 2 is equal to F1 to J1A1 minus F21 J2A2. Take the mod value because we don't know which will be having a larger magnitude. Fine. So from here, can we say F1 to A1 will be equal to we can say F12A1 is exactly equal to F21A2. Reciprocity theorem, take that common. So we'll be having J1 minus J2 divided by 1 minus F12A1. So now let us try to have a visualization that we can have a similarity of resistance analogy J1 to J2, right? So this particular expression basically signifies the space resistance. This basically resembles the space resistance, right? Okay, so this is your space resistance, that is 1 upon F12A1. So now if I now try to club this particular expression over here, if I try to understand, let us suppose we are having a surface 1 at temperature T1, emissivity 1. We are having a surface 2 at temperature T2 and emissivity E2, right? Fine. So definitely what will be having, how many resistors will be having? One will be your surface resistance. On this surface will be having a space resistance and will be having a surface resistance too. Fine. So in total we will be having 3 resistances, 2 surface and 1 space. If I try to write in terms of your network diagram, EB1 J1, from J1 to J2, from J2 to EB2, right? So this will be your surface resistance 1, this will be your space resistance, and this will be your we can say surface resistance for 2. So now if you want to calculate what is the total heat transfer between the surface, that is equal to EB1 minus EB2 divided by the total resistance, that is 1 minus emissivity 1 upon emissivity 1 A1 plus 1 minus 1 divided by F12 A1 plus 1 minus emissivity 2 upon emissivity 2 A2. So this expression you can now apply to between any 2 bodies. That could be 2 parallel long plates, that could be 2 infinitely long cylinders. You can apply this to any of the formulations. Let us try to apply this particular concept over here. Let us try to apply this concept, the heat transfer between infinitely large parallel surfaces. That means if I say there are 2 plates which are infinitely long. So if I say if the 2 plates are infinitely long, what will be the shape factor from 1 to 2? Yes. What will be the shape factor from 1 to 2? Anyone? What will be F12 if you're having infinitely long? Sir, obviously it will be equal to 1 because it is infinitely long. That simply means F12 will be exactly equal to F21, that is equal to 1. And also we can say that A1 is equal to A2 is equal to 1 meter square, because we can assume, or we can say this is equal to A because both are infinitely long. We can say, we can calculate per meter square. So now let us say how many resistance will be there. Again we'll be having 3 resistances. There is a surface resistance, there is a space resistance, and there is a surface resistance, right? So now if I try to write the expression, it will be Q is equal to EB1 minus EB2 divided by 1 minus emissivity 1 upon emissivity 1 A1 plus 1 upon F12 A1 plus 1 minus emissivity 2 A2. Right? We can take A1 equal to A2 is equal to A. So we can say Q by A is equal to sigma T1 to the power 4 T to the power 4 divided by, we can write this as 1 upon emissivity 1 minus 1 plus 1 plus 1 upon emissivity 2 minus 1. So this get cancelled out. So ultimately what we are having, if I write small q as a heat flux is equal to sigma T1 to the power 4 T2 to the power 4 divided by 1 upon emissivity 1 plus 1 upon emissivity 2 minus 1. This is for the heat flux between two infinitely long parallel plates. Two infinitely long parallel plates. I've not applied anything new, just I've taken the same expression. Only the boundary conditions I've applied. F12, F211, A1, A2 is equal to A. Okay, but if I try to apply the same logic over here between two infinitely long cylinders having emissivity E1 and E2, let's try to apply the same logic over here. There are two infinitely long cylinders. This is T1, this is T2, emissivity E1 and E2. So in this case, will it be F12 equal to 1? What will be the value of F12 equal to 1? Or F12 is equal to less than 1? Or F12 equal to, what will be this? Sir, because this is infinitely long, if you try to see from the side view also, this is your inner surface, this is the outer surface, F12 will always be equal to 1. F12 will always be equal. If you see the side view, this is the side view, you will be getting this as F12 is equal to 1. Right? If F12 is equal to 1, now let us apply the same logic. How many resistances? We'll be having one surface, we'll be having one space in between, and again a surface resistance. So apply this logic. So we can say Q122 or heat flux between the two surfaces is equal to EB1 minus EB2 divided by 1 minus emissivity 1 A1 plus 1 upon F12 A1 plus 1 minus emissivity 2 A2. But here, is A1 and A2 same or unequal? What is A1? A1 is equal to, it is 2 pi R1 into L. This is your radius R1. And A2 is 2 pi R2 into L. This is your R2. So definitely A1 and A2 are not same in this case. A2 is more than that of A1. Okay. So now we can say that Q is equal to, if I take A1 common, what will happen? A1 into EB1 minus EB2 divided by 1 upon emissivity 1 plus 1 minus emissivity 2 upon emissivity 2 A1 by A2. So this is the expression that we are getting for a heat exchange between two infinitely long parallel cylinders. Okay, fine. The same thing is being written over here also. Fine. Is this clear? Okay. Yes. So now we are entering to a very interesting segment, that is radiation shield, the last segment of radiation, right? I'll be taking approximately 10 to 15 minutes, not more than that. Okay. Then Chandra sir will be coming and we'll be discussing about very important topic of heat exchanger and convection. Now, what is this radiation shield? Basically, this is being used to reduce the heat transfer. Shield is basically, you can see from the this particular diagram also, there's a shield being used. There's a shield being used which is trying to restrict or reduce the effect of radiation. Okay, so here what we are doing is we are decreasing the radiation heat transfer. It tries to reduce the radiation heat transfer. Okay, then how we can reduce this shield? So let us take one example. Let us suppose when we were having two plates, okay, T1, T2, emissivity 1, emissivity 2. Can you tell me what is the total number of resistances? Total resistances. Anyone? When we were having two plates which is kept at some distances, so definitely we are having three resistances, right? If I write it like this, Q is equal to, we can say EB1 minus EB2 divided by the total resistance, that is your three resistances, right? Fine. But if I now try to understand that, if I say there are two plates at temperature T1, T2, emissivity E1, E2. Now I am introducing one more surface at having a emissivity of E3. By this introduction, now can you tell me how many surface and how many space resistance? How many surface and how many space resistance? Try to count this. This is a surface, a space, a surface, a surface, a space, a surface. So if I try to see, the surface resistance has have 1, 2, 3, 4, 4 surface resistance, and space resistance is equal to 2. So total resistance is 6. Our total is coming out to be 6. Okay, total 6 resistances. Now, but is the temperature in both the case different or same? It is still the same. T1 and T2 is still the same. So if we try to visualize, Q is equal to sigma T1 to the power 4 minus T to the power 4 divided by the new R total. Numerator is same, but the denominator has increased. What will happen to the heat transfer? It will be drastically decreasing. It will be drastically decreasing because now the R total has increased from 3 resistance to 6 resistances. From 3 resistance to 6 resistance, because if you write this expression, Q is equal to sigma T1 to the power 4, T to the power 4 divided by R total. So numerator is still same, denominator has been increased. So now we can simply say that the heat transfer has been decreased by a very huge magnitude. Okay, so now one important question is, what should be the property of a shield? What should be the property of a shield? What should be the characteristic of a shield? If I want to increase the resistance or if you want to decrease the rate of heat transfer, what should be happening? Because if you see, space resistance you cannot do. But if I talk about the surface resistance, if I talk about the surface resistance, which is equal to 1 minus emissivity upon emissivity into A. If I want to increase the surface resistance, what I'll be preferring? High emissivity or low emissivity? High emissivity or low emissivity? Which I'll be preferring? If you are having low emissivity, right? If emissivity decreases, the surface resistance is increasing. Right? And we also know that emissivity is equal to 1 minus alpha, or 1 minus, we can say rho is equal to 1 minus alpha, or rho is equal to 1 minus emissivity. That means if you try to decrease the emissivity, you try to increase the reflectivity. That means, very important conclusion that we are making, that we always keep a highly reflective surface. The shield should be highly reflective surface, and that is the reason you might have seen inside the thermos flask, it's a very shining surface in order to keep that hot fluid inside the thermos flask for a longer duration. If I want to increase the resistance, we always try to increase its reflectivity. Once the reflectivity increases, it decreases the emissivity, and once the emissivity is decreased, you are increasing the surface resistance, and you can restrict the heat transfer for a longer duration. Okay, is this clear? Fine. Now let us suppose I'm having, let's say this is T1, this is T2. I'm using, let us suppose, 10 shields in between. So how many number of surface and how many number of space resistance? If you are using 10 number of shields, can you tell me how many number of surface and how many number of space resistance? Yes? Anyone? There are 2 plates. In between these 2 plates, I am keeping 10 shields. Then how many number of surface and how many number of space? Quickly. It's a very simple expression. We can simply say that the number of surface resistance is equal to 2n plus 2, and the number of space resistance is equal to n plus 1. It is only applicable if all the we are having we can say non-black body, because black body is having a 0 surface resistance. Please make sure we are using this expression only for non-black bodies. For black bodies, surface resistance is basically 0. So now if you see there are n is equal to 10, if n equal to 10, the surface resistance will be equal to 22 and space resistance will be equal to 11. So total will be 33. Total will be 33. Okay, fine. And after this, let's try to quickly wind up. So if I say, if I'm having two infinitely long parallel plates having temperature T1, T2, but same emissivity, right? Then what will be the rate of heat exchange? Q will be equal to, let me write this direct expression, that is sigma T1 to the power 4, T to the power 4, or let me write it like this, EB1 and EB2. EB1 minus EB2 divided by 1 upon emissivity plus 1 upon emissivity minus 1. So we can say this is EB1 minus EB2 divided by 2 by emissivity minus 1. This is the net heat exchange between two plates. This is without a shield. This I'm talking about for without shield. Okay, this is without shield I'm discussing. And keep in mind, I'm taking same emissivity. But if I'm having a condition like this, T1, T2, emissivity E, the shield is also having an emissivity E, then what will happen? We will be having the heat flux is equal to EB1 minus EB2. Now there will be how many resistances? 4 surface and 2 space. So if I write it like this, it will be 1 minus emissivity upon emissivity plus 1 upon F13 A1 plus 2 times 1 minus emissivity by emissivity into A plus 1 upon F31 A3 plus 1 minus emissivity upon emissivity into A. Okay, so when you try to solve it, because all are having the same emissivity, A1 is equal to A2 is equal to A is equal to A3. This is your surface 3, right? So I can say an F13 will be equal to 1. F13 is equal to 1. F32 is equal to 1. Ana? 3, 2. Fine. So while solving, we're getting EB1 minus EB2 divided by 4 times emissivity minus 2, or we can say EB1 minus EB2 2 times 2E minus 1. So this is the same expression that we got over here. So we can say this is nothing but Q without divided by 2. That means, what is the meaning of this? The meaning of this is, this is your A3, A2. The meaning of this is, when you are introducing a shield which is having the same emissivity as that of these plates, the heat transfer has been decreased by 50%. If you try to visualize what has happened, the Q width is equal to Q without a shield divided by 2. This was with a shield. Okay, that means we had a 50% decrease in the heat transfer. We had a 50% decrease in the heat transfer. This is only I'm talking about one shield. I have used one shield, 50% decrease in the heat transfer happened. But if I try to use multiple n number of shields, then what will happen? In that case, there's a direct relation that we can use. The net heat loss with n number of screen or n number of shield is equal to 1 upon n plus 1. That means the Q with shield is equal to Q without shield divided by n plus 1. Okay, this is only applicable when all the plates are having same emissivity. This is only applicable when all the plates are having same emissivity. So if I ask you a last question, if I want to have an 80% decrease in the heat transfer, can you tell me how many plates, how many shields you have to use? If I want to have an 80% decrease in heat transfer, so can you tell me how many shields you will be using? Simple question. When we were using one shield, 50% heat transfer decrease we are getting. So how many shields we have to use in order to get 80% decrease? 80% decrease means 0.2 times. So 0.2 will be getting when you are taking n equal to, very good Malish, 4. So when you take n equal to 4, it will be 1 by 5. 1 by 5 is 0.2 times. 0.2 times means if I take n is equal to 4, so Q with shield will be equal to 0.2 times Q without shield. That simply means we are having a 80% decrease in heat transfer. Is this clear? We are having 80% decrease in the heat transfer. So now this is basically we have completed the radiation topic, right? So now we will be going with the Chandra sir and he'll be discussing with the next set of concept from the heat exchanger and convection. Very important. Every year one question is being expected from the heat exchanger topic. So Chandra sir, so bas ab yahan se you will be leading our students to the end, and from there he will be winding up our entire heat transfer marathon session.
There are more than 500 slides in total. So we have made these slides for you guys. We have worked so hard and we also expect the same thing from you guys. Definitely you will remember this time. Once you are through with your examination, you will definitely cherish this moment. So do enjoy, do get benefit from these sessions, and keep on sharing your doubts and keep on sharing your knowledge. Discuss whatever you feel like and keep your momentum high. Keep yourself positive till the examination gets over. That is what we have already discussed. Thank you, sir. Okay, thank you. So, convection. Yes, shall we start? All ready with your pen, paper, and dedication. That is most important. Your dedication, your motivation, keep yourself charged up. Have some energy drink because it is very much required. You are here from last seven hours without any break. Just small break we have given you. But because the examination is round the corner, that is why we want you guys to practice, we want you guys to revise as much as possible. Hi Bhaumik, welcome guys, welcome once again. So let us start without wasting much of your and our time. So convection, I have already told you in the previous session. Basic understanding about the convection we have already discussed. Convection, Newton's law of cooling defines the convection. So according to Newton's law of cooling, yes, the rate of heat transfer by convection, those who have missed the morning session, Q convection is given by H into surface area into bulk temperature difference, right? This is the mathematical expression. H is called as convective heat transfer coefficient. All right. And another important thing I have discussed, convective heat transfer coefficient is not a fluid property. It is very complicated parameter which can be obtained through experimental observation. So we can say that convection is the combined effect of conduction in the no slip region and bulk motion of the fluid. So from here we can write H, convective heat transfer coefficient, is minus thermal conductivity of the fluid into temperature gradient in the fluid at the interface divided by delta T. Delta T is the bulk temperature difference. This is how we get the parameter, and once we know the temperature as a function of Y, we can get the temperature gradient, and to get the temperature variation with y, we should have the velocity profile, and that is where the fluid mechanics comes into picture. So convection can be divided into two parts: forced convection and forced convection or artificial convection. First, when the fluid is forced to flow by using some external means like pump, boiler, fan, etc. So that is called as forced convection. The forced convection can be external forced convection or it can be internal forced convection. There are two types of forced convection, internal and external. Do you know the difference between them? When the fluid is flowing over the surface, that is external flow, and external flow will give rise to external forced convection. And when the fluid is flowing inside a pipe, then it will give the internal forced convection. Two parameters are involved in the fluid motion in case of forced convection. One is the pressure gradient, negative pressure gradient, favorable pressure gradient, and the inertia force. Pressure gradient and inertia force are responsible for fluid flow in case of forced convection. All right. And another is natural convection, when the fluid is flowing or when the fluid is moving naturally without any external means, then it makes the convection to be natural convection. Here, the parameters involved are density gradient, positive density gradient, and due to density difference, the buoyant force, FB, acts on the fluid particles and that develop the mixing, that develop the circulation of the fluid particle. That is how the free convection or natural convection takes place. All right. I hope you are comfortable with this basic understanding. Now we will be going into the deep details about convection. So give me thumbs up, guys, if you are all ready to explore. Give me thumbs up. Give me write Y in the comment section if my audio video are clear. ना थके हैं कभी पैर, ना कभी हिम्मत हारी है, क्योंकि जज्बा है अगर कुछ बनने का जिंदगी में, तभी संघर्ष जारी है. So keep your संघर्ष, keep your momentum high, keep your motivation, keep yourself positive for the next 1.5 hours, even 2 hours, so that you will be able to revise the whole concept of convection. Convection is important because it involves the fluid mechanics and heat transfer. That becomes the favorite topic for GATE examination. The topic which involves the concept from other subject, that becomes very, very important for GATE examination. All right. So let us start with the forced or artificial convection. When the fluid is forced to flow over by using some external source, so the flow can be classified in forced convection. The fluid flow can be divided into two parts. It is all about the fluid mechanics, and in fluid mechanics we define the flow or we classify the flow in two ways. One is external flow, when the flow is over a surface. Flow over a surface is external flow. And how to study the external flow? Who will tell me? How to analyze the external flow? By using which theory? Which theory is used to analyze the external flow? Tell me. And then it is internal flow. The flow in a pipe or flow inside a duct is a case of internal flow. When the fluid is flowing inside some restricted boundary, it is internal flow. When the fluid is flowing over some surface, over some boundary, that is external flow. External flow is studied by very well-known theory that is called as boundary layer theory. Who gave the boundary layer theory? Who had given the boundary layer theory? Tell me. Who gave the boundary layer theory? Given by L. Prandtl in 1904. No, it was not Blasius. It was Prandtl who had given the boundary layer theory, and Prandtl was the one who connected the fluid mechanics with the heat transfer. Right? All right. So first of all, we will talk about the external flow analysis of external flow that is already been done in fluid mechanics. If you have missed the fluid mechanics marathon, you can watch the recording. The link has already been shared with you, and PDF has also been shared with you on my Telegram group. Those who have not joined me on the Telegram yet, do join me on the Telegram. That is Mechanical by Chandrasekhar. So according to the boundary layer theory given by Prandtl, there is boundary layer developed when the fluid is flowing over some surface, over the flat plate. What is boundary layer region? It is very thin region, very close to the solid surface, in which the velocity of the fluid gradually increases from 0 to free stream velocity. The velocity gradually increases from 0 to free stream velocity in y direction, in the direction normal to the flow. Here u is equal to 0 and here u is equal to u infinity. U is equal to u infinity. The velocity is gradually increasing from 0 to u infinity. That region is called as boundary layer region. The region near surface in which velocity gradient exists. When u is a function of y, du by dy is not 0. And when du by dy is not 0, shear stress is not 0. Right? So u becomes a function of y. We need to understand how the velocity varies in y direction because of the boundary layer. So in this region, in boundary layer region, there is a steep velocity gradient. Velocity gradient is change in velocity with the space is called as gradient of velocity. That gradient exists, which promotes the momentum transfer in y direction. Due to the boundary layer theory, or due to the variation of velocity in y direction, there is a momentum transfer. It gives rise to the momentum transfer in y direction. And now we define one term that is called as thickness of the boundary layer. What is the boundary layer thickness? According to boundary layer thickness, or according to the Prandtl theory, the distance from the surface in y direction at which local velocity u becomes 99% of free stream velocity. That distance is called as thickness of boundary layer, that is delta x. The boundary layer thickness is delta x when the ratio of local velocity I am using small u divided by u infinity, it becomes 0.99. Almost u becomes almost u infinity, then the distance y will become delta x, or we can also call it as delta or delta x. That is called as thickness of boundary layer. I hope these 3 points are clear to everyone. Right? Now there is a growth of boundary layer over a flat plate. This is how the growth of boundary layer will take place. This is x is equal to 0, leading edge of the plate. This is the plate over which the boundary layer gets developed and grow. What is the meaning of growth of boundary layer? The thickness of boundary layer keeps on increasing from the leading edge to the trailing edge. This is x is equal to L, that is called as trailing edge of the plate. Initial part of boundary layer is laminar, then it becomes transition, then it is turbulent boundary layer. This is how the boundary layer growth takes place over the flat plate. Can you just let me know how do we identify which part of the boundary layer is laminar, which part of the boundary layer will be turbulent? Bataiye quickly. I want you guys to let me know which part of the boundary layer is laminar, which part of the boundary layer will be turbulent, how to find it out. How do we decide? How do we come to know which part of boundary layer is laminar, which part of boundary layer is turbulent? And those who have not liked the session, please do like it. What is the value of Reynolds number which makes the boundary laminar or turbulent? What is the value of Reynolds number? Bataiye. Definitely it is the Reynolds number. Yes, for external flow, the local Reynolds number which is given by rho u infinity x by mu, or we can write u infinity x by kinematic viscosity. That is called as local Reynolds number. Why? Because it is a function of x. At any x, the Reynolds number is defined as Rex. if Reynolds number at any x is less than 5 into 10 to the power 5, then the boundary layer over the plate will be laminar. And if the Reynolds number is greater than 5 into 10 to the power 5, then the boundary layer will be turbulent. So critical Reynolds number, we can define. What is the critical value of Reynolds number? That is 5 into 10 to the power 5. What is the meaning of critical Reynolds number? Yes, critical Reynolds number is 5 into 10 to the power 5. It means rho u infinity, critical value of x can be calculated from here, where the boundary layer changes from laminar to turbulent. That is called as critical value of Reynolds number. Critical means the boundary layer changes from laminar to turbulent at this value. All right. Similar to the velocity boundary layer, we can also have the thermal boundary layer to be developed. Why the velocity boundary layer gets developed? Because of the variation of velocity in y direction. Y direction is the direction which is normal to the flow. The flow direction is x direction. In normal direction to the flow, the velocity gets affected because of the presence of solid surface. That is called as velocity boundary layer. Similar to that, whenever there is a temperature difference between the surface and the fluid, the temperature profile gets developed in y direction. That is known as thermal boundary layer growth over the flat plate. What is thermal boundary layer? Similar to the velocity boundary layer, the definition says it is again the thin region very close to the solid surface in which the fluid temperature gradually varies. We are not calling it increases because it can either increase or it can decrease from the surface temperature to the fluid free stream temperature in y direction. Here the temperature is Ts. Here the temperature will be Ts. Surface temperature will be Ts and the fluid temperature is T infinity. There is a variation of temperature in y direction. The region in which variation of temperature takes place in y direction. You can see the temperature profile can be the velocity profile I have already shown you. The velocity profile I have already shown you. There is only one possibility for the velocity profile. The velocity here will be 0, here will be u infinity. So the velocity keeps on increasing. That is why it is mentioned the velocity increases. But in case of temperature, it can either decrease or increase. So if Ts is less than T infinity, then the temperature profile will be like this. Then the temperature profile will be like this. And if Ts is greater than T infinity, do you know how the temperature profile will look like? The temperature profile will look like this if Ts is greater than T infinity. This is the surface. This is how the temperature profile will look like. Here the temperature is Ts, here the temperature is T infinity. So it can decrease in y direction or it can increase in y direction. So that is why it is mentioned the temperature varies in y direction from surface temperature to the free stream temperature of the fluid. The region near surface in which temperature gradient exists. It means dt by dy is non-zero. dt by dy is non-zero. In this region, dt by dy is not zero, and that is why Q will be non-zero. There is a heat transfer taking place. In this region, steep temperature gradient exists, promoting the heat transfer. The velocity gradient promotes the momentum transfer, and the temperature gradient develops the heat transfer. Similar to velocity boundary layer thickness, we can define the thermal boundary layer thickness also. The distance from the surface in y direction at which T minus Ts becomes 99% of T infinity minus Ts is called as thermal boundary layer thickness delta T at that particular location. What does that mean? How we are getting this definition? Look, in case of velocity profile, what we say, u by u infinity is equal to 0.99, then y will be delta x, isn't it? When the ratio local velocity to the free stream velocity becomes 0.99, we can say u minus 0 upon u infinity minus 0, because 0 is the velocity at the surface. Here velocity will be 0. At the surface velocity will be 0, but the temperature will not be 0. but the temperature will not be 0. So corresponding to U, temperature is T. Corresponding to 0 velocity, temperature is Ts. Upon T infinity minus Ts, if this ratio becomes 0.99, then Y will become delta T. That is how the definition of the thermal boundary layer thickness. When the ratio of T minus Ts becomes 99% of T infinity minus Ts, then it is called as thermal boundary layer thickness at that particular location. Can you just let me know, in Y direction dt by dy, will it increase or decrease? In Y direction, what is happening to dt by dy? Will it increase, will it decrease, or will it remain constant? In Y direction, dt by dy, quickly, let me know. In Y direction, dt by dy, will it increase, decrease, or will remain constant? Tell me, increase, I for increase, D for decrease, C for constant. Everyone, please do let me know. dt by dy, will it increase, will it decrease, will it remain constant, or your answer is, or you are agreeing with Surendra? Do let me know, may increase or may decrease. Whether it is du by dy, listen very carefully, very, very important. Whether it is du by dy or dt by dy, it will always decrease in Y direction. When it become parallel to y-axis, when the profile becomes parallel to y-axis, it means dt by dy will be 0. Whether it is Ts greater than T infinity, or whether it is Ts greater than T infinity, or Ts less than T infinity, here dt by dy is equal to 0. So here the temperature gradient will be maximum. Here the temperature gradient will be maximum. So as Y increases, dt by dy or du by dy, both will decrease. Both will decrease in both the cases. The only thing is, here it is dt by dy is negative. Here dt by dy is having a negative sign, but here dt by dy is having a positive sign. That is the only thing. Why dt by dy is positive? Why dt by dy is positive in this case? Because as y increases, temperature increases. So the temperature gradient or the slope of the curve will be positive. Why it is negative in this case? Because as y increases, temperature of the fluid gets decreased. And that is why dt by dy will be negative. So sign will be different, but the magnitude will keep on decreasing. It is maximum near the surface. Either dt by dy or du by dy, it will be maximum near the surface. Is this clear or not? Is this clear or not? Do let me know. Is it all clear to everyone or not? It will decrease. No, Surendra, it will always decrease. Is this clear? So if I draw velocity boundary layer and thermal boundary layer over the flat plate, the free stream velocity is capital U or U infinity. The free stream velocity is capital U or U infinity. Or U infinity. And the free stream temperature is T infinity. The surface temperature is Ts. So if Ts is not equal to T infinity, if the temperature of surface and the fluid is not same, T infinity is the free stream temperature, then there will be growth of boundary layer velocity and thermal, and the curve will be like this. The curve will be something like this. There will be two curves here. In the laminar part of boundary layer, there will be two curves, and this is the transitional portion, and here it is turbulent. In turbulent boundary layer, the thickness of velocity boundary layer and thickness of thermal boundary layer will be same. It will be given by a single curve. But here, in the laminar part of boundary layer, there will be two curves, curve number A and curve number B. Can you just let me know which is thermal boundary layer, which is velocity boundary layer? A and B, which is thermal boundary layer, which is velocity boundary layer. In the laminar part of the boundary layer, when the Reynolds number is less than 5 into 10 to the power 5, there will be two curves, A and B. And in the turbulent part of the boundary layer, there will be a single curve. Velocity boundary layer and thermal boundary layer both will coincide. Tell me which is thermal boundary layer, A or B? Curve A, black one, or curve B, the other one, which is thermal boundary layer? यही आप लोगों को सीखना है. That is what you need to learn. That is what you need to revise. That is what you need to understand. That is why we are here. Last moment revision, which will help you to recollect all the concepts which we are going to discuss here. In your final exam, you will be able to recollect. Look, only one student had given me the correct answer. Sujis had given me the right answer. That depends on Prandtl number. The boundary layer is all dedicated to Prandtl. The boundary layer theory is all dedicated to Prandtl because Prandtl was the first person who had given the concept of boundary layer. So A and B, which one of them will be velocity or thermal boundary layer will be decided by the Prandtl number. When Prandtl number is less than 1, when Prandtl number is less than 1, then delta x will be less than delta t. When Prandtl number is less than 1, then delta x will be less than delta t. Velocity boundary layer thickness will be less than thermal boundary layer thickness for less value of Prandtl number. We are talking about laminar boundary layer when the Reynolds number is less than 5 into 10 to the power 5. There are two curves. In case of laminar boundary layer, when the Reynolds number is less than 5 into 10 to the power 5, when delta x is less than delta t, it is the upper one, the red one is the thermal boundary layer. This is thermal boundary layer. This is velocity boundary layer. So you can say the thickness of velocity boundary layer is less than the thickness of thermal boundary layer. Can you give me an example? Which fluid? Prandtl number, is it a property of the fluid or not a property? Prandtl number, is it a fluid property or not? Prandtl number, is it a property or not a property? Quickly. We need to wrap it up as early as possible. Prandtl number, is it a property? P for property, N for not a property. Tell me, everyone, keep your keyboard in front of you and try to give me the answer whenever I ask you something. Prandtl number is the property of the fluid. It is the dimensionless number which is property, and for a particular fluid, Prandtl number is fixed, like the density. It is like the density. If the fluid is fixed, the Prandtl number is fixed, like density. So for Prandtl number less than 1, the velocity boundary layer thickness will be less than the thermal boundary layer thickness, or we can say A will be the thermal boundary layer thickness boundary layer and B will be the velocity boundary layer. Can you give me an example of a fluid which is having less than 1 Prandtl number? Can you guys give me an example where the Prandtl number is less than 1? For mercury, Prandtl number of mercury is around 0.03. Mercury is having a Prandtl number less than 1. 0.03 is the Prandtl number. When the Prandtl number is equal to 1, we can say delta x and delta t will be equal. Very, very important concept we are discussing here. There is high chances you will find one question from this concept in your GATE 2023 examination. Yes, when the Prandtl number is equal to 1, delta x will be equal to delta t. It means A and B will overlap. The curve A and B will overlap. Like air, Prandtl number of air near atmospheric condition is almost 1. Air is an example where the Prandtl number is almost 1. When the Prandtl number is greater than 1, then delta x will be greater than delta t. For Prandtl number greater than 1, delta x will be greater than delta t. Can you give me an example where the Prandtl number is greater than 1? Prandtl number of water will be around 7. Prandtl number of water will be around 7, which is greater than 1. So in that case, delta X will be greater. So A will be velocity boundary layer and B will be thermal boundary layer. Do you understand it? Please give me thumbs up. If you have understood this concept, please guys give me thumbs up to motivate us to make us feel more energetic. That is only for laminar boundary layer, but for turbulent boundary layer, if we are talking about the turbulent boundary layer, when the Reynolds number is greater than 5 into 10 to the power 5, then delta X is equal to delta T irrespective of the Prandtl number. You should remember this concept. For turbulent boundary layer, delta X and delta T will be equal irrespective of the Prandtl number. It will not depend on the Prandtl number. Why? Because of mixing of the fluid particles, there is equal exchange of momentum and heat. In turbulent flow, the particles from one layer start mixing into another. So due to mixing of the fluid particles from one layer into another, there will be equal amount of exchange of momentum and heat across the boundary layer. So the thickness of boundary layer, velocity and thermal will be same, right? Clear? I told you, if I show you the velocity profile will always be like this. Here the velocity is u infinity, here the velocity will be 0, no slip condition. This is how the velocity keeps on growing, and outside the boundary layer du by dy is equal to 0. It is maximum near the surface. The thermal boundary layer, if Ts is greater than T infinity, thermal boundary layer will look like this. Here also dt by dy will be equal to 0 outside the boundary layer. The thermal boundary layer will be like this. And it can be shown like this. This is Ts, this is T infinity. It can be shown like this when Ts is less than T infinity. Again, outside the boundary layer, dt by dy is equal to 0. So the temperature profile can be of two types depending on whether the fluid temperature is more or the surface temperature is more. All right. So now if I define or if I write the general velocity profile and temperature profile for laminar boundary layer. So u by u infinity is equal to 3 by 2 y by delta x minus 1 by 2 y by delta x to the power 3. This equation is known as, what do we call? This equation is called as Blasius equation. What do we call this equation? This equation is known as Blasius equation, and similar to that, we can write the temperature profile. Can we write u minus 0 upon u infinity minus 0? So u corresponding to velocity u, temperature of the fluid is T, corresponding to 0 velocity, the temperature of the fluid is Ts upon T infinity minus Ts. Can we write left hand side like this? Is equal to 3 by 2 y upon, it will be delta T, minus 1 by 2 y by delta T cube. These are the velocity and temperature profile, general velocity and temperature profile for boundary layer, velocity and thermal boundary layer. Now we know velocity as a function of y. From here we develop the temperature as a function of y, and from the temperature as a function of y we can find out dt by dy. And from dt by dy, we can find out dt by dy at y is equal to 0. And from here, we can find out h, that is minus kf into dt by dy at y is equal to 0 upon delta t. That is how we can find out h, convective heat transfer coefficient. That is the connection between fluid mechanics, heat transfer, and then convective heat transfer coefficient. Getting it or not? So let us have one question. Let us discuss one question before proceeding further. I want everyone to get me the answer for this. I want everyone to reply me with any of the given options. Whether your answer is correct or not does not matter at all. But your participation highly motivates us to make the concept more simple, make the concept more beautiful for you guys. Do let me know the answer to this question. Read the question and try to get me the answer. Yes. What is your answer? Very nice, Nora Fatai. Good, good, good. Everyone, please do respond. So many people are there in the live session. I want every one of you to give me the answer to this. Every one of you. Yes, Manas, Sujis, well done. What about other? Mallesh, good, good, good. Keep it up. Bataiye, bataiye, quickly. Quick. Water is having Prandtl number 6 or 7. So the Prandtl number for water is given as 6. They may not give you the Prandtl number for water. I have already told you it is greater than 1. The Prandtl number of water is greater than 1. Flows over a flat plate which is heated over the entire length. Which one of the following relationship between hydrodynamic boundary layer thickness, that is delta, and the thermal boundary layer thickness, delta T, is true? Which is the right answer? Some people are saying B. Some people are saying D. Look, do we have any information about laminar or turbulent? Do we have any information about laminar or turbulent boundary layer? Do we have any information about the laminar boundary layer or turbulent boundary layer? No. That is why if it would have been laminar, I told you, in case of laminar only, Prandtl number delta X and delta T are related with Prandtl number, but in case of turbulent boundary layer, delta X is always equal to delta T. So option A can also be true if it would have been turbulent boundary layer. When the Reynolds number is more than 5 into 10 to the power 5, it could have been B when the boundary layer would have been laminar. So what is more appropriate answer? What is more appropriate answer? The more appropriate answer is option D. D is the right answer. It is D which is correct. D will be the right answer to this. I hope it is clear. So that is why you need to understand the question completely. It is very important. Sometimes what happens when we are in the actual examination, we have a lot of pressure to complete the paper within the time frame, and we are in such a hurry that we do not understand the question fully, and that is where the silly mistakes happens. So read the question properly, understand it, and then finally find out the correct answer which is more appropriate. That is how questions will be framed in your examination. So that was all about the external flow boundary layer theory, hydrodynamic as well as thermal boundary layer. Now let us talk about the internal flow, when the flow is in a pipe or duct. When the fluid is flowing in a pipe or duct. These are the assumptions we carry. Q is constant, steady flow. That is equal to A1 V1 is equal to A2 V2. And uniform flow means area is constant. So we can say from here V1 is equal to V2 is constant, and that can be called as average velocity. Average velocity will be constant throughout the flow. Here average velocity is same as the average velocity here, is equal to same as the average velocity here. Average velocity will be same as long as the flow is steady and uniform. So the Reynolds number, this is the laminar flow, then bottom one is the turbulent flow when the fluid particles start mixing. So it is the Reynolds number which decides the nature of the flow. What is the Reynolds number? Ratio of inertia force to viscous force, and that is how we can write Reynolds number based on hydraulic diameter, rho into average velocity into dH by mu. Or we can write it as mu by rho is kinematic viscosity or momentum diffusivity, V average into dH by kinematic viscosity. That is how the Reynolds number is defined. Here the free stream velocity will be replaced by the average velocity, and distance from the leading edge will be replaced by the hydraulic diameter. Do you know the concept of hydraulic diameter? DH? Do you know the concept of hydraulic diameter? hydraulic diameter dh, 4a by p. A is the flow area, which is normal to the flow, and p is the wetted perimeter. P is the wetted perimeter. So if the pipe is non-circular, convert it into circular pipe. If the pipe is already circular, you can see hydraulic diameter is equal to actual diameter. But if it is not circular pipe, then hydraulic diameter will be calculated by using the given formula. And then based on the Reynolds number, if the Reynolds number is less than equal to 2000, the flow in a pipe will be laminar. If it is greater than 4000, the flow in the pipe is turbulent. If the Reynolds number is less than 2000, the pipe flow will be laminar, and if it is greater than 4000, it will be turbulent flow. This is how the flow takes place in case of pipe. The fluid flow takes place. So this is the fully developed region. If you have studied fluid mechanics, in the fluid mechanics session, I have discussed about the fully developed flow. This is the fully developed region. In case of temperature also, this is the fully developed region. And this length is called as entrance length. This is called as hydrodynamic entrance length, LE, for velocity boundary layer, and this is the entrance length for thermal boundary layer. This is the fully developed flow. So this is LE for thermal boundary layer. So for thermal boundary layer, entrance length is less than the entrance length for velocity boundary layer. That can be important. The entrance length for thermal boundary layer will be shorter, because the fluid achieves the surface temperature very fast compared to the velocity variation. So the fully developed region is developed late in case of velocity profile, and for temperature profile, it develops early. That is the entrance length. So how to define the average velocity? Let us talk about the average velocity in case of flow in a pipe. Average velocity is the local velocity is replaced by a constant velocity in such a way that the flow rate from this section remains constant. The variable velocity at any section can be replaced by a constant velocity V average, such that the mass flow rate remains constant. How to write the mass flow rate? That is rho into area into average velocity. And if we go for integration, then it integration rho into dA into U. U is variable. So from here we can find out the expression for average velocity. Average velocity is 1 upon A into integration of U into dA. Mass flow rate must remain constant. The condition says from a particular section, the flow rate must remain constant. So this is how we can define the average velocity, where A is the flow area, dA is the area of the element, U is the velocity profile. U is a function of R. U is variable. If the pipe is circular, for circular pipe, area will be equal to pi r square, isn't it? And the element, area of the element dA will be equal to 2 pi r dr. And U will be a function of R. For circular pipe, if we put these values, then what will be the average velocity expression? It will be 2 by r square integration 0 to r. U, which is a function of R into dr. Isn't it? Just put the values. This will be the expression for average velocity. And if U is a function of R is given as linear, if velocity profile is given as linear, so we will assume, first of all, we will assume U is equal to some constant into R plus C2. And to find out C1 and C2, we can use the boundary condition. What are the condition? At R is equal to 0, that is the center line of the pipe, the velocity is U maximum. And at R is equal to capital R, that is the wall of the pipe, the velocity will be 0, no slip conditions. So by using these two conditions, we can find out C1 and C2 and put the value of C1 and C2 here. And then we can put U as a function of R here and do the integration to get the velocity, average velocity at any particular section. That is how we can get the average velocity at a particular section, right? Is this clear? Similarly, we define the average temperature or bulk mean temperature. In the similar manner, we can define the mean temperature of the fluid, that is called as bulk mean temperature, TB, at a particular section. Again, if you see the definition, variable fluid temperature at any section is replaced by a constant temperature in such a manner that the heat flow rate remains constant. The rate of heat flow must be same from this section. The heat flow rate must be same. Q must be constant. So how to write Q? How heat flow rate takes place, that is m dot mass flow rate into Cp into mean temperature. Here mean temperature is, let us say, TB. So the heat flow rate is mCt is equal to, we can go for integration, that is dm dot into Cp into T. So Cp getting cancelled out. What is the mass flow rate? That must remain constant. That is the definition. Heat flow rate remains constant. So what is mass flow rate? That is rho into A into V average. That is the mass flow rate into TB is equal to integration. What is dm dot? Rho into dA into U. That is dm dot for the element into T. So if you simplify, rho and rho are getting cancelled out. So TB will be equal to 1 upon area into average velocity, integration of U into T into dA. Heat flow rate must remain constant. That is the condition. To define the average temperature at any section, heat flow rate must remain same. The temperature profile can be drawn like this also. The temperature profile can be drawn like this also. Again, it depends on when the fluid temperature is greater than the surface temperature, the temperature profile will be like this. And when Ts is greater than fluid temperature, then the temperature profile will be drawn like this. There is two possibilities to draw the temperature profile, either this or this, depending on which temperature is more, fluid temperature or the surface temperature. All right. For circular pipe, if the pipe cross section is circular, A is equal to pi r square, dA will be equal to 2 pi r into dr, and U is a function of r, and T will also be a function of r. If you put these values, then the mean temperature at any section, 2 upon V average into r square, integration 0 to r, U, which is a function of r, T, which is also a function of r, into r into dr. That is the formula for bulk mean temperature. That will be the formula for mean temperature. Correct? And for linear temperature profile, for T is a function of R is linear, what we do is we assume T is equal to C1R plus C2. To find out the value of C1 and C2, we need boundary condition. What are the boundary condition? At R is equal to 0, center line. Can you let me know what is the temperature? At R is equal to 0, temperature of the fluid is. At R is equal to 0, what will be the temperature of the fluid? At R is equal to 0, what will be the temperature of the fluid? It can either be maximum or minimum, isn't it? At R is equal to 0, center line, the temperature can either be maximum. It is maximum here. And here it is T minimum, depending on whether fluid temperature is more or the surface temperature is more. Yes, it can either be maximum or minimum. There are two possibilities. And at R is equal to capital R, that is wall of the pipe, temperature of the fluid is equal to Ts. Fluid temperature will be equal to Ts. is equal to surface temperature. So by putting these two conditions, we get C1 and C2, and by getting C1 and C2, put in this expression, we get the temperature profile, and put the temperature profile here to get the mean temperature, bulk mean temperature at any section. That is how the analysis will be done. I hope this is clear. All well? Now let us talk about the energy balance equation. Now let us talk about the energy conservation equation. Very, very important. Now let us talk about the energy conservation equation or energy balance equation between 2 points 1 and 2. Let us say this is the inlet section 1, the fluid is entering, and this is the outlet section 2 where the fluid is leaving. Inlet and outlet. If we apply the energy conservation equation between inlet and outlet, this is our control volume. This is our control volume. The system is the fluid. This is our system. And if Ts is greater than Tf, if the surface temperature, then the fluid will get heated. Heating of fluid will take place. Heating of the fluid will take place. So the surface will heat the fluid like this. The heat will flow into the fluid from the surface. Isn't it? So for the system, what is the energy conservation equation? Q in plus Q generated. Do you remember this expression? Q out plus Q stored. Do you guys remember this expression? Q in plus Q generated is equal to Q out plus Q stored. Heat is entering into the system through the surface. There is no heat generation in the system. There is no heat generation. There is no concept of heat generation. And there is no heat leaving from the fluid, because fluid is having less temperature compared to the surface temperature. So heat will always flow from high temperature to low temperature. So there is no heat out, and Q stored will be there. That is change in internal energy between section 1 and 2. So we can say here the mean temperature is TB1. Here the mean temperature of the fluid is TB2. So what is Q in? That is due to convection. The mode of heat transfer will be convection. So we can say H into surface area available for convection into delta T is equal to, how to write rate of change of energy storage? M dot mass flow rate into Cp into bulk into temperature difference for the fluid, because it is heat stored in fluid. So how to calculate the change in internal energy of the fluid? That is temperature difference for the fluid. That is TB2 minus TB1. Do you agree or not? Do you understand this expression or not? What is delta T here? Who will tell me what is delta T? If I ask you the surface temperature, this is the surface temperature, the temperature which is in contact with the surface temperature for the convection. So we can write H into, it will be pi into D into L if the length of the pipe is L between 1 and 2. Pi dl will be the temperature of the surface. Into delta T means surface temperature minus fluid temperature. This is average temperature of the surface minus average temperature of the fluid is equal to mass flow rate, can be written as density into discharge into Cp into TB2 minus TB1, or Q can be written as area into velocity. This is how we can apply the energy conservation equation if the surface temperature is greater than fluid temperature. Average surface temperature is, let us say, Ts. What is the fluid average temperature? Average temperature of the fluid is equal to TB1 plus TB2 by 2. Inlet and outlet, the mean temperature of the fluid between inlet and outlet is the average of TB1 and TB2. ये वाला बताइए. Is this concept clear or not? Is this concept clear or not? Everyone, please do let me know. Is this clear or not? Give me thumbs up. Give me yes. Drop a yes in the comment section if it is clear. Or if you have any doubt, you can just let me know. Very, very important concept. There are so many questions previously asked in GATE examination from this portion. Fluid is our system. So if we apply the energy balance for the system, there are 4 terms I told you in the morning. Q in, Q generated, Q out, Q storage. So out of them, two terms will be 0. If the fluid temperature is more than the surface temperature, then what will happen? The heat will leave from the surface. Q out will be equal to minus Q stored. So it will be H into pi dl into TF minus TS. Rho into Q into Cp into it will be TB1 minus TB2. That will be the only difference. Right? Can you write for fluid temperature greater than surface temperature, cooling of the fluid will take place. Cooling of the fluid will take place. Now let us enter into the important formula, important correlation, which will be helping you to apply in your examination. Important correlations or important relationship for. First, we will talk about the forced convection or artificial convection. In forced or artificial convection, I have already told you pressure gradient and inertia force. Pressure gradient and inertia force are responsible for forced convection or artificial convection. Here there are three numbers which are interrelated with each other. Nu is called as Nusselt number. Re is called as Reynolds number. And PR is called as Prandtl number. These are the three dimensionless number which define forced convection. These are the three dimensionless numbers. Nusselt number is a function of Reynolds number multiplied by Prandtl number. First of all, let us talk about the Prandtl number. What exactly is the Prandtl number? I have already told you. Prandtl number is the fluid property which is relevant both in the forced convection as well as natural convection. Prandtl number will be used in natural convection as well as forced convection. It represents the ratio of momentum diffusivity. What is momentum diffusivity? It is called as kinematic viscosity. Momentum diffusivity is kinematic viscosity. Nu to the thermal diffusivity. What is thermal diffusivity? That is alpha. The ratio of momentum diffusivity to the thermal diffusivity of the fluid. Both are property. Thermal diffusivity I have told you in the morning. Momentum diffusivity you must be knowing from your fluid mechanics lectures. So it will value indicates the relative ability, because it is a property, that is why it gives the relative ability of the fluid in exchanging momentum and heat across the boundary layer. And in laminar flow over the plate or in laminar boundary layer, its value implies the relative growth rates of velocity boundary layer and thermal boundary layer. I told you delta X and delta T are related with Prandtl number in case of laminar boundary layer. So it is the connecting link between velocity boundary layer and thermal boundary layer. It is the connecting link between velocity boundary layer and thermal boundary layer. So Prandtl number is the ratio of momentum diffusivity to the thermal diffusivity. This is the Prandtl number. Kinematic viscosity upon alpha. Kinematic viscosity is mu by rho. Alpha is K by rho C. So this is the mathematical expression for Prandtl number. Cp, specific heat. Specific heat. And mu is the viscosity. K is the thermal conductivity of the fluid. It is defined for the fluid. So K is the thermal conductivity of the fluid, or we can write Kf. Mu Cp by Kf. That is Prandtl number. And I have already told you about this, the significance of Prandtl number in laminar boundary layer. In laminar boundary layer, if Prandtl number is less than 1, delta X will be less than delta T. So this is thermal boundary layer, this is velocity boundary layer. If Prandtl number is equal to 1, delta X is equal to delta T. So both A and B are equal. If Prandtl number is greater than 1, then this is velocity boundary layer. Delta X will be greater than delta T. So this is velocity boundary layer and this is thermal boundary layer. But if the flow is turbulent, for turbulent boundary layer, delta X is equal to delta T irrespective of Prandtl number. For turbulent boundary layer, delta X and delta T will be equal irrespective of the Prandtl number. All right. Clear? Then comes the Nusselt number. Try to understand the Nusselt number. What is Nusselt number? It is not a fluid property. It is not a fluid property. It is an experimentally determined, again, complex parameter. Nusselt number is again experimentally determined complex parameter. It is also relevant in both forced and free convection. It represents the ratio of conductive thermal resistance to the convective thermal resistance, both being offered by the fluid itself, because they are the parameters defined for the fluid only. These are the parameters which are defined for the fluid only. So it represents the ratio of conductive resistance of the fluid to the convective resistance of the fluid. Why fluid is important? Because there is one more number which is the ratio of conductive resistance to convective resistance. What that number is? What is that number? The ratio of conductive resistance to convective resistance. Can you let me know? Or we can write it as Q convection divided by Q conduction. Because in fluid, conduction and convection both are taking place. Yes, Biot number is another dimensionless number, which is the ratio of conductive resistance to convective resistance. But in Biot number, conductive resistance is for the solid body and the convective resistance is for the fluid. But Nusselt number represents the ratio of conductive and convective resistance, both being offered by the fluid. Or we can write, because Q is inversely proportional to thermal resistance, we know. So the ratio of convective heat transfer rate to the conductive heat transfer rate across the boundary layer or across the fluid layer, that is called as Nusselt number. So it is also known as dimensionless convective heat transfer coefficient. Why do we call it as dimensionless convective heat transfer coefficient? Because it is a dimensionless number. Q is, or we can say, because Nusselt number is directly proportional to H. So it can also be known as dimensionless convective heat transfer coefficient. And for the given condition, the rate of heat transfer by convection is directly proportional to Nusselt number. Why? Because Q is directly proportional to H and H is proportional to Nusselt number. So from here we can say Q convection will be proportional to the Nusselt number. More will be the Nusselt number, more will be the convection heat transfer rate compared to conduction heat transfer rate. More Nusselt number implies more convection, less Nusselt number implies less convection across the boundary layer or across the fluid layer. All right. For external force convection, local Nusselt number is defined NUX is equal to HX into X by KF. This is called as local Nusselt number. Why it is called as local Nusselt number? Because it is a function of X, where HX is the local convective heat transfer coefficient, local convection heat transfer coefficient. Hx is the local because it is also a function of X. X is the distance from the leading edge. X is distance from leading edge of the plate in flow direction. We can also define the average convective heat transfer coefficient, that is Nu bar. That is Nu bar is equal to H bar into L by Kf. That is not a function of X. That is called as average convective heat transfer coefficient. Average Nusselt number, sorry, average Nusselt number. And what is H bar here? We can write H bar as average convection heat transfer coefficient, which is not a function of X. And L is the length of the plate. Plate length. L is the length of the plate. Right? For internal force convection, Nusselt number based on hydraulic diameter we define. Nusselt number based on hydraulic diameter is equal to H into dH by Kf, where dH is equal to 4A by P, hydraulic diameter. This is how Nusselt number is defined for internal force convection or flow in a pipe or duct. Now, the important empirical relationship. These are the important part of convection. These are experimentally determined expressions. There is no mathematical proof as such. So you need to memorize these expressions. For laminar flow over a flat plate, when the local Reynolds number is less than 5 into 10 to the power 5. For laminar flow over a flat plate, or for laminar boundary layer, when the Reynolds number is less than 5 into 10 to the power 5, the first expression is for velocity boundary layer, 5x upon under root of Rex. That is coming from the fluid mechanics. Delta x is equal to 5x upon under root of Rex. From here, we can develop n number of relationship. Delta x is directly proportional to x to the power 1 by 2. Isn't it? Because there is a x in the denominator also, root x is in the denominator, x is in the numerator. Or delta x is inversely proportional to under root of u infinity. Because the Reynolds number is given by rho u infinity x by mu, or we can write u infinity x by kinematic viscosity. Or we can write delta x is directly proportional to under root of kinematic viscosity. These are the various relationships. The question will be solved by using, or the question will appear in the examination based on this relationship. If you are comfortable, if you know this expression for laminar boundary layer, 5 is this 5 numerical value can be changed. This 5 is actually Blasius constant. This is called as Blasius constant. Sometimes they mention that the Blasius constant is taken as 5 or 4.64. We can take 4.64 also. So the numerical value is not important, because depending on the velocity profile, the numerical value will change, right? So first expression from the fluid mechanics. Or we can develop another, we can write another expression. Delta x is inversely proportional to under root of Re, for x is constant. For a particular x at a particular location, delta x is inversely proportional to root of Re, under root inversely proportional to under root of Re. N number of relationship you can develop on your own based on this. This is formula number 1. The second formula is for laminar boundary layer, the ratio of delta x by delta t. How they are related with Prandtl number, that is 1 by 3. The second formula, very, very important, that is heat transfer. Delta x by delta t is given by Prandtl number to the power 1 by 3. And from here we can say, if the Prandtl number is less than 1, then definitely delta x will be less than delta t. If the Prandtl number is equal to 1, then delta x is equal to delta t. If the Prandtl number is greater than 1, then delta x will be greater than delta t. Second formula. This is the exact expression. This is the exact expression. If the, for Prandtl number, for particular value of Prandtl number, we can find out delta x if delta t is given. Out of these 3 parameters, any 2 parameters are given to you, you can easily find out the third one. The next one is the fluid friction, local skin friction coefficient, that is given by tau naught upon rho u infinity square by 2. Again coming from the fluid mechanics. Again coming from the fluid mechanics. That is equal to 0.664 upon under root of Rex. That is a function of x. That is called as local friction coefficient. Why it is called as local friction coefficient? Because it is a function of x. The surface shear stress divided by the dynamic pressure. So can you let me know how this is related? Cfx is inversely proportional to root x, isn't it? It is proportional to x to the power minus 1 by 2. Cfx is inversely proportional to x to the power 1 by 2. That is formula number 3. And the next formula is average drag coefficient. That is 1 by L integration of 0 to L Cfx into dx. And for laminar boundary layer, it is twice of Cf at x is equal to L. CD, it is not a function of x. That is called as average drag coefficient. That is called as average drag coefficient, which is twice of CF at x is equal to L. If we write CD is equal to 2 into 0.664 upon under root of REL, we will use L in terms of in place of x. It is called as average drag coefficient, which is independent of x. So these are some formula, and then one more formula. Fifth one is Nusselt number is directly proportional to Reynolds number to the power 1 by 2 into Prandtl number to the power 1 by 3. This is how Nusselt number is related with the Reynolds number and Prandtl number for laminar flow over a flat plate. Or if we find out the local Nusselt number, that is equal to, exact expression is 0.332 into Reynolds number, local Reynolds number to the power 1 by 2 into Prandtl number to the power 1 by 3. And this Nusselt number can be equated with, can we write it as Hx into x by kf? It is a function of x. That is called as local Nusselt number. That is again for the heat transfer. Local Nusselt number is given by this expression. Can you let me know how the local Nusselt number and x are related? How the local Nusselt number and x are related? That is x to the power 1 by 2, isn't it? How Hx and x are related? Can you let me know how Hx and x are related? Hx and x, how they are related with each other? Hx and x, how they are related with each other? Can you let me know? 1x is there and root x is there. So root x by x. So x to the power minus 1 by 2. X to the power minus 1 by 2. Yes, 1 by root x is the answer. And the average Nusselt number is equal to average H into L by Kf is equal to twice of Nusselt number at x is equal to L, where H bar is equal to twice of H at x is equal to L for laminar boundary layer over a flat plate. Average Nusselt number is twice of Nusselt number at x is equal to L. And one more expression, if I write Stanton number into Prandtl number to the power 2 by 3 is equal to Cfx by 2. That is one more expression which connects the fluid friction and the heat transfer coefficient. That is another relationship. What is Stanton number? Do you know what is Stanton number? This is called as local Stanton number. What is Stanton number? The ratio of Nusselt number to the product of Reynolds number into Prandtl number. That is called as local Stanton number. Stanton number is Nusselt number divided by Reynolds number into Prandtl number. So all the fluid properties which are used in the expression, they must be used at the film temperature. What is the meaning of film temperature? Film temperature means the average of, what is the film temperature? Is equal to Ts plus T infinity by 2. All the properties, all the fluid properties must be used at the film temperature. That is the average temperature of Ts and T infinity. That will be the average temperature of Ts and T infinity. Are these expressions clear to everyone? Next is turbulent flow over a flat plate. When the Reynolds number is greater than 5 into 10 to the power 5, then the first formula, delta x is equal to delta t is equal to 0.376 upon Rex to the power 1 by 5. Delta x and delta t will be equal, and the expression will be 0.376 into upon Rex to the power 1 by 5. So we can say delta x is equal to delta t is proportional to x to the power minus 1 by 5. Sorry, what is the expression? Here it will be 0.376 x 0.376 x upon Rex to the power 1 by 5. So it is proportional to x to the power 4 by 5. One relation. The second relation, Cfx is equal to 0.059 upon Rex to the power 1 by 5. So Cfx is proportional to x to the power minus 1 by 5. And CD will be equal to 5 by 4 into Cf at x is equal to L. Average drag coefficient, which is not a function of x. Average drag coefficient will be 5 by 4 into Cf at x is equal to L. And finally, the next expression, fourth expression, Nusselt number is directly proportional to Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. And if we write local Nusselt number 0.03 into Rex to the power 4 by 5 into Prandtl number to the power 1 by 3 is equal to Hx into x by kf. It is a function of x. That is so can you let me know how Nusselt number, local Nusselt number and x are related? X to the power 4 by 5, Nusselt number is proportional to x to the power 4 by 5, isn't it? How Hx and x are related? How Hx and x are related? It is proportional to x to the power 4 by 5 upon x. So it is x to the power minus 1 by 5, isn't it? So average Nusselt number is equal to 5 by 4 into Nusselt number at x is equal to L, or average convective heat transfer coefficient is 5 by 4 into H at x is equal to L. It is for turbulent flow over a surface. We are talking about turbulent flow over a surface. Sorry. We are talking about turbulent flow over the surface, over the flat plate. These are the formula for turbulent flow over a flat plate. Clear? So for laminar flow over a flat plate, you can memorize these formula like this. Reynolds number to the power 0.5, Prandtl number to the power 1 by 3. For turbulent flow over a flat plate, Nusselt number is 0.03, Reynolds number to the power 0.8, that is 4 by 5 into Prandtl number to the power 1 by 3. That is what you can memorize. The numerical values are not important as such. The numerical values are not important, but the relations are very, very important. That is how the boundary layer growth will take place. Depending on the Reynolds number, this is laminar part of boundary layer, this is turbulent part of boundary layer. Right? Now let us talk about the internal flow. Now some empirical relations for internal flow. For internal flow, Reynolds number is given by rho into V into dH by mu. Reynolds number is given by rho into V is the average velocity into dH by mu, where dH is equal to 4a by p. That is what we have already discussed. And average velocity is given by 2 by r square integration 0 to r u as a function of r into r dr. Bulk mean temperature is equal to 2 upon V average into r square. That is what I have already written. Integration 0 to r, u as a function of r, t as a function of r into r dr. These are the parameters. And for Reynolds number less than 2000, the flow is laminar. When the Reynolds number based on hydraulic diameter is less than 2000, it is laminar. In case of laminar flow, if we write the Nusselt number, so Nusselt number based on hydraulic diameter is equal to h into dH by kf is equal to constant. For laminar flow in a pipe, Nusselt number is constant. And the value of this constant will be equal to 4.36 for constant heat flux. When the heat flux is constant, the value is 4.36, and the value of this is 3.66 for surface temperature is constant. If Q dash is constant, then the surface temperature and the bulk temperature of the fluid are linear function of x. And when the surface temperature is constant, then TB is a function of x, that is exponential. It will be exponential. So Nusselt number, either you take 4.36 or 3.66, will be dependent on whether the flux, heat flux is constant or the surface temperature is constant. Yes, भौमिक, ये याद रखना पड़ेगा. ये याद हो जाएंगे अगर 4 बार, 5 बार, 10 बार अगर आप इन फॉर्मूले को देखेंगे तो you will be able to memorize them. ये empirical relation है, इनका कोई proof नहीं है. You have to memorize these expressions. इसलिए तो रिवाइज करवा रहा हूं. फॉर टर्बुलेंट फ्लो इन ए पाइप, व्हेन द रेनॉल्ड नंबर बेस्ड ऑन हाइड्रोलिक डायमीटर इज ग्रेटर देन 4000, देन नसल नंबर is directly proportional to Reynolds number to the power 4/5 into Prandtl number to the power n. Or we can say Nusselt number based on hydraulic diameter, that is h into dh by kf, is equal to 0.03 Reynolds number to the power 4/5 into Prandtl number to the power n, and the value of n will be equal to, the value of n will be decided by, n will be equal to 0.4 if the surface temperature is greater than the fluid temperature, if there is a heating of the fluid taking place. For the heating of the fluid, n will be 0.4 and it will be 0.3 if the surface temperature is less than the fluid temperature, cooling of the fluid. For cooling of the fluid, the value will be 0.3. For heating of the fluid, it will be, the value of n will be 0.4, right? So that is how, this is the mathematical expression for turbulent flow in a pipe. So for laminar flow, what you need to remember, for laminar flow in a pipe, it is 4.36 or it can be 3.66. And for turbulent flow, it is somewhat like this. You can remember this. For turbulent, this is for turbulent flow in a pipe, and this is for laminar flow in the pipe. Now, there is a question on the screen. Please try to solve this question and then we will move to the natural convection and then heat exchanger. Natural convection and then heat exchanger. Give me the answer for this question, everyone. Give me the answer for this one. Read the question carefully and do let me know the answer to this. Everyone, what is the correct answer? For a hydrodynamically and thermally fully double laminar flow through a circular pipe of constant cross section, the Nusselt number at constant wall heat flux is NUQ, and that is constant wall temperature is NUT are related as. So when the heat flux is constant, the value of Nusselt number is, at constant heat flux is 4.36. Nusselt number at constant temperature is 3.66. So what is the correct answer? Option D. That is the question asked in GATE examination. That is how the question can be asked. And now let us talk about the natural convection. Next is artificial or natural convection. Two factors are involved. One is density gradient and bind force. Density gradient and bind force. So in natural or free convection, Nusselt number is a function of Grashof number. Here it is Grashof number. Grashof number multiplied by a function of Prandtl number. So in forced convection, We talk about Reynolds number, which is the ratio of inertia force by viscous force. But in case of free convection, there is no inertia force. So buoyant force divided by viscous force is called as Grashof number. Here we define Grashof number, the ratio of buoyant force to viscous force. And in force convection, we define the Reynolds number, that is the ratio of inertia force to viscous force. What is Grashof number? It is again not a fluid property. It is relevant only in free or natural convection. It is only valid in natural convection. Now it represents the ratio of buoyant force to viscous force. The ratio of buoyant force to viscous force is the Grashof number, and its value indicates the type of the fluid motion in natural convection. If the Grashof number is less than 10 to the power 9, then the flow or the motion will be laminar, organized. And if the Grashof number is greater than 10 to the power 9, then it is turbulent. For small value of Grashof number, the fluid motion is laminar, organized, and for large value, it becomes turbulent. Now, fluid motion over a vertical surface, we define the local Grashof number is given by rho square g beta delta t x cube by mu square. That is the mathematical formula, or g beta delta t x cube by kinematic viscosity square. That is the local Grashof number because it is a function of x. Because it is a function of x. Rho is the density, g is the acceleration due to gravity, delta t is the bulk temperature difference. Delta t is the bulk temperature difference. X is the distance from the leading edge in the direction of motion. Delta T is bulk temperature difference. It can be Ts minus T infinity for Ts greater than T infinity, or it can be T infinity minus Ts for T infinity greater than Ts. That is called as bulk temperature difference. Mu is the viscosity, nu is the kinematic viscosity. X is the distance from the leading edge in the flow direction. Leading edge. Then we define average Grashof number. Average Grashof number is given by rho square g beta delta t into LC cube upon mu square. Or we can write g beta delta t into LC cube by kinematic viscosity square. That is average Grashof number. What is LC? LC is called as characteristic length. Here it is not a function of x. It is not a function of x. We define the characteristic length. What is characteristic length? Do you know the significance of characteristic length? Characteristic length is the distance over which the thermal boundary layer is allowed to grow in case of natural convection. It is the length over which the thermal boundary layer is allowed to grow in case of free or natural convection. So in case of vertical surface, LC will be the vertical dimension. In case of vertical surface, it is the vertical dimension. In case of inclined surface, LC is the vertically projected dimension. If it is inclined surface, then it is vertically projected dimension. And in case of horizontal surface, because the boundary layer will not grow, then LC will be equal to surface area upon perimeter. Area by perimeter. Surface area upon wetted perimeter is the characteristic length. A by P is the characteristic length. That is how we can define the characteristic length for the given. If there is a plate kept like this, if the plate is kept like this is L and B, then characteristic length will be equal to B. If the plate is kept like this is B, this is L, then characteristic length will be L. Vertical dimension. It is the vertical dimension. And then we define beta. What is beta? Beta is called as coefficient of thermal expansion or volumetric expansivity. volumetric expansivity. How to define beta? You must have studied in thermodynamics. Beta is given by 1 by V dV by dt at constant pressure. It is a thermodynamic property. You must have studied beta in thermodynamics. Cp minus Cv. No, Malays, there will not be any practice session today. We will plan some other day. Thermodynamic property of the fluid, which is defined as the change in volume, per unit change in temperature at a constant pressure. What is the unit of beta? What is the unit of beta? Can you let me know the unit of beta? Or in terms of density also we can write minus 1 by rho into d rho by dt at constant pressure. Or it represents the variation of fluid density with temperature at a constant pressure. I told you, due to the temperature, when the particle gets heated, when the fluid particle gets heated, then what happens? Then it expands and the density decreases. So increasing the temperature will decrease the density. So beta is the parameter which defines how much will be the change in the density due to unit change in temperature. That is called as, hello Sharma ji, bada late hai aap? थोड़ी देर और next half an hour we will wrap it up. इसके बाद heat exchanger I will take last half an hour. Please guys, do focus, keep your momentum energy high, because last half an hour we will complete our whole syllabus of heat transfer. So the unit is Kelvin inverse. The unit is Kelvin inverse. It is the property. Beta is the property, thermodynamic property of the fluid. For perfect gas, we can define, or we can conclude beta to be 1 upon film temperature. Beta is given by 1 upon film temperature. And what is the film temperature? I have already told you Ts plus T infinity by 2. That is the average temperature of the surface and the fluid. Acha, you are writing the mock test. Acha, good. Keep yourself busy, either in the mock test, practicing the numericals, or revising the theory for the entire month. This whole month, keep yourself busy as much as possible. Do not waste your time even a single minute. It is very, very important. The more you keep yourself busy, the more negative thoughts will be away. The more you will be free, the negative thoughts will come into your mind, and that will demotivate you. So to keep yourself motivated, try to be as busy as possible throughout your entire day, so that you do not get time to get yourself disappointed, demotivated. That is the thumb rule. So in general, beta for gas is more than the liquid, than the solid. So this is how we can define beta. And the final expression for natural convection, Nusselt number is given by C, some constant which is always less than 1, into Grasov number multiplied by Prandtl number to the power m. Or Grasov number into Prandtl number is called as Rayleigh number. What is this called? Rayleigh number is the product of Grasov number and Prandtl number to the power m. And for laminar motion, the value of m will be equal to 1 by 4 when the Grasov number is less than 10 to the power 9. And for turbulent motion, m will be equal to 1 by 3 when the Grasov number is greater than 10 to the power 9. For turbulent motion, the Grasov number, the value of m exponent will be 1 by 3, and for laminar motion it will be 1 by 4. Acha Malays, yes, I will try to wrap it up. This is the velocity profile. There will be velocity profile, but velocity here will be 0. Velocity here will be 0, velocity here will be 0. U will be 0. So the velocity profile will be something like this, and the temperature profile can either be this, or the temperature profile can be like this. This is how the temperature profile can be shown. So that completes our discussion. There is a question on the screen. Please do solve this question and let me know the answer. And then I will move to the heat exchanger. After this question, The next is heat exchanger. Can you solve it? Can you guys solve it? And the final topic is heat exchanger. I will try to wrap it up as fast as possible. Can you solve it? The average Nusselt number is laminar natural convection. When it is laminar, M will be equal to 1 by 4. You must remember, M will be equal to 1 by 4. From a vertical wall at 180 degree Celsius with a still air, that is at 20 degrees Celsius, is found to be 48. If the wall temperature becomes 30, all other parameters remaining same, the average Nusselt number. So what you need to do is Nusselt number as a function of delta T. Bulk temperature difference we need to develop. So Nusselt number is given by, is directly proportional to Grashof number into Prandtl number to the power 1 by 4. Prandtl number does not involve delta T. It is the Grashof number. So Grashof number is directly proportional to delta T. So Nusselt number is directly proportional to delta T to the power 1 by 4. That will give you the answer. That will give you the answer, isn't it? So we can say Nusselt number in second case upon Nusselt number in first case is equal to delta T in second case. Delta T in second case is 30 minus, 30 minus 20 upon 180 minus 20 to the power 1 by 4. What is the Nusselt number? What is the answer? Are you getting C or not? Are you guys getting C or not? Isn't it C, option C? C will be the answer. Right? Are you getting C? Nusselt number 1 is given 48. This is 48 given. So now the final chapter, the last chapter of your heat transfer, the heat exchanger. There are two fluids which exchanges heat with each other. There are two fluids. One is the hot fluid. So hot fluid gives the heat to the cold fluid. So the temperature of the hot fluid decreases, and this is the cold fluid. The temperature of the cold fluid increases. The heat exchanger are the instrument or the devices which exchanges heat from high temperature, which exchanges heat between the hot fluid and the cold fluid. In the process, hot fluid temperature decreases and the cold fluid temperature increases. So we will be talking about the surface contact heat exchanger. We will be talking about the surface contact heat exchanger, that is called as recuperator. First of all, let us have the classification of these heat exchanger. Based on, in surface contact heat exchanger, both the fluids flow simultaneously through the surface. This is the surface. On the top of the surface, hot fluid is flowing. On the bottom of the surface, cold fluid is flowing. So the exchange of heat is taking place. Hot fluid gives the heat by convection to the surface. Then there will be conduction, and the surface will give the heat to the cold fluid by convection. So it is combined mode of heat transfer. So first classification is based on the design. You already know. I will quickly discuss the theoretical part based on the design or based on the construction. One is called as concentric tube type or double pipe heat exchanger. There are two concentric pipes. In one pipe, hot fluid is flowing. In another pipe, cold fluid is flowing. That is how concentric tube type. And the other type of heat exchanger is shell and tube type. There is a bigger pipe that is called as shell, and there are number of tubes. That is how, that is called as multi-pass heat exchanger. Based on the design, these are two types of surface contact heat exchanger. This is double pipe heat exchanger. There are two pipes. In one pipe, hot fluid is flowing like this, and it is coming like this. And in another pipe, cold fluid is entering and cold fluid is leaving. And shell and tube type are like this. In one, the bigger pipe or the shell, one fluid is flowing, and in the another pipe, the another fluid is flowing like this. The flow fluid is like this. These are called as baffles. These are called as baffles. Baffles are provided in case of shell and tube type heat exchanger. What is the objective of providing the baffles? Can anybody let me know why the baffles are provided? Baffles are provided to hold the tubes with equal spacing. That is one objective baffles fulfill, and forcing the shell side fluid to flow across the heat exchanger, improving the performance. Baffles are provided to make the shell side fluid to flow across the heat exchanger, and that is how the performance will get increased. That is the first classification. The second classification is based on the relative direction of the fluid flow. That is only for double pipe. That is only for double pipe or concentric tube type. Parallel flow or co-current flow, when the fluids are flowing parallel to each other and in the same direction, that is called as parallel flow or co-current flow heat exchanger. Counter flow heat exchanger, when these are the two double pipe, these can be only double pipe. Counter flow heat exchanger, when the fluids are flowing opposite to each other and parallel and opposite. And the cross flow is multipass heat exchanger. Both fluids flow perpendicular to each other. If one fluid is flowing in positive x direction, another fluid is flowing in y direction. That is how, based on the relative direction of the fluid flow, we can define the surface contact heat exchanger. And you can see counter current or counter flow heat exchanger, one fluid is flowing like this, another fluid is flowing like this. Parallel flow, both the fluids are flowing parallel to each other in the same direction. This is called as cross flow. Hot fluid is flowing like this, cold fluid is flowing like this. This is cross flow. Now for parallel flow heat exchanger, let us say this is the hot fluid and this is the cold fluid. The hot fluid is entering at temperature TH1. Its temperature is decreasing and it is leaving at TH2, outlet temperature of the hot fluid. Cold fluid is entering at a temperature TC1. This is the cold fluid, and leaving at TC2. When it is a parallel flow heat exchanger, TC2 is always less than TH2. This is the temperature profile for parallel flow heat exchanger. This is how the temperature profile drawn. For counter flow heat exchanger, hot fluid is flowing in positive x direction, but the cold fluid is flowing in negative x direction. So this is TH1, TH2, inlet and outlet temperature of hot fluid. That is hot fluid, and the cold fluid is moving. This is TC1 and this is TC2. So delta TH can be, we can write delta TH is equal to TH1 minus TH2, and delta TC, temperature difference for the cold fluid, is TC2 minus TC1. In case of counter flow heat exchanger, TC2, there is no condition for TC2. In case of counter flow heat exchanger, there is no condition for TC2. TC2 can be less than equal to greater than TH2. It can even be greater than TH2. That is counter flow heat exchanger, right? Let us talk about the various performance parameter. In case of heat exchanger, there are two performance parameters. One is thermal performance. That is heat load or thermal capacity of the heat exchanger. Q must be high. Must be high for a given size. The more is the rate of heat transfer, better will be the thermal performance. And another is economic performance parameter. That is the size or area of the heat exchanger, that must be low. Must be low for a given capacity. For a particular capacity, lesser is the size of the heat exchanger, better will be the economic performance. So if we compare for a particular size, for area is constant, if we compare, then what we will get, Q for counter will be more than Q for cross flow or multipass, and then Q for parallel flow heat exchanger. So counter flow is best heat exchanger. For a particular thermal capacity, we can say area of the counter will be less than area of the cross flow and then area of the parallel flow. So counter flow, it is the best heat exchanger compared to parallel flow. Parallel flow is the worst heat exchanger, and counter flow will be the best heat exchanger in terms of thermal as well as economic performance. The last classification is based on the phase change. Condenser, when hot fluid is undergoing a phase change. So if hot fluid is undergoing a phase change, we can say TH1 is equal to TH2. Or we can say delta TH is equal to 0. That is called as condenser. Evaporator, when cold fluid, evaporator, or we can call it as boiler as well. When cold fluid is undergoing a phase change, TC1 is equal to TC2, or we can say delta TC is equal to 0. And cascade heat exchanger, delta TH is equal to delta TC, both will be 0. When both the fluids are undergoing phase change, that is cascade heat exchanger. So whenever there is a phase change in a fluid, its temperature remains constant. TH1 will be equal to TH2. If hot fluid is undergoing a phase change, TH1 is equal to TH2, and cold fluid is undergoing a phase change, TC1 is equal to TC2. And when there is a change in temperature in the fluid, the phase remains same. So for condenser means delta TH is equal to 0. It will be hot fluid curve will be horizontal line, and cold fluid curve will be like this. And for evaporator, delta TC is equal to 0. So this is the cold fluid, this is the hot fluid. That is how the temperature curve will be drawn. And for condenser and evaporator, if area is constant, for a constant area, we can say Q for counter flow condenser is same as Q for cross flow condenser is equal to Q for parallel. There is no change in the rate of heat transfer if there is a phase change. For Q is equal to constant, again there is no change in the area. Area of counter will be same as area of cross, will be same as area of parallel. So what we can say, if there is a phase change in any one of the fluid, the relative direction of fluid flow becomes insignificant as far as their performances are concerned, whether it is economic performance or thermal performance. Before going for the analysis part, the final concept I would like to discuss, that is fouling of a heat exchanger. Do you know what is fouling? Fouling is of a heat exchanger. Do you know what is fouling? Fouling can be observed in old heat exchanger of all the types. What is fouling? It is the formation of scale on the heat transfer surface based on due to calcium based salt deposition. So due to salt deposition, that provide an extra resistance to the heat flow, so Q decreases. That is why it is undesirable. The rate of heat transfer decreases due to fouling. And that is why it is undesirable, because it reduces the rate of heat transfer or thermal capacity of heat transfer. So it should be minimized. Fouling should be minimized by regular maintenance of the heat exchanger. It should be minimized by regular maintenance. All right. There is a term defined that is called as fouling factor. Fouling factor. What is fouling factor? It is the resistance offered by the fouling. It is the measure of thermal resistance. It is the measure of thermal resistance due to fouling. The measure of thermal resistance due to fouling is known as fouling factor. So fouling factor is equal to 1 upon HF. Fouling factor is equal to 1 upon HF, that is equal to A into RF. The unit of fouling factor is equal to meter square Kelvin per unit watt. That is fouling factor. Meter square Kelvin per unit watt is fouling factor. And RF can be called as fouling thermal resistance. fouling thermal resistance. That is Kelvin per unit watt. And HF is fouling thermal conductance. That is watt per meter square Kelvin. Or we can call it as fouling heat transfer coefficient. It can be called as fouling heat transfer coefficient. That is HF. So that is all about the fouling in a heat exchanger. And the last part in our discussion is the analysis of the heat exchanger. There are three ways in which heat exchangers are analyzed. One is the energy conservation equation between hot fluid and cold fluid. Q in is equal to Q out. Because there is no heat generation, there is no heat storage. The rate of heat transfer remains constant. So we can say Q, the rate of heat transfer, is equal to m dot h Ch into Th1 minus Th2. That is it should not be Q in minus Q out, or it should be actually Q in is equal to Q stored. That is equal to m dot C into Cc into Tc2 minus Tc1. Change in internal energy. The rate of heat transfer is equal to change in internal energy. Or we can write Q is equal to capital Ch into delta Th is equal to capital Cc into delta Tc. What is Ch? That is mass flow rate into specific heat. That is heat capacity rate. That is called as heat capacity rate. Delta Th is the temperature difference for the hot fluid. Delta Tc is the temperature difference for the cold fluid. The another expression is area equation or sizing equation or LMTD approach. Q can also be calculated by U into A into mean temperature difference between hot fluid and cold fluid. That is another expression. U is overall heat transfer coefficient, A is the area of the heat exchanger, and delta Tm is the mean temperature difference or logarithmic mean temperature difference. This is logarithmic mean temperature difference. Why do we require the logarithmic mean temperature difference? Because there is a variable temperature difference between hot fluid and cold fluid. So if we write delta Ti this and delta Tf this temperature difference is delta Tf. So delta Tm can be calculated by delta Ti minus delta Tf upon natural log of delta Ti upon delta Tf. That is called as mean temperature difference between hot fluid and cold fluid. That is called as logarithmic mean temperature difference. For parallel flow heat exchanger, how to write? In case of parallel flow heat exchanger, this is Th1, this is Th2, this is hot fluid, this is cold fluid. You do not have to memorize. This is Tc1, this is Tc2. So if we want to write, this is delta Ti and this is delta Tf. So LMTD is given by Th1 minus Tc1, that is delta Ti, minus Th2 minus Th2 minus Tc2 upon natural log of Th1 minus Tc1 upon Th2 minus Tc2. That is mean temperature difference or delta Tm for the parallel flow heat exchanger. Similarly, for counter flow heat exchanger, this is Th1, this is Th2, this is hot fluid, and cold fluid is moving like this. This is Tc1 inlet temperature, this is Tc2. So this is delta Ti, this is delta Tf. So if we want to write delta Tm for counter flow heat exchanger, then delta Ti, that is Th1 minus Tc2 minus Th2 minus Tc1 upon natural log of Th1 minus Tc2 divided by Th2 minus Tc1. That is delta Tm for counterflow heat exchanger. And one special case for counterflow heat exchanger, that is important. If the product of mass flow rate of hot fluid and specific heat of hot fluid is same as the product of mass flow rate for the cold fluid and specific heat of cold fluid, or we can say if CH is equal to CC, then we can say delta TH will be equal to delta TC, isn't it, from the energy conservation equation? In that case, the temperature profile will be linear. The temperature profile will be linear like this. Here, this is delta Ti. Here, delta is delta Tf. This is the hot fluid, TH1. This is TH2. It will be straight line TC1 and TC2. This is the special case. If you will use the formula, then you will get 0 by 0 form. So using L hospital rule, what we can say, delta Tm will be equal to delta Ti is equal to delta Tf. Or we can say that is, LMTD will be equal to TH1 minus TC2, or it can be written as TH2 minus TC1. That is LMTD. That will be LMTD. For complex heat exchanger, LMTD will be equal to, what is complex heat exchanger? It can either be closed flow or multipass. Cross flow or multipass. Delta Tm is equal to LMTD correction factor into delta Tm for counterflow heat exchanger. There is a correction factor defined. So LMTD correction factor is the deviation of LMTD from the corresponding values for the counterflow heat exchanger. F is always less than 1. That is called as LMTD correction factor. Last 10 minutes, guys. Last 10 minutes. Performance wise, for same terminal temperature, TH1, TH2, TC1, TC2, if they are same, then we can say delta Tm for counter will be greater than delta Tm for cross flow or complex heat exchanger is greater than delta Tm for parallel flow. And for a condenser or evaporator, the relative direction of flow is not insignificant. For a condenser or evaporator, delta Tm for counterflow condenser will be same as delta Tm for cross flow condenser will be same as delta Tm for parallel flow condenser. The relative direction of flow becomes insignificant as far as their thermal performance is concerned when there is a phase change in any one of the fluid. And the last basis of analysis is effectiveness NTU approach. That is our last part of the analysis of the heat exchanger. What is effectiveness? The ratio of actual heat transfer to the maximum possible heat transfer rate. It represents the thermal performance of the heat exchanger. It is less than 1. So it must be as much as possible. It is the ratio of actual rate of heat transfer to the maximum possible heat transfer rate, and the heat transfer rate can be maximum possible for a counterflow heat exchanger of very large area if any of these conditions are getting satisfied. Either TH1 is equal to TC2 or TH2 is equal to TC1. Either of these conditions are getting satisfied. So effectiveness can be written as Q actual by Q maximum, and Q maximum will be equal to, here Q maximum will be equal to C minimum into TH1 minus TC1. That is the maximum heat transfer rate. Q actual can be written as CH into delta TH upon C minimum into TH1 minus TC1. Either you write this way, or CC into delta TC upon C minimum into TH1 minus TC1, or you can write the numerator as U into A into LMTD upon C minimum into TH1 minus TC1. And what is C minimum? C minimum is the minimum value between CH and CC, heat capacity rates. C minimum is the minimum value between CH and CC. That is how we can define the effectiveness of the heat exchanger. Numerator can be calculated by either of these ways. Delta TH is equal to TH1 minus TH2 and delta TC is equal to TC2 minus TC1. Right? For a particular size, for area is constant, we can say effectiveness of counter will come out to be greater than effectiveness for cross, will be greater than effectiveness for parallel. And for a condenser or evaporator, effectiveness of counter is same as effectiveness for cross is equal to effectiveness for parallel. If there is a phase change, the relative direction of flow becomes insignificant as far as their performance is concerned. And the last one is NTU, number of transfer units. It is a dimensionless parameter which measures the size of the heat exchanger. It is about the economic performance. Effectiveness is about thermal performance and NTU is about economic performance of the heat exchanger. Economic performance. So it is a dimensionless parameter which measures the size of a heat exchanger for a given heat load. It must be as low as possible for a compact design for better economic performance. And NTU is given by UA by C minimum. I have already told you C minimum is minimum among CH and CC. CH and CC are heat capacity rates. They are not specific heats. CH and CC are heat capacity rate. What is C? C is equal to mass flow rate into specific heat. UA by C minimum. A is the area, U is the convective heat, overall heat transfer coefficient. It is dimensionless parameter. It is unitless parameter, but it gives the size of the heat exchanger. So it gives the economic performance for a constant constant capacity. We can say NTU for counter will be less than NTU for cross, then NTU for parallel. And for a condenser or evaporator, NTU for counter will be same as NTU for cross, will be same as NTU for parallel. NTU will be same for all of them. All right. And the last portion, effectiveness in terms of NTU. Effectiveness in terms of NTU. For parallel flow heat exchanger, that is important. For parallel flow heat exchanger, effectiveness is given by this expression where C is, what is C? C is given as C minimum by C maximum. What is C? C is equal to C minimum by C maximum. That is called as heat capacity ratio. It is the ratio of heat capacities, C minimum by C maximum. 1 minus e to the power minus n, 1 plus C upon 1 plus C, and for counter flow heat exchanger, it is given by this expression. These are the expressions for parallel and counter. Now, if we modify this value, C lies between 0 and 1. C is lying between 0 and 1. For C is equal to 0. When do we have C is equal to 0? If delta TH is 0 or delta TC is equal to 0. In that case, CH or CC becomes infinite. When CH or CC becomes infinite, that is condenser or evaporator, C. For a condenser or evaporator, C will be equal to 0. C will be equal to 0. So when C is equal to 0, effectiveness for counter is equal to effectiveness for cross flow condenser is equal to effectiveness for parallel. If we put C is equal to 0 in the previous expression, If we put C is equal to 0 in the previous expression, if we put C is equal to 0, then both will give rise to the same expression, that is equal to 1 minus e to the power minus NTU. If C is equal to 1, that is when CH is equal to CC, or we can say delta TH is equal to delta TC. In that case, C will be equal to 1. If C is equal to 1, for parallel flow heat exchanger, effectiveness is given by 1 minus e to the power minus 2n by 2. And for counter flow heat exchanger, we will use L'Hospital rule. That is important. When C is equal to 1, and if it is a counter flow heat exchanger, you will get 0 by 0 form. So by using the L'Hospital rule, effectiveness for counter flow heat exchanger is NTU upon NTU plus 1. That is the expression for counter flow. C is equal to 0. All will have the same expression for the effectiveness. For C is equal to 1, there is no problem with the parallel flow. Put C is equal to 1 in the previous expression. If you put C is equal to 1, then it will be 1 minus e to the power minus 2n upon 2. But counter flow, if you will put C is equal to 1, then you will get 0 by 0 form. So by using L'Hospital rule, we can develop the expression for effectiveness. This is very, very important. So whenever you are having a counter flow heat exchanger, please check whether C is equal to 1 or not. Accordingly, you can use the formula. And that completes our discussion for the heat exchanger. I hope you guys liked the session.